participants gathered here today and also who have joined in online mode for the International Science Workshop on Trishna. This workshop marks a significant milestone in collaboration journey of Trishna mission, an ambitious partnership between the Indian Space Research Organization and France Space Agency, CNES Trishna. Trishna, which stands for Thermal Infrared Imaging Satellite for High Resolution Natural Resource Assessment, which symbolizes the spirit of international cooperation in leveraging the cutting edge technology for sustainable future. We are deeply honored to have with us today some of the most distinguished minds in space and technology. Let me take this opportunity to invite our esteemed dignitaries on dais. Director SAC, Mr. Nilesh Desai, Professor V.K. Dadwal, Ex-Director NRSC, Mr. Philip Messengrand, Trishna Program Manager CNES, Mrs. A.M. Naga Lakshmi, Project Director Trishna, Mrs. Rashmi Sharma, Deputy Director IPSA, Mr. S.S. Sarkar, Deputy Director SEDA, Mr. I.M. Bahuguna, Chair of Local Organizing Committee, and Bimal Bhattacharya, Convener for this workshop. Please, sir. Your presence today adds the immense value to this event, and we are grateful for your time and support. So moving ahead, now I request to set the tone for today's event. I invite Mr. Bahuguna, Local Organizing Committee Chair, to deliver welcome address. Please, sir. Sir, welcome address. Sir.
I have to be quick because our director sir is occupied. He has to leave also. Respected Dr. Vinay Kumar Dadwal, Indira Gandhi Chair, Professor at National Institute of Advanced Studies, former Director NRSC, former Scientist of SAC, and former Director of IIRS Dehradun, and today's guest of honor of this inaugural session, at this inaugural session of this international workshop on high resolution thermal earth observation, Dr. Philip Mason-Grand, the project manager of Trishna mission from CNES, Shri Nilesh Desai, Director Space Application Center, Shri Soumya Sarkar, Deputy Director of SEDA and Distinguished Scientist of Space Application Center, Dr. Rashmi Sharma, Deputy Director of Earth and Planetary Sciences and Application Area, Dr. Nag Lakshmi, Project Director of Trishna Mission at UR Satellite Center at Bangalore, Dr. Bimal Bhattacharya, who is Group Director of Agriculture, Forestry and Ecological Group, and the force behind this entire workshop and behind, thermal Earth observation program at Isro. Senior SMC members, Controller SAC, and other SMC members of Space Application Center, distinguished scientists, research scholars, engineers, and other delegates from all over the globe who are participating in this workshop. Namaskar, good morning, and very warm greetings, and welcome to all of you at Space Application Center. Space Application Center is one of the important organ of Indian Space Research Organization located at Ahmedabad. Basically, it's a center for payload development of various kinds. It is not mere customary to welcome you in the beginning. It is our pleasure, it is our privilege, it is our honor to welcome all the delegates who are the authorities in the subject and who are the experts in the subject from all over the globe, and the delegates who have joined this workshop and to exchange their views, etc. And we welcome you all at this, and it is an honor for us to welcome all of you. We hope that you will enjoy the discussions and interactions in this workshop. I'd like to inform you that November to February is a very pleasant time in Ahmedabad. The temperature ranges from 32, 33 degrees maximum, and minimum is around 20 degrees or 18 degrees, like that. So it's a very pleasant time for 4 months in Ahmedabad. But of course, in next 3 days, we hope that you will enjoy the pleasant weather at Ahmedabad. You will also enjoy, I hope, we are sure that you will also enjoy the hospitality of our SAC colleagues. And also, Ahmedabad is a World Heritage City of India. So you will also enjoy the culture and the Indian cuisine and the food in Ahmedabad, traditional Indian style food made for all of you. Above all, you will also like the scientific culture and the temperament of our SAC colleagues who have joined, to welcome all of you and to share, their experience with all of you in this workshop. And again, welcome to all of you, and especially our guest of honor, Dr. Vinay Kumar Dadwal, who is the authority. I'd like to take this opportunity to inform you that India has a program, foremost program in agriculture and ecological remote sensing. Out of all the remote sensing which is going on in India, out of all, agriculture and ecology happens to be the foremost. And the person behind this program in entire India is Dr. Dadwal. So with these words, I'd like to close my welcome remarks and invite you for the next program.
Yeah. Thank you, sir, for your warm and inspiring welcome note. Your words have set a positive tone for a day, and we look forward to the meaningful discussions ahead. Thank you. To invoke the blessing of wisdom, light, and knowledge, let us now proceed to a traditional lamp lighting ceremony. I invite all the dignitaries on the dais to join for this auspicious moment. Please. While the dignitaries lamp the light, we will be graced by the soulful chanting of Saraswati Vandana by Mr. Partho Ghosh. Partho, please.
सरस्वती महाभद्रा महामाया वरप्रदा श्रीप्रदा पद्मनिलया पद्माक्षी पद्मवक्त्रका शिवानुजा पुस्तकवृत् ज्ञानमुद्रा रमापरा कामरूपा महाविद्या महापातकनाशिनी महाशाय मलानी च महाभोग महाभुज महाभागमहोत्साह दिव्याङ्गसुरवन्दिता महाकाली महापाश महावार महाङ्कुश ईटा च विमल विश्व विद्युन्माल च वैष्णवी.
Thank you, Partho. As a token of our appreciation and commitment to the sustainability, we now present supplings to our dignitaries. I now request Mr. Arvind Sahai to welcome Mr. Nilesh Desai, Director SAC. Now I request Mrs. Dimple Garg to welcome Professor V.K. Dadwal. I request Satish Kumar to welcome Mr. Philip Messengren. Now I request Mr. Dalaka to welcome Mrs. Nagalakshmi ma'am. Now I request Mr. Arvind Sahai to welcome Mrs. Rashmi Sharma ma'am. I request Dimple Garg to welcome Mr. S.S. Sarkar. Now I request Satish Kumar to welcome Mr. Bahugan Asif. Sir is a part of this local organizing committee. Now I request Dheeraj Adaleka to welcome Mr. Bimal Bhattacharya, sir. Thank you all. Now to proceed further, to give a brief overview of SAC activities, I request Mr. Nilesh Desai, Director SAC, to give the address on.
Good morning, everybody. The dignitaries on the dais, Dr. Dadwal Sahab, our distinguished friends from France, Soumya Sarkar, Naglakshmi Madam, Rashmi Sharma, Bimal Bhattacharya, Bahugana Sahab, and all the dear participants from France as well as various other institutions, as well as my dear friends, colleagues from SAC and Isro. At the outset, let me welcome all of you for this very important international science workshop on high resolution thermal earth observation. And sorry for jumping the queue because I was supposed to address afterwards. I have some engagement by 11 o'clock, so I have to leave. So I generally start all my addresses either with disclaimers or apologies. So today with apology, I'll be leaving after my address. So please pardon me for that, Sadwal Sahab. So let me welcome once again all of you, and it is a very important event in the French-Indo collaborations, especially related to various Earth observation missions. We have a long history of collaborative efforts, starting with long back. We had worked on megatropics, followed by Saral Altica, and now we are on to the Trishna project. I always forget the full form of the Trishna, because when initially we were trying to name this particular mission, because Trishna, if you see, it is only French acronym. So there is no mention of what Indian part in that particular mission. So I suggested that we should add something so that it reflect the contribution which India is going to do with our visible and other infrared sensors which we are going to give as a part of this particular mission. But the importance of this particular mission need not be emphasized more. All of you know that thermal imaging is very critical, and especially when in the world Earth observation scenario, we find that there is a lack of this particular type of observations. And with the LSTM from ESA and SBG from NASA, long away by 2030 timeframe only they will all will be available. So in between we need very good observations of Earth in thermal infrared band, and that will be filled by this particular mission. It will really have a lot of utilities for various applications. And today we have a distinguished guest in form of Dr. Dadwal Saab, who had been a mentor of all my application colleagues here. And as pointed out by Dr. Bahuguna, he has been a pioneer in various activities related to remote sensing, especially for agriculture, forestry, and many other domains. So let me welcome sir and thank for being here at a very short notice. And today, of course, it is an important day for us, for we are having this science workshop for next 3-4 days. But today we are celebrating India as a national integration day, remembering the birth date of our former Prime Minister Indira Gandhi. And she was the Iron Lady of India. All of you may be aware of that. And incidentally, today we also celebrate International Men's Day. So it is ironical that the lady's birthday we are celebrating as a International Men's Day. But it was told that she is a man among all the people in her cabinet. But anyway, remembering her because she promoted a lot of activities related to science and technology. And of course, the current government is giving a lot of emphasis, which culminated into our efforts related to soft landing on Chandrayaan-3 South Pole. So that was really a massive effort on the part of ISRO. And of course, we are basking in the glory of that particular mission. But more importantly, the activities which we do for planetary exploration is only 20-25% part of the work which ISRO does. The rest of the thing is what we are here today to discuss, that is Earth observation, communication, navigation, and all those aspects. So predominantly, this being the birthplace of Vikram Sarabhai, all of you may be aware that India space program originated from this particular place in Ahmedabad. And his vision was that we want to use space research and technology for the benefit of common man and society. So fulfilling that dream of Dr. Sarabhai, Earth observation in electro-optical domain, especially thermal infrared, which we were lacking since last many years. So I'm very glad that this mission will fulfill all the requirements which we have been looking for, and with the complementary payloads from our side being developed by our team led by Dr. Soumya Sarkar. And of course, we are looking forward to various new applications of this particular mission, and under the guidance of Dr. Rashmi Sharma and her team. So I wish all the best for this science workshop and hope that we'll have very good deliberations over these next 3-4 days. And once again, I welcome all the delegates for this important conference related to science and applications of these particular missions. So I wish all the best and thank you for coming here. Thanks.
Thank you, sir, for your brief overview. Now the moment has come to release the abstract companion of this workshop. I request all the dignitaries to kindly join the hands in releasing the companion. The companion reflects the depth of research and collaboration this workshop embodies. We hope it serves a valuable resource for all the participants. Yeah, thank you all. Now I invite Mr. S.S. Sarkar, Deputy Director, Sensor Development Area, to give opening remarks on Krishna evolution.
Respected dignitaries on the dais, esteemed participants, delegates from different countries, and my colleagues. First of all, Suprabhat, bonjour, a very good morning to all of you. Yesterday evening when Dr. Bimal told me that I have to give a bit of a history of how it evolved actually, so far as this mission is concerned, the Trishna mission. So since it was a bit of a history telling, so I'm bad at remembering dates. So I just am carrying this paper where we are having actually all the dates and it's all important dates actually how this concept or the mission evolved. Krishna, as our directors are told, and most of you would be aware as well, that Trishna is basically a Sanskrit word and it means thirst. It's like in Hindi that is called pyas. So it's basically the thirst for when you feel actually the need for water, kind of. So that is one connotation. There is another connotation which means basically yearning. That is a strong desire to achieve something. Your aspiration, strong aspiration. So maybe the second connotation actually fits in very nicely here because this mission was conceived actually to meet with the stated objectives, and those were actually to study the ecosystem stress and water use, and also actually coastal and inland waters, and thereby actually add to the body of human knowledge, and also actually come out with practical applications for the global community as such, and of course scientific community. Krishna was conceived actually way back on 17th June 2014 to be precise, when a technical discussion was held between Isro and CNES at Bangalore for a future mission in thermal infrared in order to address the objectives that which I just now mentioned. Then in 2015, actually, there was a cooperation agreement signed between Isro and CNS, and that happened on 10th of April 2015. And that provided that broad framework actually because that mentioned about reinforced cooperation in space activities. And under the umbrella of this cooperation agreement is in 2016, an implementing arrangement was signed between ISRO and CNES in the august presence of the Honorable Prime Minister of India and then Honorable President of France. And that's what actually gave Trishna a formal base on a foundation. Then between April 2016 to May 2017, many scientific and technical discussions took place. And it was felt that there is a strong need for inclusion of a payload in visible and shortwave infrared, that is the vSphere payload, which our director also mentioned about. And preliminary instrument configuration studies were carried out. It was decided that the feasibility study for the development should be carried out in two phases. Phase 1, which had a duration of 6 months, leading to mission definition review, that is MDR, and phase 2 of duration of 2 years nearly, leading to preliminary requirements review. And accordingly, in November 2017, we had this mission definition review held in again Bangalore, and it was held with an objective to finalize scientific requirements, because science what drives the mission actually. So it was very important to firm up the scientific requirements and also to define a technically feasible and cost effective concept which meets the requirements of mission and system, data policy, payload concept, platform configuration, launch strategy, cost effectiveness, cost sharing, of course work share and responsibility is between ISRO and CNES. Then from April 2018 to August 2019, there were various meetings that took place. There were science meetings, there were meetings on instruments for mission and also on spacecraft interface. So this was the time when a lot of discussions took place. And 28th September to 3rd of October 2019, we had this preliminary requirements review held, where the outcomes of mission definition review were discussed. They were reviewed and approved. And besides, it is in this actually PRR, that is preliminary requirements review, that besides the primary objectives of ecosystem stress, water use, and coastal and inland waters, there were certain secondary objectives that were also identified. And those secondary objectives were on urban fluxes, solid earth, which basically consisted of or consists of, I would say, volcanoes and earthquake, etc., and also cryosphere and atmosphere. Then in March 2020, the steering committee meeting took place, which basically again actually addressed or reviewed the PRR proceedings and approved those proceedings. And that's how actually the work started. And around the same time, that is in March 2020, the CNES program approval came. And then came COVID. So almost like for 1.5 years, all of us were affected, as you are aware. So once we were through from that difficult phase, then in 2021 to 22, the TIR payload and the system PDR took place from the CNES side. The Isro approval came a bit time coming, but however, it finally came on January 2023 when the program approval was obtained by Isro and the financial sanction followed. That is what was in April 2023. Then in June 2023, the implementation arrangement was again actually revised and it was signed between Isro and CNES, and that basically provided the legal and I would say the procedural framework to proceed further with this mission. Accordingly, in November 2023, we had system interfaces and performance validation review, that is SIP VR1, which was held at URSC, and it addressed various aspects like system developmental plan, product definition, then data policy, then compliance of the system to the data policy and the science requirements, etc., etc. Then one important milestone for SAC, that is for us or for ISRO, happened on December 2023 when we had this vSphere payload BDR baseline design review held. In Q1 of this year, we had spacecraft and ground segment PDR completed. And in October 2024, just very recently, SIPVR2 was held at the CNES. So this is where actually, as on date, we stand in terms of development for this mission. And what is the road ahead? So if you look at what is the road ahead, it is basically in December 2024, we are going to have the vSphere payload PDR, and that would be followed by spacecraft and payload and ground segment CDR. So it is planned next year, that is in 2025. And in 2026, both the payloads TIR and SWIR, the payload deliveries are expected, leading to spacecraft integration and subsequently to launch. So this is in nutshell actually that like how the mission was evolved. So a bit of a history, and I sort of actually tried to traverse or navigate and bring you to the present status. So that is where we stand today. So I take this opportunity to welcome all of you, to all the delegates, and wish for a very fruitful, invigorating, and stimulating discussions. And certainly science is very important. So if there are any outstanding issues or there is anything which needs to be reinforced, I'm sure actually it will be addressed during this workshop. So once again, actually, I welcome all the delegates, all the participants, and wish you all the best. Thank you.
Thank you, sir, for your encouraging words. You have shown the complete evolution map of Trishna project, and I hope in near future we are going to meet the milestone defined for this project. Now, to provide an overview of this workshop, I request Mrs. Rashmi Sharma, Deputy Director, Earth and Planetary Science and Application Area, to address the gathering.
Thank you, and very good morning to all of you. Dignitaries on the dais, participants from various national and international institutions, from different space agencies, my own ISRO colleagues, online participants, A very warm welcome to all of you for this 3 days of International Science Workshop on High Resolution Thermal Earth Observation. So it gives me a great pleasure to tell you that in this 3 days of deliberations, we are going to have in-depth discussions on different facets of this thermal remote sensing, and of course with a special emphasis on Kenner's Isro Trishna mission, where many of the applications would be synergized using the thermal data along with the visible and the SWIR data. And also we're going to focus on the LSTM and SBG missions as well. So I'm very pleased to inform you that there is a great amount of interest towards in the national and the international scientific community towards making use of this high resolution thermal data sets, and primarily for understanding the water stress for in the ecosystem domain. And I'm sure that when the data comes, it'll be able, it'll unravel many of the outstanding science issues and that are yet to be answered. It is said that well begun is half done, and we are very, very grateful to Professor V.K. Dadwal sir for gracing this occasion. And I'm sure with his vast experience in this domain under the ecosystem research area, his talk is going to inspire all of us, and it will set the context of this 3 days of scientific meeting. So thank you, sir, for accepting our invitation. The workshop technical sessions have been carved out very, very meticulously. Actually, it starts with the discussions on the global thermal missions that are going to be there in a couple of years, and which will be followed by the retrieval challenges that we face for this high resolution data sets, and challenges mostly for the terrestrial, coastal, cryospheric, and hydrological parameters. We all know that calibration and validation is integral to any spaceborne missions, and that too for such a high resolution mission, it becomes even more critical to ensure the data quality. So plan for calibration, validation, ground instruments, campaign plans, etc. are very challenging, and I'm sure that the dedicated session in this meeting is going to deliberate upon all those aspects towards meaningful and high accurate data products and science products data sets. Another aspect which is very, very important is the development of the downstream applications, and addressing some of the key outstanding questions. And these are actually at the heart of any satellite missions that we launch. So towards this also, the session is dedicated to address water stress in ecosystem. And another important aspect which will be discussed is the urban and coastal heat extremes. So I'm sure that the outcome of these 3 days of deliberations on all these aspects, retrieval, calval, and science applications, will shape the future science and applications from the forthcoming thermal missions. And very, very importantly, it will also sensitize the users and researchers towards fully utilizing the data sets which are going to come from these missions. So with these words, I conclude, and I wish the workshop a great success. Thank you all.
Yeah. Thank you, Dr. Rashmi Sharma, for providing a comprehensive overview of this workshop. Your insights underscore the significance of this collaborative initiative, and we are excited to dwell deeper into the session planned for 3 days. I now invite Mrs. Nagalakshmi Ma'am, Project Director Trishna, to share her thoughts and insight with us.
Good morning to all the dignitaries on the dais, representatives from across the globe for this workshop, and participants from India, and my dear colleagues from different centers of ISRO, which are part of Krishna project. Greetings and very warm welcome to this workshop. It is with great enthusiasm and commitment we are presenting this workshop celebrating the collective efforts towards the Trishna mission. Trishna represents a significant advancement in high resolution thermal earth observation, offering new insights into water resource management, urban heat studies, and ecosystem monitoring. This initiative, a collaboration between Isro and KENES, highlights our shared commitment to sustainable solutions. Trishna, which is a joint collaborative project between Isro and KENES, carrying state-of-art thermal infrared and visible shortwave infrared payloads, enables high-resolution thermal imaging of natural resources. The high-resolution data will be simultaneously processed at payload data centers to provide a consistent and systematic record of various biophysical variables along with the surface temperature profile to model surface energy balance. The payload data will enable monitoring of urban heat islands and fluxes along with evapotranspiration for estimating ecosystem stress and water use. Trishna is designed to acquire data globally using 4 thermal infrared bands around noon and midnight and 7 visible and shortwave infrared spectral bands with a spatial resolution of 60 meters, which stands as a unique resource for the global community. This science workshop will rightfully serve as an excellent platform, bringing together Indian and global science community and various user agencies, departments to understand and involve in the utilization of Trishna data and science products for the benefit of mankind. Besides the technical sessions, the organizing committee had also planned a tutorial which was a preamble to this workshop on modeling tools for thermal radiative transfer, surface energy balance, and evapotranspiration to further enhance the outreach and utility of this unique international science workshop to the participants. We are embarking on a journey to utilize Trishna's capabilities to tackle global environmental challenges with precision and impact. As we look forward to the insights and innovations this collaboration will bring, we are reminded of the vital role Earth observation plays in sustainable development. This workshop will serve as a catalyst for knowledge sharing, research, and progress in our mission to understand and protect our planet for future generations. We at India Trishna Project team and our counterpart at KENES do understand the importance of this mission, and we know the commitment and the timelines we need to stick on so that we reach the goal of launch at the required timeline and the synergy which is required with the other follow-on missions. From configuration with respect to the science requirements and deciding on the equipments required, instruments required in order to meet this science mission, and configuring a satellite to carry these payloads to the space and addressing the requirements at the ground stations and the data products and the disseminations so that this data will be well received and well serve the scientific community with respect to the science objectives which was conceptualized initially. And at ISRO, we know that our objective is to realize and launch communication satellites, navigation satellites, remote sensing satellites, and space science missions to meet the requirements of the nation. ISRO has long association with KENES and has jointly developed various missions like SARAL and Megatropics. And we hope that this workshop fosters valuable collaboration and advancements in the field of Earth observation, and our collaboration with Isro and CNES will continue, and this workshop will aid towards that. Thank you so much.
Thank you, Madam, for providing insightful address. With the Trishna mission, we are eager to witness its remarkable impact on natural resources and management. We are delighted to have Mr. Philip Messengren, Trishna Program Manager from CNES, among us. May I now request Mr. Messengren to address the gathering, please.
Thank you. Good morning. Dear directors, dear project managers and project members, dear principal investigators and scientists, dear conveners and dear colleagues, I'm very glad and it's an honor for me to represent CNES in this opening session as a program manager, it was said. Program manager of Trishna at CNES. I have three principal messages, three principal things that I'd like to say this morning. The first one is concerning history of a project. The second one is concerning the programmatic strategy of our agencies, and then I would like to put the emphasis on the scientist involvement in the project. So concerning history first, it's a fact that Isro and CNES really have a long common history in their successful partnership. First with Megatropic, that was launched in 2011, and then Saral, we all remember Saral, launched in 2013, and these were two successes. Today, our two space agencies continue their collaboration with Trishna, that will be launched within the next 2 years by the end of 2026. Among all these years in the history of our partnership, for us, precisely concerning Trishna, there is a milestone which is important for CNES. It's the year 2019. In 2019, it's very important for Trishna at CNES and for Isro as well, because it was the time of the preliminary requirement review, which was concluded successfully, thanks to the project managers and thanks to all the people that were involved. And the PRR, the preliminary requirement review was has oriented the project toward the phase A at CNES. An happy end after 5 years of work that was initiated at SAC, as mentioned by Philippe Gamet last Sunday. The history began here in this Isro center. 2019 is also a very important year because at CNES in France we also had our own prospective seminar in October 2019, and during that seminar Trishna has been declared as a priority by all the French research institutes. Then in 2020, the few months later, in fact, the PRR steering board of CNES decided to switch toward the phase B. Then we all regret the COVID time period that we will try to forget. After the COVID, the IA, the implementing arrangement was signed by Isro, which in turn switched to the phase B. Since that time, two successful CPVR occurred. It was mentioned previously, and I take it's an opportunity for me to thank and to pay tribute to all the Isro and SNEC and CNES project members, and especially the project management, Miss Nagalashmi and Thierry Carlier, for their work and the way they manage this project and all the people involved in it. The second part now is dealing, as I said initially, is dealing with the programmatic strategy and its consistency with all the international space agencies. In France, we have a very strong interaction with our colleague of the European Space Agency. And concerning the water cycle, we have some missions like SMOS, which is a mission of the Earth Explorer program, of the European Earth Explorer program. By the way, SMOS is going to be extended until 2028. It has been decided very, very recently. But of course, there is also the Copernicus program, and with the current Sentinel-1, 2, 3, and 6 that are very useful in the modeling, in the integrated modeling of the water cycle. This Copernicus Sentinel and the next generation, and among the next generation, there is of course LSTM, there is also S3 and JTOPO, and we all know that Trishna is the precursor of LSTM, and that, for example, SWOT, CNES NASA success is the precursor of S3 and JTOPO, which means that there is a strategy. Last but not least, there is NISA to be launched very soon, and we expect a lot from this the synergy of Trishna with NISA, with SWOT as well, to address the water budget issue. While Trishna will be combined with LSTM and SBG, and the gathering of their visiting capacity will allow to address the evapotranspiration fluxes and their calculation. I know, we all know that a strong effort has already been paid to optimize this multi-mission synergy in terms of products definition, in terms of LTBDs, in terms of orbit, and in terms of calibration validation. Third and last point, I said at the beginning, I would say some few words concerning the scientist involvement in that program, in that project. Maybe you don't know, but last February in France, we have held an inter-institute committee meeting, which has confirmed the involvement, of course, of the French Science Institute, all the French Science Institute and other public authorities. This meeting has shown many things. It has shown first a satisfying readiness of LTBD levels. It has shown, and this is important, an increasing human and financial resources allocated to our laboratories. It's very important because without these resources, we cannot work. Additionally, we will know that we still have to go further into the research process, which is necessary. For example, on the thermal infrared and visible synergy, concerning directionality, concerning the assimilation of albedo and evapotranspiration calculation, but also on the Trishna data assimilation into agrometeorological models. It was stressed, we are at SAC, and applications are very important. And we all know that application need reliability, which makes the calibration validation exercise a very, very important issue. This is why, for example, it will require special efforts to coordinate our validation and our cross-validation at the level of our respective payload ground segments. Application, to finish, application development is very important at Isro and at CNES. It was reminded to me by Dr. Bhattacharya a few days ago. And this is why we have at CNES downstream program for the emergence of application, to facilitate the emergence of application. And in the domain of application, the last key word is timeliness. Timeliness is a crucial issue that will take advantage of the gathering of, by the way, of SBG, of LSTM, and of Trishna. To finish, technical and research team have already made impressive efforts in all this domain, in all the domains that I've mentioned, and I'm sure this workshop will be a very fruitful and useful meeting, and it will be very helpful to achieve our scientific and applicative objective. I'd like to express again my sincere gratitude to Isro and SAC for hosting this meeting, with a special thanks to Dr. Bimal Bhattacharya for his tremendous involvement in the preparation of this event. And thank you to all of you. I'm sure we're going to have an excellent meeting during the 3 day. Thank you.
Thank you, sir, for highlighting the international collaboration and the vision behind the Trishna. Your perspective reinforces the importance of shared goal in advancing the space research. Thank you. I now request to all the dignitaries to kindly join the audience as we continue with the program. Please. keynote का है हाँ तो इनको ऑर्गेनाइजेशन लेकर बोलिएगा सबको गढ़वाल सर को थोड़ा लेकर रखेंगे ठीक है बाद में
एडवांस हम यही रहेंगे ना एडवांस हम यही रहेंगे अब आएंगे
उनको बोला है यही रहेंगे
यही रहेंगे ना सर
Next, we are going to have a keynote address by Dr. V.K. Dadwal. So before we proceed, it is my privilege to invite Dr. Rahul Nigam to introduce our esteemed guest of honor, Dr. V.K. Dadwal.
Very good morning to all. It is an absolute honor to welcome you all to this extraordinary gathering at International Science Workshop on High Resolution Thermal Earth Observation at Space Application Center, Ahmedabad, where brilliant minds converge to unveil the advances of thermal sensing. In the quest for knowledge, we are privileged to have with us luminary Dr. Vinay Kumar Dadwal. Professor Vinay Kumar Dadwal is currently the Indira Gandhi Chair, Professor for Environmental Sciences at National Institute of Advanced Studies, Bengaluru, in India. He has more than 38, you can say 4 decades of research work and leadership at Indian Space Research Organization under different centers. He was a director of Indian Institute of Space Sciences and Technology, Trivandrum, from 2016 to 2021. He was director of National Remote Sensing Center, Hyderabad, from 2011 to 2016. He was a dean of Indian Institute of Remote Sensing, Dehradun, from 2004 to 2010. And concurrently, he held the post of director of UN Center for Space Science and Technology Education in the Asia Pacific during 2005 to 6 and 2009 to 10. He obtained his PhD in plant physiology from very prestigious institute termed as Indian Agricultural Institute, New Delhi, and joined Space Applications Center, Ahmedabad, in 1983. In the Space Applications Center, he headed the crop inventory and modeling division, and we are basically all the kids from that division. His research focuses on developing application of Earth observation data for vegetation, include agriculture and forests, and very importantly, land surface processes, hydrology, biogeochemical cycles of carbon, forest dynamics, and disaster management support. He has co-authored more than 325 peer-reviewed journal publications, which have more than 10,500 citations, and co-guided more than 12 PhD students. He has been the chair of Subcommittee on Science and Technology of UN Committee of Peaceful Uses of Outer Space at Vienna in 2016. He was a president of Technical Commission 8 of International Society of Photogrammetry and Remote Sensing, ISPRS, 2012 to 2016, president of Indian Society of Remote Sensing, 2012 to 14, president of Indian National Cartography Association, 2013. He is a fellow of NAS, Indian Society of Remote Sensing, Dehradun, Indian Meteorological Society, New Delhi, International Academy of Astronautics, and received many awards and recognition. Because so many awards are listed, so I do not want to cut a list time. And I'm just shortcutting that, and presently chairing 2 important technical groups: Technical Expert Committee for National Geospatial Program, Departments of Science and Technology, Government of India, and also chairing the Research Advisory Council for National Bureau of Soil Science and Land Use Planning, Nagpur. And now I request you all, please welcome him with a huge round of applause. Thank you. Over to Dr. Good morning. Thank you, Rahul, for very kind words. Let me at the outset thank the organizers, Director SAC Nilesh Desai, and my friend Dr. Bimal Bhattacharya for inviting me to be present today on what I'm sure will be written in history as this Trishna Science workshop at SAC. And there cannot be any better place than SAC to discuss the genesis of all new eras of remote sensing. I joined SAC in June 1983, and we are very lucky that we are now in a hall named after Professor Yashpal. Professor Yashpal had just shifted out to Vienna to head the Unispace 2 by the time we joined, and Professor Chitnis became the director. The keynote address can be many things, but I specifically took the advice of three my friends, Bimal, Mehul Pandya, and Dr. Samudraya, who headed the SIDA just before, I think even before Dr. Soumya Sarkar was there. So the emphasis is not to really give you everything that is done in India, but still focus on next. We could just start by looking at thermal sensors developed at SAC. Even before this campus was built, Dr. George Joseph, he joined the SAC before the formally this campus, and they started working on an aircraft-based whisk boom sensor. And all the ones Mark 1, Mark 2, and HRMSs, they had a thermal channels. Then the INSAT 2A onwards, INSAT 1A was developed in USA by Ford Aerospace, but 2A onwards up to now, the last one is the INSAT 3DS, which was launched in February 2024. All of them had thermal bands. Unfortunately, thermal bands did not move down from geostationary to the Earth observation satellite. Instead, the thermal bands moved to the planetary exploration. So the group developed for Mars as well as Chandrayaan mission sensors which had thermal band. Now the thermal bands, they provide entirely complementary information of the vegetation, allowing us to compute energy balance, water balance, giving rise to hydrology studies, irrigation studies, and you can extend it even to the soil moisture and groundwater balance. Now this gets to be added by the other channel. So since the work on development of methodology is more towards the geostationary, I'll just take a couple of slides to discuss that the single channel from Kalpana, the approach as well as the validation of the product. Second, the split window for INSAT 3D and 3D repeat. Next. And all this data is actually available at very frequent interval from 2017 and 15 onwards, 10 to 15 you can see. But unfortunately these resolutions are 4 and 8 kilometer. They do not lend themselves to the natural resources and other applications. So most of the Indian community had to depend on Landsat and Ester for all the work. So I'm sure the techniques are being developed and have been also, I think, done at SAC, which will allow emissivity and LST estimation, which may be very useful for the Trishna mission. Now, if we just take the size measurement of emissivity. So that work also is being done, but I'm sure much more would have to be done. Next. So if you just take thermal remote sensing and we search the literature, so roughly I think 450 plus papers are getting published by the Indian remote sensing community, and they cover all types of things: agriculture, crop studies, stress, drought estimation, ecosystem studies on vegetation functioning, soil moisture, evapotranspiration and hydrology, measuring of urban heat island, geoscience, exploration, geohazards, open fires, forest, not only the forest fire, but the underground fires which happen in the coal mines in the Singhbum area. It allows us to estimate various properties of those fires, and also in cryosphere. So the standard LST has been very routinely used uh, to talk of the snow melt, and in even the whether it is gross primary productivity or NPP, the LST comes as a water stress scalar and then gets assimilated into the normal functioning. I just will illustrate some of the work. So here, more I think the work done at SAC, and I have tried to avoid the work done by me. And so the disclaimer is I do not endorse work, but all of them I think is important work. But it just talks of the type of areas and it talks of the challenges. Next. So one thing what has always I think been done is that whether you take Landsat or etc., very large effort is spent either in thermal sharpening or disaggregation. Obviously, I think many of the people feel that the current resolutions are not good enough. So what I'm hoping is when this Trishna comes and the type of resolution you have, there would be balance between the various bands, and then uh, because such disaggregation and sharpening, which predominantly have used vegetation as the covariate, haven't really led to very large scale operational applications. There have more been publications demonstrating accuracy assessment and algorithm development. So to move to the era, I think the resolution of the Krishna will be very important. More important is the MODIS has and LST has been used in most of the ecosystem models, as I explained to you, whether it is ET, whether it is the GPP and PP. I'm sure between a kilometer and 50-60 meter, there is a huge, uh, 400 time difference. So the type of features which will be discriminated and analyzed will be entirely different, and there should be a totally a new era for applications. The other part is uh, this data has a power to really using the LST and NDVI to know something about the soil, the near surface or the active root zone part of the soil. The challenge has been that all these techniques basically are local area specific, can't be extrapolated very large, and you really have to work on the same data. And the for generally for soil moisture, 20% RMSE is very good. So we really are looking at what type of RMSE would be there in the Trishna era. But more importantly, when you move from such type of studies with this type of data to a high resolution, you would immediately find that the soil properties for digital soil mapping are not that high resolution available. So then the thermal remote sensing would have moved forward, and the other areas will then have to be developed, including the soil physical properties, soil organic matter, soil water holding,
and permanent wilting point, right? That is something which I think will be there next. The other part is to really combine large number of approaches for soil moisture, uh, Landsat, the Sentinel-2, as well as the C-band SAR and other SAR. So such type of studies have been done to go up to even the field scale. Now, unless such studies are attached to a high repeat sensor, which allows you to make decisions of irrigation, then these studies do not really work in real time. So I think the 1 kilometer plus swath of Trishna will fill a very, very important gap to undertake this type of investigation, both from the retrieval of the surface soil moisture affecting the vegetation, as well as for the evapotranspiration. Next. Now, as far as the evapotranspiration is concerned, various approaches, energy balance, and other are available. I just thought I'll put this one, Dr. Bimal's work, where they are coupling the ET and the heat flux model to really explain the energy balance. I think a better energy closure will come, and the satellite driven approach will become more robust. And a challenge with this is to really calibrate the model and get for different vegetation type, you should have measurements which match this type of accuracy. So for that you require eddy covariance flux towers. Till 10-15 years ago, there were not many. Uh, so Dr. Bimal put the albedo towers. We had also put about half a dozen flux towers. Professor Shekhar Muddu also has flux towers, and I'm sure more are getting added. MOES has put 5. Forestry also, couple of them are there at FRI and the GB Pant Institute of Himalayan Development. More recently, under the World Bank Hydrology Project, NRSC has put about another dozen flux towers. So hopefully, I think the number of flux towers operating would now exceed around 35. So with this much, I think there would be, I think, more data to work on such model. Whether adequate or not still remains a question, because all vegetation categories are not, fully sampled. The hydrology project is talking concerned more about the irrigated areas. We were more concentrating on the forest in natural environment, and Ministry of Earth Sciences has concentrated, I think, more in the hilly region and coastal mangrove because of high carbon fixation. But this is an area I think we need to work. Next. Uh, then there would be many novel applications. So in this one such noon night LST application, what is demonstrated, what you see in the circle, is to really look at the crop which have been affected by the root soil borne disease. The whole idea is we are looking at a region which doesn't have soil moisture stress as measured by thermal data, but actually it has canopy dryness. Generally, in most of the crop stress studies with visible NIR and SWIR region, you can detect the stress, but you cannot ascribe the cause. So what is being expected is, with this type of thermal complementary data, you would be able to really ascribe the cause of the stress, at least in some instances. That, I believe, would be another step forward for agricultural applications. Next. The one very large number of applications you see is the urban heat island. I just thought I will share with you the large number of institutions, whether it is IITs, universities, and so many other uh, organizations which are on interest. Generally, the UHI has only concentrated on the variability, characterization, estimation of anthropogenic heat fluxes, right? And relating the UHI to LULC and urban expansion. Hopefully, we haven't come down to city zoning, city planning, and the number of heat waves is increasing in India, and we really need to manage the urban planners need to really manage the local urban environment, not only for the uh, people, but also to cut down very huge AC load and other things which are happening. But when it will translate, when this type of studies will lead to uh, policies for urban zoning and urban management, I'm not sure, but I'm for the society and I think urban area, this would be a very, very important application. Next. To talk of the geology, I just took this example. Morning, I met Arindam. Yeah, so here the emissivity and LST separation allows us to differentiate the lithology. This one is from Dharwad Craton, Karnataka. And I'm sure most of the studies have either been in Rajasthan, Singhbhum, Dharwad, couple of uh, very, very extensively investigated areas. So there will be, I think, better delineation. There will be more classes. It may also aid in some type of exploration, mineral exploration also. Next. This is a very, very important area, but you don't really have clear-cut answers. There are many studies, especially from IITs, which have looked at the thermal anomalies before major earthquake. So some of the earthquake you get very good signatures prior to, but you would still can't predict where and when. Some of the studies which have, I think, different type of topography or climate, or the epicenter is very deep, there are no response also. But in the semi-arid and arid area, and even in the example of the the Himalaya Muzaffarabad, there have been publications which have detected thermal anomalies prior to the actual earthquake event. Next. Coming to cryosphere, you can use the LST and have snow melt prediction. For India, it is very important. You also, there are some more work is getting done. So in this case, the differentiation between supraglacial and periglacial debris because of the temperature to allow you to delineate the boundary by combining optical and thermal has been demonstrated. I think Dr. Bogana is there. He wants to do much more glacier and other work. But what I believe, although there are other issues, with better snow grain characterization and thermal, we should be looking very, very closely at avalanches. So that is another area, I think, with the Trishna era and the type of swath and the repetitivity it has, there would be more avalanche-based studies, which for the geohazard as well as cryosphere, because in winter you lose regularly many lives because of the avalanches. It includes the tourists, includes the local citizens, and it also includes the security personnel. For all the three, it's very important. Next. I want to end by saying that Trishna represents a very significant enhancement of spaceborne thermal remote sensing, and it will definitely have emissivity and LST products, a spatial resolution to really delineate most of the features separately, and the 3-day sort of repeat coverage, and 8-day retracing the orbit will allow to track this with all thermal inertia applications of day night coverage. While the products will be there, I just looked at uh, wherever beyond the level 2 level 3 level 4 products are the one which the larger community uses, because it corrects for the gaps, it corrects for clouds and many other artifacts. So I'm sure the higher level of products would be developed for Trishna. So what exactly would be the challenge? So the challenge is uh, matching visible NIR sphere geophysical retrievals and the level 4 products to really do near real-time processes and fluxes of water, hydrology, irrigation, and some of the cases disaster. True that the remote sensing moves to a new era with thermal remote sensing. Up to now, what was demonstrated is actually brought into the practice for use of community. And I think the data model fusion and with the availability of more ground observations on fluxes, we may be able to run much more the machine learning and other type of algorithms also, which hasn't seen in this particular case, but uh, 2026 is not far off, right? And Megatropics took 10 years plus to deliver. Saral Altica also took some time, and I'm sure the NISR also we have been discussing. So if you really want a very, very big thing to be delivered, you need patience and you need to continuously work and fill all the gap, which I'm sure all of you are more than capable of doing and delivering. So I really want to once again thank Director SAC, the organizers, Dr. Bimal, and the Bimal, Mehul, and Samudraya who shared some of this information, and have the wish you well in your new challenge of developing this new era of thermal remote sensing. Thank you very much.
Thank you, sir, for your enlightening keynote address. Your profound insight into the evolving application of thermal remote sensing in sustainable development have truly set the stage for meaningful discussions throughout the session. Your expertise in vision inspire us to think beyond the conventional boundaries and to explore the innovative solution for the challenges we face. We are deeply grateful for your invaluable contribution to the field and for sharing your wisdom with us today. Thank you, sir. So please sit. Betty, please. It is now our honor to recognize and express our gratitude to Dr. V.K. Dadwal for his remarkable contribution in the field of remote sensing. I now request Dr. Bimal Bhattacharya to kindly join us on a stage to present the token of appreciation to Dr. V.K. Dadwal. Thank you, sir. As we draw to the close of this inaugural function, I now request Dr. Bimal Bhattacharya to deliver vote of thanks.
Good morning to all delegates and colleagues from other part of the world and Indian colleagues, Isro colleagues. So I will not take much time between you and tea break. So First, it is a formal vote of thanks. I would like to place on record that as convener of Science Organizing Committee, I would like to express my deep gratitude to Chairman Isro, Secretary DOS, Dr. S. Somnath, as well as CEO of CNES, Philip Baptiste, for giving go-ahead for this 3-day ISRO CNS Joint International Science Workshop on Thermal Earth Observation. And it was preceded by 2-day pre-workshop tutorial at Space Application Center ISRO in the backdrop of Trishna and similar other global follow-on missions. We are grateful to Director URSC M. Sankaran to provide basic guidance for organization of the science workshop and tutorial. We're extremely thankful to Director SAC, Nilesh M. Desai, to facilitate us to host such workshop and pre-workshop tutorial at SAC and for providing time-to-time guidance to organize this. We're grateful to all SMC members for providing their necessary support. The esteemed members of Scientific Advisory Committee from ISRO centers, IISc, CNES, European Space Agency, JPL NASA, USGS, USDA list provided timely inputs and feedbacks for preparing workshop objectives, flyers, structuring the agenda. We thank them all from core of the heart. We are indebted to Dr. V.K. Dadwal, Chair Professor NIAS, to agree to our invitation to deliver a very insightful keynote address in this event. We are delighted to have you here, sir, after a long time. We are extremely indebted to Chair LOC, Dr. I.M. Bohoguna, and Co-Chair Dr. Rashmi Sharma, and Member Secretary Dr. Rahul, and members of all local organizing committee for providing their necessary guidance for meticulous planning and execution of this science workshop. I would like to place on record that the hosting of this workshop would have not been possible without the hard work and dedicated efforts put in by conveners or co-conveners and all members of 10 subcommittees which have been constituted for registration, technical, then tutorial, website, then hall management, logistics, catering, finance, medical, etc. in a very well coordinated manner, and special thanks to admin, accounts and CISF personnel for their necessary help. We are very much thankful to Director URSC, Director IIRS, and Director NRSC, Director ISTRAC, and different other ISRO centers to extend their required support to facilitate the participation of scientists and engineers from their respective ISRO centers. We are indebted to Scientific Secretary, Director EDPO, and also ISRO International Cooperation Office and DOS officials, MEA, to take up timely actions for arranging necessary clearances for this international event. There is an overwhelming response from CNES and its affiliated institutes, other institutes abroad, as well as from ISRO and Indian institutes, which led to the registration of more than 400 entries and submission of 134 abstracts. Heartfelt thanks to those who could join in person and also remote presenters, as well as global audience following this proceeding through internet webcasting on ISRO YouTube channel. We are extremely indebted to CNES, ISRO, and Indian faculties from IIT, IISc for extending their expertise to Indian and Southeast Asian country students under CSSTP, young researchers and scientists through lectures and conducting lab sessions on various advanced topics related to thermal remote sensing. Special thanks to Dr. Shashmita, Yogesh, and colleagues and SRTD officials and staff for well coordinated effort for this pre-workshop tutorial. Last but not the least, our special thanks to Project Director Trishna AM Nagalakshmi Madam to provide the fullest support to make this event happen. Thanks to all of you for coming here and hope you will enjoy fruitful discussion, interaction, scientific exchange during these 3 days. Thanks. Thanks to all.
Yeah, thank you all for your attention. and wish you a very fruitful and engaging workshop ahead. Now, I request all to join for the refreshment, which will be served in the basement. And with that, we'll have one group photo in front of auditorium. So request all to join for a group photo, please. And after 20 minutes, we'll be here for our technical session. Thank you.
because we can see it here. So it's going here.
But actually, it should come on the screen also.
There.
You have Type C output.
USB-C.
Yes, USB Type C.
Yeah.
Bye-bye. You can change.
Done. Is USB-C.
Setting is
Ah.
hello and change. How connector here?
Sorry?
Type C to any connector.
Yeah.
Converter.
For
Type C to HDMI.
I have one also.
If you don't mind, please.
Yeah.
One.
This one is old. This one is old. They have it here also.
Okay, they will check there, otherwise it's here. So please change the setting.
Yeah.
Not extended.
To put what? Here. Screen. Display. I don't know how it works. Can we try again HDMI? Maybe.
HDMI is not global output there.
Visibly आ रहा हूँ.
क्या और क्या बचना लो पकड़ो
HDMI वाला नहीं. सब चलेगा. नहीं. वही
पेनड्राइव दूसरी कोई भी नहीं चाहिए रजिस्टर चाहिए
सर काम कीजिए आप वाइड पेनड्राइव में कोई हटा से आप. हाँ पर वो अभी ठीक है अभी जितना है उतना कर देते हैं अगर इसमें है तो.
Can you just please change the mirror setting? Display.
Now we can see here.
Yeah, but not here.
Not there. We can see here, but not there. Yeah, just you have that converter, white converter. Ah, yeah. XC2, yes. Go back. But that need that converter actually. Good converter. We need good converter actually. Ah, this one. Yes, this one. Yeah, can we try this one? Yeah. Actually, but
Hello, mic testing.
Hello. 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 Sir, start करेंगे? Welcome back. Good morning again. So after the inaugural session, we will start the technical session here. The session name is this is International Thermal EO Mission Initiatives and Synergy. So I would like to invite the co-chairs for chairing the session. Thierry Carlier from CNES France. Please come on the stage. And then AM Nagalakshmi Madam from URSA. Madam, please come on the stage. So they will take over the session proceedings, and Nitesh Thapa from SEDA will be the rapporteur for this session. Nitesh, you can also come here. No, Madam and Sir, you can please take over the charge. You can start the proceedings. You can call the speakers and everyone, and then as per the schedule, you can start the session.
Good morning to all once again, and welcome to this technical test session. And first session is International Thermal EVO Mission Initiatives and Synergy. And this will be presented by our Trishna team, science team, and the project team. I invite the science team, Mr. Bimal Bhattacharya, Ganesh PV, Dhiraj Adhalka, Manikumar Meenakshi Sarkar. I think speakers can come over and we can start the session. And Mr. Philip, yeah. Please, Corinne.
Corinne and Philip. You can see one. You can come. So good morning to all. So this presentation on Trishna basically has three broad segments. It will start with science perspectives, which myself and John Louis, science PI from CNA side, will actually talk on that. So I think we can go to the next slide, please. So if you see that signals of global warming, actually there is thermal anomaly of more than 0.5 degree centigrade annually, and it is increasing. And IPCC summary report for policymakers says that 80% of the global warming is due to the human-induced global warming and climate change. And as a result of that, there is an increasing extreme events which are reflecting in the ecosystem stress, then drought, urban heat island, flooding, then sea rise and the extreme events, and also shrinking of ice sheets and retreat of glaciers. Next one, please. Yeah. So
okay, thank you. So it's pretty clear that actually the added value and one of the main objective is water stress, which is the main driver of the Trishna mission. And you can see on this slide actually that today we have to feed about 7 billion people, and pretty soon in the future we turn to 9 million people. So we need to optimize actually the water consumption, use, quality, and distribution. And this is what's expected from Trishna. And so there is really one objective linked to the food security. And you can see is to have increased our efficiency of water use to improve crop productivity. Yeah. Okay, so if you look into that, so it's really Trishna oriented to water stress for agro ecosystem. You see that agriculture uses about more than 2/3 of the water, the rest is for industrial and domestic use. And it's even more is expected to grow with time. And the projections, you can see that even for India is more than 50% of India facing actually extreme high water stress. That means that actually we made huge effort try to optimize water consumption for irrigation, and we expect really from Trishna to bring new insight in this direction.
So we have carried out the long-term studies using NOAA and MODIS thermal remote sensing data of 8-kilometer resolution, and 2-3 PhD students actually have worked hard on these, and these has led to the annual water consumption in terms of evapotranspiration between 1981 to 2010, and the trend shows that in irrigated agriculture, basically there is an increasing trend of the evapotranspiration or water consumption from agricultural patches, and that leads to at least significantly increasing at 4 kilometer cubic 4 cubic kilometer per year. That is the trend of increasing the water consumption, and there is a large gap existing in terms of 160 kilometer cube between the irrigation water withdrawal versus water consumption in agriculture. And if you see the report of NABARD from India and ICRIER, that there are two terms called these physical water productivity and the economic water productivity. And physical water productivity, actually for India it is 4 times less than many agricultural rich countries, and also in economic water food productivity it is actually the water footprint, that is $3 per meter cube against some $8 per meter cube of water usage in Indonesia and also China, and as compared to US, in India has very less this economic water productivity. And finally that leads to basically the India is acting as the virtual net exporter of water flow to total available water, especially from 10 water guzzler crops like rice, sugarcane, potato, many others. So just for giving one example, that for rice crops generally we know that from 800 to 1000 millimeter 800 to 1000 liters of water is needed for producing 1 kg of paddy. But in real sense, actually 15 on an average 100 liter is used for producing 1 kg of paddy. So if we are eating something in the previous slide, you can see that basically we are indirectly consuming 2000 to 4000 liters of water through our food. So how to save water, that is the actually main concern for the Trishna and many other thermal missions. Next.
Oh, okay. So it's just an illustration of the access to water, fresh water reserves. Okay, so we need to optimize the consumption. That's pretty clear. We expect a lot for the map of surface temperature and high resolution and high frequency. This is why we have great expectation on Trishna and the follow-on with SBG and STM to cover all the globe in short time period, almost daily. So you know about the threat from evaporation, the competition with the optical. Optical, you can see the change of the colors on the leaves and the plants, but still, because of the evaporation, you know earlier, but the status of the water stress for the water, because can measure actually the plant transpiration from Trishna. So you'll be back later on different products that will be released from Trishna, but evaporation is a major product. And you look about the energy budget, you see that you can access also to heat, sensible heat flux and latent heat flux, and also net radiation will be or downwind radiation will be output product of Trishna. So on the left, on the right here, you can see a graph, a function of time during the seasonal use consumption of water for evapotranspiration, a function of different category of crops. And also you see that the response you can export to rainfall, because you are rain-fed water, but it's not sufficient. So you need to have also some irrigated water source. So that's what we expect from Trishna, just to find a good trade-off and compromise between water use for crops. Okay, I go to the next slide. So where we are today, actually, we don't start really from scratch. We use, most people use optical data. So from optical data, you have high spatial resolution, and you can combine also with the Landsat. For instance, we measure the thermal. The only thing that you can measure some directional vegetation indices like NDVI. What it tell you today, you can know about the maximum evapotranspiration for crops, and the water requirement you need. And but also you can use thermal and like Aster or Landsat. The only thing that has the appropriate spatial resolution, the footprint for crops. But the problem is time revisit. You like in the case of Landsat, it's twice a month, so it's not clearly appropriate to do that. So actually, what we need to know for energy balance, we need to know actual evapotranspiration, actual water consumption, not only potentially or the maximum. And because of that, we need to have not 16 days revisit information from satellite, but we have, because it's not sufficient, we have something which is actually every day almost, or every several times a week at least. So this is what we expect from Trishna, because what we have regularly today is 1 kilometer, is not appropriate to time resolutions pixel of most of crops. And you see in the equation of terrestrial equation of water budget, you can have, you can know about water storage from altimetry for grass, for instance, and you can know about, you have some mission also that measure the precipitation, or you have salt mission for about salt moisture. What is really missing today, and that's we made Trishna, is actually the through evaporation. So, okay, clearly that we close the budget for terrestrial water, and so pretty soon, so we have a lot of great expectation. Next one. So just a glance, as a glance for Trishna mission. So we have, when we define the mission, there was what called a design driver, primary design driver. So it's from the very beginning, it was very clear that's oriented to a water budget. So that's the reason why ecosystem plus the water user, they drive the specification and definition of the mission. And also inland water, coastline, shoreline was also a targeted objective. There are second design drivers. I say secondary driver, but still some come very importantly on the table. I think normally, in particular to urban heat island, I see this quite important. Solid Earth, we have a slide this morning that saw that can be some thermal anomaly, can be useful for geology and volcanology. Cryosphere, if you're interested by polar caps, snow melt, and by glacier, we know that's quite important. So it's part of a hydrology cycle. So certainly we can bring, Trishna will bring new insight in this direction. Atmosphere also, we have, you see some dedicated spectral bands that measure water vapor column in the atmosphere at high resolution of Trishna. And I was also we need to actually to say before we can reach the target objective of having 1 Kelvin precision for the temperature of the surface to correct properly for atmospheric effects. So this is a long cooperation for 5 years, maybe 2 years extension depending on the fuel, and there will be global coverage. Overtime price is 12.30. It's really harmonized with other mission SBG LCM. So I want to emphasize this fact that really have a good level of communication and discussion, and in terms of global coverage and so on, the geographic coverage and so on, and so specification. Even with sometimes about deliverable product, we try to be sometimes maybe more or less transparent for the user when you have all the 3 missions in flight, hopefully. And we have 3-day revisit at the quarter. And improve the revisit. We improve as you move towards the higher latitude, like mid latitude, maybe one observation every 2 days. And so the final pixel resolution footprint will be 60 meters. So we have 7 bands in the vernier and sphere, 4 in the thermal infrared, and this, because the wide field of view, we see this afternoon we have some directional effect because same target will be seen over short time period of different angles. And okay, so you can see on the graph the acquisition mask. I mean, I'm going to choose the coverage for land surface and for the coastline, and you can see the frequency of revisit on the right bottom up. So it's increased with the latitude. Yeah, you can.
So Trishna science and applications, basically it relates to the water management in agriculture, then ecosystem health, drought, fire, then coastal and inland waters as narrated by John Louis. These are the primary objectives, but there are other secondary objectives also related to urban heat island. There is strong response. Actually, we have seen the abstracts. After ecosystem, this urban heat island is next, and then cryosphere and solid earth. Solid earth basically relies on the temperature emissivity. And then if you see that evapotranspiration temporal progression, it is actually highly varying. So and it depends on both surface and atmospheric characters, and drought episodes, basically flash drought, that is also coming in, that actually depends on the instantaneous water deficit, and if it persists for long time, little more than week or 15 days, and below certain threshold, if there is the root zone soil moisture, then actually there is a need for water supply to be given to the crop fields. If it is not, then plants will suffer from this dry matter accumulation. So it is basically the soil plant atmosphere continuum which actually drives this mechanism using the Dixon-Joly theory, and which ultimately reflects into the surface temperature and different biophysical properties. So what properties actually we would like to observe or derive from Trishna data? Basically, it is the reflection from the subsurface, so into the plant and soil, and then we are sensing that. So that's why this evapotranspiration temporal progression is very dynamic and very unpredictable also. That's why this repeativity, high repeativity is very required. So Trishna will be addressing the primarily the land surface temperature and the through different vegetation properties to derive the vegetation status, and finally will solve the land surface energy balance, and where the latent heat flux actually is converted into the evapotranspiration. So this mission will provide very high repeat, field scale, global thermal and visual observations, and with a low latency system. Next one. Yes.
Okay, this just to show actually the gain we'll have to oversee, in particular because the strategy is to keep the same full resolution of Trishna away 200 kilometers away from from the cost, it means that for fishery has some application. And you can see this map actually what we have with VS SST, sensitive surface temperature, which is the follow-on of MODIS, and compared to EcoStrail, where it's flying or ISS now, and you see that actually, which is resolution footprint, which is close to what we get with Krishna. We see the gain actually in for the description of the coastline and the shoreline. So with many application. Also, another application will be also to hydrotic resource, to the source of resurgence if you are close to some topography relief, because you have pure water that's mixing ratio water with salt water. So that's important value. And so just to show that we know how to validate this. This is from my dear colleague from IFEMER. They have some station as a same ground, and there are also other means bureau to actually to check the quality of SST we'll get from Trishna along the coast. Okay. See, yes, this, I think, even if it was not at the very beginning a design driver, the urban component come very strongly on the table for different reasons. From one of my first slides, I talk about the food security. I think the really added value from Trishna and the other mission for civil security. You know, most people, they live in city right now and gonna increase with time. So, and because we have some heat sometimes and heat wave that can be important. So we need to redefine the strategy. Everybody know for people living in the city to increase the comfort. So the different means to do that. You can put more vegetation. You can actually change the material. And I know Ahmedabad is famous for that. There are some strong program for cool roof actually to change this. So that's quite important. And if you you look about on this graph from US for the last decades, you see that the well frequency is increased importantly, and UNIAM actually is also changed along the season. So it's quite a significant signal. If you have a zoom of Los Angeles in California, last heat wave was, was actually very close from us. That's about 2 months ago, and you see actually some area of Los Angeles actually was facing some unusual, and I mean the rapidity of that is important. So what we expect for Trishna, because the passage resolution 60 meter, with possible even downscaling with optical to reach a few meter resolution of temperature of the city. We see there is some presentation for that with good grid up and very good method. We can really communicate with decision maker and stakeholder to want people to, to take some safety measure to avoid some morbidity for disabled people or some people. So actually, so what we call sushi, so fast use urban each island in a city, you can see actually different city in the US and over the world as it change with time. So this is the message to carry on is a very strong signal, in this direction, and of course, Trishna will be of significant added value in this direction.
Next, over to our project.
Thank you, Bimal sir, for your presentation, which is insightful and which has thrown light on and gave path to the next presentation. So we will be covering Trishna system overview. So it is a joint presentation between project teams. So from our side, I am Ganesh and Dheeraj, he will be presenting, and Kenneth said Corinne will be presenting. Next slide, please. So this slide depicts entire Trishna system. So here we have ground segment spacecraft. In spacecraft, mainframe is supplied by URSC, and payloads were supplied by Viswir by SAC, and TIR payload by Canes. So integration and shifting to launch will happen from URSC and launch from Satish Dhawan Center SHAR. So PSLV launch is used for launching this Trishna mission. And with respect to the ground segment, we have two payload ground segments. One is at Canes, the other one is at Isro. So as a part of ground segment, we have command control system located at ISTREC. So which will be doing telemetry and telecommand operations for the spacecraft. And coming to the payload ground segment wise. So we have defined two identical ground segments. So one is located at Isro India, other one is at Canes Toulouse. So Isro is connected with Shadnagar station for X-band payload data download. So and Canes is connected with 5 ground stations. One the locations are given here: Inuvik, Kiruna, Kuru, HBK, and Asugal. So both the PLDPs have identical operations. So each PLGS consists of PLDP, that is payload data processing, then technical expertise for Viswir payload, and Bunidi for data dissemination at ISRO. Similar way, we have technical expertise for TIR at Canes PLGS, and payload PLOC, that is for command operations of TIR payload, that is from Canes Toulouse, and payload distribution is through GODS from Canes side. So and we have one dedicated network established between ISRO and Canes to exchange the raw data between both the agencies. This mainly for payload data we will be exchanging using this link, and the request for TIR telemetry, telecommand, those such things will happen in that dedicated network, and we will be sharing exogenous data required for payload data processing. So the PLDPs at both the ends will do means processing of data from level 0, level 1, level 2 up to level 3, and identical products will be generated at each PLDPs. Next slide. So coming to the spacecraft wise, so orbit is 761 kilometer sun synchronous orbit with local time 12:30 with plus minus 5 minutes descending node. So our orbital cycle 8 days geometric revisit. So as I explained earlier, we are launching using PSLV, launch from Satish Dhawan Center, India, and the spacecraft is our I-1K proven bus. So it has ISRO flight heritage for all missions, previous missions. So mass of this spacecraft is around 1200 kg total. So 700 kg is for mainframe and 330 kg for both the payloads. So and which will generate around 2 kilowatt power. The pointing accuracy is around 0.05 degrees and pointing stability 5 into 10 power minus 4 degrees. We have host of sensors, star sensors, gyros, and which will give accurate pointing accuracies. So TMTC is operated in S-band with 64 kilobits per second telemetry and 4 kilobits per second telemetry. So our X-band downlink data rate is 960 Mbps in dual polarization mode, and mass memory we have configured with 1.4 terabyte. So mission life we are envisaging is 5 years plus 2 more years. So mission life is targeted for 5 years. So it can be extended for 2 more years. So this shows the stored configuration, then bottom deck view and deployed configuration of Trishna mission. So as you are seeing below is a mainframe platform. It is like 2 module configuration. So and all the mainframe systems are accommodated in the below that mainframe systems, and the 2 payloads are accommodated on the payload deck. So this is entire our system spacecraft view. Next slide, please.
Thank you, Ganesh. So I'll be talking about the Viswar payload. So the Viswar payload, as you all know, is being developed by Space Application Center ISRO, and to cater to the swath requirements of plus minus 34 degree, what we are doing here is we are separating the field of view of plus minus 34 degree into 3 electro-optical modules, each which will cater to 1/3 of the swath. You can see in the center diagram showing the footprint of the sensor on the ground. So what we have done is we have the veneer bands accommodated together in a single detector. Okay, all the 5 bands will be separated in a long track, so there will be a total of 5 bands, while the switch channels, given the fact that certain switch detectors were available, what we are doing is we are having separate detectors for SWIR 1 and SWIR 2, which are being accommodated separately. So in all, there are going to be 9 electro-optical modules, which will be catering the swath requirements of plus minus 34 degrees and a total of 7 bands. The configuration is a simple push broom configuration with a line scanning mechanism as you can see. So the spacecraft traverses, with the spacecraft motion, you are going to continuously get the data. So there are, like I mentioned, there are separate optics for Vined and switch channels, and for the Vined channels, we have the 5 multi-band array detector, which will be accommodating the spectral bands and the individual performance parameters. So here you can see on the left hand side the block schematic of the payload. Next slide. So I'm just giving a brief overview, a very brief overview of the subsystems. So the optics configuration is shown here. The optics has been designed at SAC and is being developed in one of our other ISRO establishments called the OS Laboratory of Electro-Optical Sensors. The detector, there are two different types of detector here. The Vined detector, which I mentioned, which is a pentaline detector, is a 6K custom designed detector which is being developed at Semiconductor Laboratory, which is a facility in India, which is right now under MeitY, Ministry of IT and Electronics. Okay. And while the SWIT detector, we are having the detector, these are flight grade detectors, which we are already tested, characterized. Coming to the electronics, we have modular electronics with a common controller, which will do all the necessary functionalities to be able to cater to the requirements of Trishna mission, which majorly includes the generation of different kind of clocks and biases, the video processing operations, binning operations to achieve the requisite SNR, which is one very critical parameter for Trishna mission, generation of the clock signals, telecommanding, telemetry, temperature control, digital data processing, compression, and so on and so forth. Corinne, we'll move on to the test slides.
So the visual instrument is a push broom instrument, but the chair instrument is a whisk broom concept. That means that the large swath, which is around 1,000 kilometer, is acquired thanks to the scanning mirror. We have this scanning rotation for a basic cycle of 5 seconds, which is repeated along the track. And for each cycle, we have internal calibration thanks to two internal calibration devices, a black body and a deep space aperture. So this instrument is under CNES responsibility and has been contracted to Airbus in Toulouse. And it will provide four TR bands from 8 to 12 micron. So where we are in this is development of the instrument, we have built a full EM cryostat equipped with a detector, filter inside the cryostat, and with the two EM cryocoolers, and we have been able to perform a full environmental testing campaign with this EM, as well as some preliminary optical characterization. Also regarding EM activities, we had a successful coupling test with engineering model of the TIR instrument and a platform simulator, and to ensure the good connection and good comprehension of the interfaces between the platform and the instrument. So it was really successful with a good cooperation between ISRO, CNES, and Airbus team. We are ongoing with flight model activities. So we have performed the PFM telescope integration. So we have integrated the three mirrors in the optical bench, and we have performed the alignment of the three mirrors. And we are doing the PFM cryostat preparation. So you have some picture of the alignment of the mirror and also of integration of the focal plane.
This slide shows the payload operation plan. Actually, we have two payloads. TIR is always on, and vSphere will be on during only sunlit. So that sunlit we have defined as sun elevation is above 5 degree. So that maximum 55 minutes will be getting per orbit. So here the slide shows that means the map was put as full resolution and reduced resolution. Payloads are giving in full resolution mode, but binning and compression is happening at our BDHN to reduce the data rate in the ocean areas. Basically, ocean resolution is 1 kilometer. So that way we have defined two different products.
We will have to deliver a global production of products up to level 3, so which means a very huge amount of data. We talk about 15 petabytes of data for the 7 years of operation. So as mentioned previously, we have two growing segments that will share equally the production of the world, I would say. And all the data will be available on the two gateway, Bunidi and on India side and Geodes on French side. Along with some semantic portals. So for users, they can access all the data wherever it has been produced from either one of those two portals in a transparent way.
Actually, Sarkar sir has in his overview, he has briefly explained these milestones. So we have completed SAP VR1 in 2023, and Viswir BDR was there in December. Then 2024, we have good amount of work was progress, like we have spacecraft on ground segment PDR, then KNS PLGS CDR, then SAP VR2 recently held, followed by JWG review, and they have recommended all the, means approved all the recommendation by SAP VR2 committee. Then we have like tier CDR is planned. Then we have verification and validation key point for our ATBDs and CalVal plans. Then spacecraft and ground segment CDR is planned. Then followed by Viswir CDR. Then 2026, we are planning tier and Viswir delivery. Then mission operation review is in before launch, 3 months before the launch. Then satellite pre-shipment reviews and system qualification reviews. So launch we are targeting December 2026. So CalVal plan.
Yeah, just to the launch is not the end of the story. After that, we will have a period of 16. Yeah, time we are okay. Yeah, I think it's just to say that we will deliver the products for all the scientists who are here, and we will present what we will do with that after the CalVal phase. It's okay.
It's okay. You can put it in. It's okay.
Okay, now we have an overview of the Trishna products, different level of Trishna products that will be distributed to the users. So these are the spectral bands again, and I only have 5 minutes, so I'm going to be in quite a rush. So these are the different spectral bands that we have, and all what they are meant for, from surface reflectance computation to albedo and vegetation variables, and then thermal infrared bands are here to compute, of course, emissivity and land surface and sea surface temperature. Level 3 products will be day-to-day evapotranspiration at 60 meter. Level 1 variables, 60 meter sampling, as I said, are in the Viswir domain, the reflectances, top of atmosphere reflectances, in the tier domain, the brightness temperatures, together with the rough cloud mask and every angle and quality flags that goes with the product and sensor information. Level 2A products are surface reflectances and temperatures, emissivities, also an accurate cloud mask, which is built from multi-temporal analysis of the data, scene classification, and key information about the atmospheric content, total water vapor content, aerosol optical thickness, and also associated uncertainties. This is a quick overview of how we get to science products and to applications. So we have level 2A products from which we build level 2B land products that consist in vegetation variables, radiation fluxes, evaporation fluxes, and we're also working on primary productivity products. And then from this, we have this level 3 product, which is, as I already said, continuous time series of daily evapotranspiration. As far as coastal and inland waters are concerned, we're working on the possibility of having these water products for water quality and corals. Other themes will have access to level 2A products, urban microclimate, cryosphere, and solid earth. Okay, I'm not going to go through this. If you are lucky, you were at the tutorials, so you know everything about those two equations. The basics for Trishna is that we are going to compute a surface energy balance and compute the evapotranspirations as the residue of this, of the net radiation computation. And as you can see, all of the terms of these equations are driven by Trishna variables, land surface temperature, of course, but also emissivity and albedo. Just one quick word about something that we shouldn't forget is that these evapotranspiration products are one of the key aspects of this product is the timeliness and the data latency. This is a very simple scheme to show that when a healthy crop faces water deficit, it results in a stomatal closure to limit the water losses, and then the plant heats up. And this results ultimately in a reduced photosynthesis and then reduced dry matter production. And you can see here on this scheme that it's detectable from veneer data after a few days, maybe 1 week, maybe more, depends on the scene, depends on many things. And from the moment when the plant heats up, it's detectable from thermal infrared. So this is where this kind of data is really critical. I mean, we have this time from satellite acquisition to level 2 and level 3 data delivery to get this key information to the users to take the decision for water supply, and then we get the stomata reopening and the crop is healthy again. And this is like a reversible mechanism on the bottom of this slide. On the top of this slide, you have something that is not reversible. You have lost something. Your crop is not healthy anymore. But if you can put water in the system soon enough, then you can get your healthy crop again. The evapotranspiration projects that we are going to deliver, well, it's very challenging to do this at 100-meter resolution. And maybe because performance is partly driven by meteorological inputs, and they are only available at lower spatial resolution. This is why, first, of course, we have a specific effort to get this data as reliable as possible. But also, this is the reason why we selected this contextual algorithm, which is called EVASPA. It will minimize the impact of meteorological inputs. So that's very important in the context of Trishna. To run such an algorithm, you need some specific conditions in the area that you are considering. This is why we have to raise an alert when these conditions are not fulfilled, and we have to propose an alternative. And we selected the stick model, again with the objective of minimizing the impact of exogenous meteorological information. This is why with the Trishna production, you will have two different products for evapotranspiration. Okay, very quickly, you have a presentation on session 1.4, actually made by Anand with Albert Olioso about how we plan to compute the vegetation variables with Trishna. You will have also in session 1.4, Jean-Louis Rougeant and Sushil Kumar Singh presenting how we compute the albedo. And then also the downwelling shortwave and longwave radiations that are critical to compute this. Albert Olioso in session 2.1 will also have a presentation about the contextual evapotranspiration. And of course, Kanishka will present the stick evapotranspiration algorithm. Just to conclude about the challenges that we are facing to compute these very demanding variables, of course, directionality, soil heat flux modeling, and this will be presented in session 2.8 by Dr. Gilles Famous Boulet. And the gap filling for continuous evapotranspiration is also something critical. Okay, I'll stop here. Thank you.
I have a question. The flow of data across the cognizant ISRO is well planned. But what is the plan under any critical condition of one instrument failure for the data products? In case we have a critical failure of one instrument, either VSWIR or TIR, the other partner is engaged to continue collecting data from ground stations and transmit the data to the other ground segment for processing it. So in case VSWIR fail, Isro will still provide the data to CNES, and they can process tier data alone. In case it's the tier will fail, CNES will continue to support with the ground stations downloading the data for the VSWIR and then transmit to Isro. Then regarding the product, I can answer that we have some products for tier alone, since during night we only have the tier instrument. I'm not able to answer what about product, single product with only VSWIR. I don't know if so.
Yeah, as Corinne pointed out, veneer failure just results in being like in the night conditions. So this kind of work. And then if we have a tier failure, we still have lots of products that we can produce, vegetation variables, albedo, this kind of variables that are very important also. So we will still continue producing these variables.
Clear-cut understanding with respect to what products we will be generating when there is a single instrument failing. Thank you. I think we can move on to the next presentation. Thank you.
So we are more than happy to welcome our international partner, and we will start with Ferrand Ferrand Gascon from European Space Agency, and with his talk on the LSTM and potential strategy with our program. So welcome.
Thank you, Thierry. Preparing the presentation.
While waiting for the slides, what I would propose is to invite the our partner representative, and Simon, if you could join us on the stage, would be a great honor today. Then Ralph also. So let me introduce Simon Hook from GPL and Ralph Basilio from GPL NASA. They will talk about eco-stress and SBG. Please have a seat. Then we have a friend from Netherlands, from the University of Delft, and Mr. Bastiansen, if you could please join us. And the last person from SAC is Anut Das. If you could please join us. Is online or? Oh, it's okay. Sorry. Okay, so please join us.
Thank you very much. So thank you very much. Very glad to be here. Sorry for the delay. There was a last minute update of the presentation. So with the security rules, it took a bit longer to update it, but thank you very much. It has been finally updated. So very glad to be here to present LSTM in the framework of this international cooperation between LSTM, SBG, and Trishna missions, an international cooperation which is often referred as LST. So not land surface temperature, but LSTM, SBG, and Trishna. So the list of co-authors here shows the very large number of people that has been involved in preparing, developing LSTM. So many of those people are here in the audience. So I'm presenting the mission on behalf of all of us, please. So just a quick overview of all ESA missions in development. You have scientific missions on the left, Copernicus missions in the center, and meteorology missions on the right. The LST mission is on the Copernicus, is part of the Copernicus family, the middle path, and it's foreseen to be launched first unit in 2029 and second unit in 2031. So just after Trishna and SVG. Next one, please. So as part of the Copernicus family, there is a set of missions called Sentinels, which are the core element of the Copernicus space component. And there are 6 Sentinels already flying or in preparation up to now, from Sentinel-1 to Sentinel-6. And LSTM is part of a new family of Sentinel satellites, which is under preparation, the so-called Sentinel expansion missions. So I will not detail what's the scientific scope of LSTM. I think it's very similar to what Trishna is aiming at in terms of science and operations. And just to briefly introduce the other expansion missions, there is CO2M for anthropogenic carbon dioxide monitoring, CHIME is a hyperspectral imaging mission, Roselle, L-band radar, CIMIR for a microwave radiometer, similar to SMOS, and Crystal, which is an altimetric mission. Next one, please. So in terms of what LSTM aims at tackling, in terms of challenge, I would like to refer here to the IPCC report from 2022, which identifies a set of threats which Europe is facing. In that case, the report was focusing on Europe. And there are 3 main risks which the report was highlighting as well, and that risk which can be tackled using LSTM. So first one is human heat stress, mortality and morbidity. Second one is losses in crop production, and third one is water scarcity in Europe, and in particular in Southern Europe. Next one, please. So in terms of mission objective, as mentioned, very similar to Trishna in terms of science and operations. It's a thermal infrared observation missions over land and coastal regions in support of mainly agricultural management services and water management. But there is also a very large range of additional applications, and that often happens with Sentinels. They are designed for a specific application, but then we discovered during the course of the mission that there are many more applications that can be performed. Next one. In terms of mission key requirements, here on the left you have the system requirements, which we have 2 satellites with a 2-day revisit, one in the afternoon as local time for the overpass over Europe. SSD, a special sampling distance of 50 meters at the edge of the swath and 37 meters at nadir. There will be a sampling of the mission at 50 meters for the whole swath. There is a debate whether we should sample at 40 meters, 50 meters, but for the time being, 50 meters is the baseline. Then there are a set of spectral bands, previous one please, 11 bands in the tier of near and sphere. The swath is 687 kilometers, is a Wisdom scanner, also similar to Trisna. And then you have here also more details on the different system specification. Then on the right, upper right side, you have what we had as user requirement for the evapotranspiration product, which is a product which will not be generated by ESA itself. It's a downstream product that will be generated by the Copernicus services and other entities. And then finally, also the requirement we had in terms of observations, we want in terms of user needs, 1 to 3 days revisit, 50-meter resolution, and 1 to 1.5 K as LST accuracy. Next one, please. In terms of mission constellation, so there was an animation here, but being a PDF is not anymore visible. It's 2 satellites which are on the same orbital plane, separated by 180 degrees, and scanning the whole Earth as it's rotating. Next one. In terms of acquisition mask or observation scenario, it will cover the same areas which are covered today by Sentinel-2 mission, except Antarctica, which is not yet part of the baseline. Also, this is an aspect which is being considered whether we can extend to cover Antarctica as well. And to mention also that all small islands will also be covered by the mission. Next one, please. In terms of instrument concepts, so as mentioned, is also is similar to Trisna instrument concept, Wisdom scanner, browsing as the full swath, and then also having a deep space for cold calibration and a deep space capture for cold calibration and a black body for hot calibration. You can here see on the bottom right also what will be the instantaneous field of view for the mission. So you can see along track the different spectral bands, so including the visible, which is all the 11 spectral bands are Wisdom, so it's not like Trisna where there is a Pushbroom and a Wisdom. All the bands will be acquired by the Wisdom instrument, and then you have along track the 39.4 kilometers of each pass acquired. Next one, please. In this slide are presented the details on the 11 spectral bands. So there is a single aperture for the instrument and 3 optical paths for the near, the sphere, and the thermal infrared parts of the spectrum. MTF will be between 0.2 and 0.3, NEDT less than 0.15 Kelvin, and the absolute radiometric accuracy of 0.5 Kelvin. Next one. In terms of products, ESA will only distribute 2 low-level products. The level 1C, which is an auto-rectified top of atmosphere radiometrically and geometrically calibrated product. And then there will be also a level 2A product, which will include land surface temperature, land surface emissivity, for the thermal infrared spectral bands, both of atmosphere surface reflectance, total column of water vapor, which is an intermediate product for LST retrieval, and then finally a cloud mask, which is also a key element for having accurate retrievals. So the downstream products like evapotranspiration will be generated by, as mentioned before, by the Copernicus services, which are also part of the overall Copernicus program. And in terms of data latency, there is a goal of 3 hours and a threshold of 6 hours for the level 1C product. and for the level 2A goal of 6 hours and a threshold of 12 hours from sensing, from acquisition to the availability of the data on the Copernicus, the so-called Copernicus data space system which distributes the data. Next one. So this is what I was mentioned, the Copernicus data space ecosystem, which is the platform, the digital platform for the distribution of all Sentinel data to the user community. As it's a free and open digital platform, any of you can register there and get access to all Sentinel's data already flying. And in the future, there will be LSTM made available also there. Next one. So in terms of international cooperation, in this LST cooperation, the main goal that we have is to have the 3 missions harmonized as one in order to reach long-term data series. So the missions will be shifted in terms of timeline, so that will allow to have a longer time series combining data from the 3 missions, and also to have an improved revisit which can go up to daily. Here on the right also there was an animation showing how the three missions combine and providing an example of what's the revisit of the 3 missions combined. In terms of cooperation domains, there are 5 domains: product harmonization and also ATVD harmonization, where we exchange knowledge on how we approach for the different retrievals, and we benefit each other from these exchanges. Orbit coordination, as mentioned before, in-flight intercomparison is also foreseen during operations. Common Calval approach, also we're working on that. And finally, we have airborne campaigns organized together. Next one. And this one is a focus on airborne campaigns. The objective is to support the 3 missions with directionality experiments, urban and nighttime overflights. They are linked to other activities, international activities. There are also eco-stress coordinated acquisitions, thanks to NASA GBL for that. And then also the data of these campaigns is made available to the public as with an open data policy. Next one, please. So this is the last slide, like just to provide you a quick overview on where we stand in terms of mission. So the LSTM phase V2 kicked off end of 2020. We had a preliminary design review in 2022, which successfully concluded. There is a critical design review planned for last quarter this year, about to start the system design review. The instrument one has already started. And finally, there is a prototype flight model QAR, which is foreseen end of 2028 for having a launch, as mentioned before, beginning of 2029. And next one. So this is just the last slide to say thank you to all of you. It's an image from Sentinel-2 acquired yesterday over the city of Gandhinagar, the capital of Gujarat. And I found it very interesting when I heard about this city, which is, I heard was the greenest city in Asia, as it has more than 50% of the city surface covered by trees. So that I found it very interesting, that approach, that this new policy approach of combining nature and urban areas in the best possible way in order to adapt as much as possible to global warming. So with that, thank you very much.
What I do think is that we will wait for question after GPL presentation, just to highlight, yes, because I think we have some question relative to how the synergy will work in the future. So I would suggest perhaps to wait for GPL presentation. Now giving the floor to Simon. Okay.
Well, good morning, everyone. I'd like to start by thanking our hosts for inviting us here, both our Indian colleagues as well as our French colleagues. It's a real pleasure to be here. This is my first time in India. Today, I'm going to talk to you a little bit about a couple of missions that are actually working now, as opposed to missions that are coming along in the future. The first one is EcoStress, or the Ecosystem Spaceborne Thermal Radiometer Experiment on Space Station, that was launched up there in 2018. And then the other is HITES, which is an airborne instrument which allows us to get some very high spatial and spectral data for doing some precursor work for these upcoming missions. My name is Simon Hook, and I'm from the Jet Propulsion Laboratory in NASA, California. So this next slide sort of shows the science behind EcoStress. So we put together the proposal for EcoStress back in 2014, and we specifically wanted to look at evapotranspiration. And one of the things that appealed to us about going to the International Space Station was that the International Space Station goes over at different times of day. So this provided the potential to look at diurnal variation within in evapotranspiration over the day. And it also gave us the opportunity to look at drought and evaporative stress, as was indicated in the middle panel there. And so if you look at the panel on the right, you can see that change in evapotranspiration during the day. You can see the drawdown in the early afternoon. And we wanted to see if we could measure that with EcoStress. Next slide. So this is a quick description of the mission. It was built very quickly. We were selected in 2014 and launched in 2018. It's a 5-band thermal radiometer with a 400-kilometer swath width and a pixel size of about 70 meters by 40 meters. As I said, it was launched in 2018. It's on the ISS. And the repeat is on the order of about 3 to 5 days. It was originally intended to be a 1-year mission. And then once it got up there, NASA saw that it was working well and it was extended for a few more years. And then recently we've been told it's being extended till the end of life of the ISS, which is in 2030. So this instrument is producing data now for putting together precursor data sets for these upcoming missions, and may well overlap with all of these upcoming missions as well. Now, originally, as I said, it was targeted at addressing particular issues associated with plants, looking at critical thresholds of water use and water availability, seeing the timing and changes in the diurnal cycle, and then seeing if we could use this to determine how much water we needed to put on crops. But once the instrument was up there, it is the highest spatial resolution thermal infrared measurement in space, or temperature measurement, and there were many other uses that became apparent. And so what I'm going to do is show you some examples of how the data are being used today. So next. This just shows you the general process. You're probably familiar with this from the other presentations, but basically we put the payload together and then launched it on a Falcon 9 and started to acquire the data. And the plan was to take the instrument off after 1 year, release it into space, and that would have been the end of it. But fortunately, we're still around today and doing some great science, so very exciting. Next. So this was the original plan. We were just going to look at a small number of regions around the world. But once we got onto the International Space Station, we were able to get far more downlink than we expected, and we were able to cover the entire range from the ISS orbit. So if you look in the next slide, you can see this is the area that we cover, and we have acquired numerous images over this entire area, and we're continuing to acquire those images today. This is an example of the first high spatial resolution emissivity map from EcoStress. We tried to produce something like this with ASTER that you heard about in some of the earlier presentations. With ASTER, it took us 15 years to acquire something that was close to this, which we were able to acquire in a few years with EcoStress, because of that much higher revisit, that 3 to 5 day revisit that we have with EcoStress. Next. Now, one of the things about EcoStress is we can produce ET, and it wasn't long before, after we'd launched EcoStress, that companies were coming along, and we'll hear a little bit more about one of those from Wimbastian today. And these companies were taking the EcoStress data, they were using it to derive ET, and then people would sign up for the service and use it to determine how much water to put on their fields. And this is actually an app that you can download and you can put on your phone. And it's a good example of how we see SPG, LSTM and Trishna being used in the future. Next. Now, earlier you heard the example of how much water rice is using and the potential problems associated with producing a lot of rice in terms of water use. And this was a study that just came out this year. And in this study, they basically looked at how much water crops were using in the Southwest. And they determined from that if you were to change the crop from what we're currently using, soybean, things like that, and plant chia instead, which can be used as a substitute for soybean, you would be able to make a dramatic savings in terms of the amount of water that you would need to use in order to irrigate the chia, as opposed to crops like soybean. And so this is just an example of a paper that came out very recently. Next slide. Also, back in 2023, we were on the front cover of Nature with some eco-stress measurements. And these eco-stress measurements had been used to derive T-crit or T-critical, which was the temperature at which plants stopped functioning. And this was measured in the tropical regions with where they were measuring temperatures of above 45 Celsius. And this was a great example of how you can use these data in a tropical region, because the higher spatial resolution meant that we could get sufficient data between the clouds, which you couldn't do with coarser resolution sensors like MODIS and things like that. Next slide, please. And then this is also a very recent study, which I'll spend a little bit of time on. So in this particular example, what was done was to take the temperature that was derived from EcoStress and then use it to paint the colors of the roads. So different colors in terms of the road network relates to different temperatures. And you can see within the city, there are clearly hotter parts of the city and cooler parts of the city. And these are related to how much vegetation is present, and as you can imagine. Now, one of the things that's very interesting about this is Phoenix, a very hot place. And what you can see is any of the areas where the streets are red, if you were to fall over on the street, within 3 seconds, you would have a 2nd degree burn. And that's how hot the streets are getting. But with EcoStress, we can actually measure those temperatures and do something about it. Now, what we can do, for example, is we can start to paint the roads, we can plant more trees, we can plant bus shelters, and these data are being used to inform city councils and things like that on how best to mitigate those effects. Next. Now, you can also use the data for looking at coastal regions. This is an example of that. And in fact, this is looking at shellfish production. So again, the high spatial resolution is able to determine the best places to actually plant or to farm shellfish. And you can see that in this particular area, there were certain parts that were heating up more than other parts, and so they actually moved the shellfish locations. Next. So in terms of EcoStress, the instrument is still working really well. It was originally a small experiment, and it's grown, and now we're acquiring about 230 scenes a day with a plan to continue on to the 2030 timeframe. It's still the highest spatial resolution multispectral thermal infrared radiometer NASA's ever built, and still the highest spatial resolution one in space. and it acquires data every 3 to 5 days. And obviously, if there are any students in the audience and you would like to work on eco-stress data, just come and ask me questions afterwards, and we can also arrange for you to come and visit JPL and spend some time working with us if that helps. Next. So now I want to say just a little bit about the airborne instrument. I'm not sure how I'm doing on time, but hopefully okay. 2 to 3 minutes, good. So HITES stands for the Hyperspectral Thermal Emission Spectrometer. Next slide. And this is an airborne instrument with very high spectral resolution and very high spatial resolution. So today you were hearing about instruments with sort of 3 to 5 bands in the thermal infrared. This instrument has 256 bands in the thermal infrared, and you heard about instruments with spatial resolutions on the order of 30 to 60 meters. This instrument has 1 meter spatial resolution. So very useful for doing these very in-depth kinds of studies, but only over small areas. Next. This is just the instrument. It flies on various light aircraft. We have talked about bringing the instrument to India, and that's something we would still very much like to do if the opportunity arises. Next. And this is some work that we have been doing in collaboration with LSTM and Trishna, looking at angular effects, because all of these instruments are wide swath instruments, so they look out very much to the side, and we want to understand if we make those measurements at those high angles, will it impact our algorithms? How will it impact them? How will it affect those retrievals? But whilst we were there, this was from a European campaign. We also looked at other areas, for example, looking at some volcanoes, and there's some data over Volcano there as well. Next. So this is just an example of the quick looks. All of these data are also freely available, or all available for download from JPL, just like the eco-stress data are available for download. And you can see these airborne strips going through these 2 cities. So very useful for looking at urban heating, where you can get down to the building level, or useful for looking at these volcanic areas, is illustrated for Volcano. Next. Now, we also got some data over some cold areas, and this is over a glacier in the Alps. Very, very little thermal data that I've seen from glaciers. But as we heard earlier, they are rapidly regressing and or retreating. But if you look at these data, you can automatically see the different moraines within the glacier itself, and we are currently working on these data. But an exciting new data set, and not much work has been done on the cryosphere either. Next. So one of the things about HITES is, I'm not going to go into the details here, but we are building a second airborne HITES instrument, and we do have some new detectors for that instrument, which allow us to produce even better quality data in that wavelength range, 7 to 12 microns. So just to summarize then, eco-stress data available until 2029, 2030, that time frame. Still the highest spatial resolution instrument up there. It's very useful for looking at putting together precursor data sets for Trishna, SBG, and LSTM. We also have the airborne instrument for doing local studies, and these data are also available, and more information is indicated for those 2 websites that I've shown there. So I'm going to stop now. Thank you very much.
Okay, thank you very much, Simon. Thank you for opening this path of very, very exciting thermal missions. Thank you. So I'm giving the floor now to Ralph and presenting the SBG program from NASA. Thank you.
Thank you, Teddy. Okay, thank you very much. My name is Ralph Basilio. I'm with the Jet Propulsion Laboratory. I'd just like to thank our gracious hosts here at Isro, SAC, and the joint Isro-CNES Trishna team for allowing me to be here. Again, it's an honor and privilege to join you all today.
for some of you who know me, I always like to try to start a presentation by understanding who the audience is. So a little bit of group participation. I'd just like to show of hands, there are people here in the auditorium that are affiliated with a government entity like Isro, CNES, ESA, NASA. Can I just see a show of hands? Yeah. Okay. How many people are with industry, like working for a company? Okay. How about people that are with in academia? Professors, researchers. Okay, how many are students or people that are interested in data applications? So, okay, very good. So we have a large cross section. So I'll try to tailor my presentation to address this broad interest here. So we heard earlier this morning that Trishna is not only an acronym, for thermal infrared imaging satellite, but it also has a meaning. It's thirsty, in the Hindi language. And so for SBG tier, we also have an acronym. So, tier is thermal infrared. A few months ago, Simon and I were at NASA headquarters in Washington, D.C., and we were asked, well, if you had to talk about SBG tier, uh, how would you describe it to somebody who doesn't know much about the scientific and engineering work that we do? Well, we talked about it, we created a chart, we put some bullet points down, and we call it a backyard barbecue chart so that people can understand, here are the talking points. If I'm talking to my friends and family, they can better understand what SBG tier is all about. At the very end, I think we were just half-heartedly joking about it, and we said, well, SBG tier is a thermal mission, so it must be a smoking hot mission. So smoking hot mission. So it's just something that reminds us about the work that we do. So let's go to the next page. Actually, I just wanted to acknowledge that this is a joint project, SBG tier, with between NASA and the Italian Space Agency. I'd be remiss if I didn't acknowledge my counterpart in the Italian Space Agency, Dr. Simona Zoffoli, and our joint team working together on this SBG tier project. So it all started with us in the United States and with NASA and SBG with what we call the decadal survey. So the U.S. National Academies conducted a survey about 6-7 years ago, and it helps establish priorities for the U.S. space program and especially NASA. So one of the designated observables that was identified was surface biology and geology. So if we go to the next slide, there are focus areas, and you'll hear more about this. There's a lot of common themes, but we talk about 5 general areas, which is climate, ecosystems and natural resources, hydrology, solid earth, and weather. So one of the things that kind of brings home to me, like, what is the specific purpose? What are the purposes of SBG tier? So I also work in a larger group called SBG, and we have a V-SWIR element. So the V-SWIR element, for example, can look at surface mineralogy. And so they can look at clay material like kaolinite. They can look at iron oxides like hematite. So SBG tier complements the ability to see this broad range of surface mineralogy by focusing on silicates and silicate minerals like basalt and granite. So it's quite complementary in nature. So it really takes all of these observations and all the researchers to produce the value and utility to the research and applications community. So let's go to the next slide. So this comes out of the decadal survey, and it speaks to both the V-SWIR as well as the tier mission. I'm going to focus on number 2, which is the theme of today and the next couple of days, and it has to do with the thermal infrared observations in the thermal infrared part of the spectrum. So one of the primary goals for us is to try to provide a short revisit time, somewhere between 2 and 4 days. You'll see later that the baseline is a 3-day repeat cycle, and then working in conjunction or collaborating with LSTM and with Trishna, together we'll be able to produce a daily volume of data that'll serve up
thermal quantities of interest like evapotranspiration and such to the community at large. Let's go to the next chart. So SBG tier or SBG is actually part of the NASA Earth System Observatory, and ESO basically is comprised of a number of different observations and satellite systems. So SBG is on the far left side, and in the lower left corner is surface deformation and change. We heard a little bit about NISAR and the work that Isro and NASA are doing, and we're looking forward to a launch of Isro next calendar year. And that'll actually be a mission that will serve at least the initial needs for surface deformation and change observations. On the upper right-hand corner is what we call now AOS, this Atmosphere Observing System. There are actually two elements. There's what they call the inclined orbit, and then finally the polar orbit. So those are split up now into what they call AOS, storm, and sky. And there's a significance there when I get to it. On the bottom right-hand corner is what we call mass change, or we refer to that as gray C. And the reason I bring this up is that NASA is focused on making sure that they maximize the community, maximize the value utility to the community. They obviously have, I would say, very real, very practical constraints like budget and money and those types of challenges. So the concept that NASA is following, the Earth Science Division, is to decouple, to partner, and also to compete. So in that kind of framework, they can try to meet all of these objectives here without having to cancel a mission, for example. So these are very real constraints that NASA has to deal with, and that's the philosophy that they're choosing. So we can go to the next chart. That's the primary reason this decouple, partner, and compete is the reason why SBG is broken up into both the SBG vSphere project and the SBG tier project. So for SBG tier, we are planning a launch as early as December of 2028. We're looking at a 3-year prime mission, but we also want to make sure that we have enough resources on board so that we can have a long extended mission, at least 5 years. So that's what we're looking at. So in addition to partnering with the Italian Space Agency, within NASA, we also are partnering with other NASA centers. So for example, Ames Research Center, the Goddard Space Flight Center, Kennedy Space Center, and such. Next page, please. So here's the SBG tier architecture. So I'll start on the upper left-hand corner and then just work clockwise. We will be launching on a Aussie provided launch vehicle. The baseline is a Vega C launch vehicle. And on the upper part of the figure is the actual payload system. So this is the flight system. JPL will be providing what's called the thermal infrared, or what we refer to as the orbiting terrestrial thermal emissions radiometer. And Aussie will be providing a visible and near infrared camera, and we call that VIREO, so visible and infrared Earth observing camera. And then that will be mounted on an Aussie provided spacecraft. So it's really an international flight system. Telecommunications is handled primarily by NASA JPL with scheduling capabilities that are provided by Aussie. Aussie and JPL will conduct mission operations, and then we have specific science data systems for both the Otter instrument as well as the VNear camera. And on the right-hand side is just kind of a color coding to see which organization is providing what particular element of this very critical mission that we call SBG tier. So let's go to the next slide. For me, this is always a fun slide because I'm trained as an engineer. I kind of like doing this kind of stuff. So this is really the heart of SBG tier. So this is what we call the payload system. So it's Otter. So it's the thermal red instrument with this VNear camera, or what we call VIREO. So without going into a lot of detail, there's a color coding here where you see the tan or sand colored elements. Those are elements of the Otter, or the orbiting terrestrial thermal emissions radiometer, and in black is what we call the elements of the VIREO camera. So we heard earlier like the architectures for the other instruments. For us, we take advantage of the eco-stress architecture, which is this push whisk system. So we have a constantly rotating mirror that provides this cross-track motion, and then the motion of the spacecraft provides the long-track observations itself. Our field of regard is a little bit more than about 68 degrees, so I would say we're comparable in the swath width to Trishna. It's about 935 kilometers. And we have this veneer camera, or what we call Vareo. It'll actually allow us to not only do scientific missions on our own, but for those of us who have a fundamental interest or understanding about, like, for example, evapotranspiration, you'll know that one of the scalar functions in order to get from this predicted ET down to the actual estimates or retrieved estimates for ET, you need scalar functions. One of the scalar functions, you need NDVI, which comes directly from this veneer camera. So differently than how EcoStress does it with contemporaneous measurements, we have simultaneity of these measurements, which is going to be a boon to providing better accuracy for these ET retrievals. So next slide. Here are the key specifications. I would submit, maybe in the interest of time, that I will go ahead and maybe just speak to just a few of these to highlight some of the things that we're doing. So number 4, the noise equivalent delta temperature, which is a measure of sensitivity, even though our high level requirement is 300 millikelvin at 300 Kelvin, we have lower level requirements that we are targeting. We are targeting 200 millikelvin because we understand that that's the state of the art and that's what the community is looking for. As far as the absolute accuracy, we're also targeting an improved accuracy, maybe as much as like 500 millikelvin there. The modulation transfer function, or the MTF, is greater than 0.2, and we do have a design already where we have estimates that allow us to show that we can meet that modulation transfer function. In the middle of the chart are the Vareo camera specifics, and then finally the orbital parameters. So kudos to all 3 teams, LSTM, Trishna, and SBG Tier. We've coordinated on the local time of acquisition, which is the maximum plant stress time at 12:30 p.m. So let's go ahead and to the next chart. And so I'm almost done here. So the international collaboration, again, will allow us to have higher temporal resolution. So instead of the nominal 3 days for SBG Tier, for example, flying in a coordinated manner, in a collaborative manner with Trishna and LSTM, all of us will be providing to the research and applications community this daily resolution of evapotranspiration, other thermal quantities of interest. I would also submit that one area of opportunity, you saw observation mask from LSTM and from Trishna. We also have an observation mask, but that's an area where I think we can actually develop some synergy so that we can pinpoint specific targets of interest and allow us to work together and provide even greater set of observations for the mission. So I have one last chart, and my closing remarks, SBG Tier is responsive to the decadal survey back in 2017. We have an excellent example of international partnership with the Italian Space Agency, and obviously with collaborating here with Isro, CNES, ESA, and I'm fully expecting that over the course of the next several years, we're going to provide a boon to the research and applications community. We saw a lot from Simon about eco-stress and high test, but I would submit they're only scratching the surface. And once we have Tier, vSphere, Trishna, and LSTM, it's going to provide something that we're going to be all proud to be part of. So thank you very much for your time and attention.
The next one is Hydrosat, from our colleague from the University of Delft.
Yeah, thank you, Mr. Chairman. Thermal infrared colleagues. Yeah, this is another story on ET and moisture and water stress. So I will try to be short. There's maybe one distinct difference. Hyderabad is a private sector company, so we are not a space agency. We are private sector. Our headquarters is in Washington, D.C. We have offices in Luxembourg and also in Wageningen in the Netherlands, where I am from. So really, Hyderabad is meant also to add to this very interesting space between near infrared and SWIR and thermal infrared. There are also other private sector companies coming up. It's good to have some competition, I would say. I'm only pleased we get more and more thermal data. Our first satellite is already up. We will launch another 15 in the next year, so it will be busy there up with a lot of thermal measurements. So this is an old picture, I think. The SBG, LSTM, and Trishna EcoStress are there, but they are more presented as individual systems. So I'm very pleased, Ralph, with your presentation that you merge all this data together, and of course then you will end up very close also to the high frequency that Hyderabad is looking for. Also, I want to say again that the thermal infrared really affects the ET and the gross primary production. When the crop is really getting problems with leaf angle wilting and leaf damage and so on, it's really too late and it's irreversible. That you will detect with the visible near infrared. The thermal really responds immediately in terms of minutes to the water stress of a plant. So it's very important we have lots of thermal measurements. So Hyderabad actually was created from GPL. People who left GPL and had a vision. I have to remember Jacob van Zyl. He unfortunately passed away soon after he raised Hyderabad company, but we mentioned the first Pathfinder mission after him. So here's where we are. We have our first one launched in orbit. Second one is planned for 25. And if we get all these investments coming through, then we can really start racing in 26. And we will build every year 5 to 6 thermal small sats. So we are not having these big ones, but we have small sats that only weigh some 50 kilogram, and we can produce them in a relatively short time span. Here are some specs. So the left column is more the first version, and the right is the future constellation. I'm not going through the details, but what we are aiming at is 50-meter thermal and 10-meter visible near infrared every day. These are the bands. So at the moment we have 7 bands. We also believe red edge is important because it gives a lot of information on the fertilization of the crop. That's why we have 3 of them. And at the moment we have 2 bands, but in the future also we will have 3 to 4 thermal infrared bands. That is the plan. So also Falcon 9 through SpaceX, and it's now in orbit at 517 kilometers. We have an early adopter registration, so if some of you in the room are also interested in thermal data from Hyderabad, you can register yourself. There is a very specific site. I assume the presentations will be uploaded after the workshop, so everybody can see this. Otherwise, go to the website hydrosat.com. We have first light. It's always nice. And here are some very first thermal images of Madagascar, and well, no reason to believe something is wrong. Let's put it this way. Probably we will go into commissioning stage first quarter of 25. And so from that moment, these images will become available also for products and for services. So the Hyderabad is having a product called Iri Watch. Iri Watch is meant for farmers to help them daily on their irrigation and also crop monitoring and crop health. And we have at the moment some 4 million hectares, and we have about 120 different crop types. So basically, this is already out there. So this morning, Hyderabad has given advice to 4 million hectares in all those countries on what to do. They get this information before breakfast. Where are the decisions made in farmer's house? At the breakfast table. So you have to, what time do Indian farmers take breakfast? Very early. Oei. Okay. We assume 5 o'clock. So before 5, we have produced all the and processed all the images from yesterday, and they should be on their kitchen table so that they have an advice through their mobile phone what to do. We also look at the region, so for irrigation districts. This is an example from Kazakhstan, because the operations of canals are very important to see whether you can improve. A farmer is dependent on that, on whether the canal delivers water. So we recommend local agencies to digitize the irrigation system. And believe me or not, but that is not very common. So still a lot of work to do also in India on the digitalization of your canals, but not only the canals, but also the command area. Which pixels are served from which canal? That is what we need to know. And then we can also really help with day-to-day decisions on canal operations. Why should you irrigate the canal here in green if the moisture is already near field capacity? It's a waste of water. And believe me or not, irrigation management still has to begin. I'm actually an irrigation engineer. I don't understand all these space engineers, what they're talking about. Maybe they don't understand me. But irrigation engineering and water management is still to begin because there are no measurements, not in the field, not even in the canals. So a lot of corruption and people don't know where the water is going. So I love the concept of water productivity. In fact, Hyderabad is launching an own water productivity portal next year at field scale, crop specific, where you can sign up and we can really give water productivity values. But if we really want to increase the water productivity, we have to start managing our canals better. And there's another example. So the flow is measured here in the main canal, but then you have secondary canals in your fields. No data. People don't know what's happening. Now, having the daily ET and daily moisture, we can really change that. That is fantastic. And for instance, just one example, everybody's claiming that they are not getting enough water. Everybody wants more water. I never heard somebody say, give me less. You know what the farmers in blue say? We want more water. And you know how much water they are using already? 900 to 1000 millimeter. And the one in red and orange only use 600 millimeter. All the policy documents are full with equity in water management. But it's a joke. In reality, if you look at the data, number one, there's hardly any data. Number two, there's no equity. So we really have to help this irrigation community with thermal, high resolution thermal images. That also can be expressed into performance indicators. I'm not going into detail, but it's very normal to have KPIs to evaluate your work. whatever sector you're working in. And I believe also very strongly in performance irrigation indicators. So we can really say which canals are good, where can we save water, what is the water stress level, and so on. And then just to close, at the moment we already help some 40,000 farmers in India. They use this data in different states. And I'm very glad also to announce that further in the week I have to go to Maharashtra, where another 100,000 farmers are signing up. So you can see an uptake of this. Very interesting also to say is paid by private sector. Zero money from government or subsidy programs, just paid by farmers and the agricultural industry. Of course, we cannot make this very expensive, but I believe in mass production. And if we go to mass production, we have to go to the 100 rupee per hectare per year, which is possible. But then we have to hurry up and we have to create mass production. Yeah, this was an example of the daily advisory service. So it tells you also which field is having stress, which field needs to get more attention. Not only ET, but also other things of the water balance and soil moisture, soil water potential. Soil water potential is grossly underestimated. If you don't know your soil water potential, you don't know the energy status of the root zone. And this is a very important parameter in which we have invested a lot of energy. And last one is a very interesting study with Bayer also, where they want to move away from this kind of practices. This is nice. Some people believe this is nice. Actually, it's not nice. This is the traditional way of flood irrigation of rice. We have to go to alternate wet and drying. It's there for 25 years. 25 years ago, already scientists showed that if you let all this water infiltrate into the soil and then you irrigate it once in 4 or 5 days, no impact on your rice yield. You have saved tremendous amounts of water. Also the methane emission, because all this anaerobic rice is having huge methane emissions. That is something that is not longer accepted. And it's interesting to see that bigger companies who also want to greenwash probably, but they invest in these kind of solutions to really save water. Thank you.
We'll move on to the NSR and Trishna Synergy. Mr. Anup Das, SAC IRS.
Well, good afternoon. Trishna and NICER, one is based on thermal energy, another on microwave, is likely to complement each other in many areas. And the scientific community, particularly the ecosystem science community, they're very keenly looking forward to these two missions. Myself is Anup Das. I am one of the co-leads from Isro for NICER. I'll be giving you a status update of NICER mission and bring out certain areas where these two missions complement each other. NICER is a very, NICER stands for NASA ISRO Synthetic Aperture Radar Mission. It's a dual frequency L and S band, jointly developed by NASA JPL and ISRO. The L band is developed at NASA JPL and S band is developed here in SAC ISRO. This is a mighty satellite in terms of its mass, volume, in terms of its coverage, and in terms of its data throughput. And these are some of the high-level specifications of NICER. It will be placed at a 747 kilometer orbit with a nodal crossing time of 6 AM, 6 PM. So it's a dawn-dusk orbit. And this satellite, the most distinct part of this satellite is this huge circular 12-meter reflector antenna that is based on a novel SweepSAR technology that allows the radar pulses sweep across a larger swath with retaining very high resolution. This satellite has various modes of observations depending upon its polarization as well as wavelength, the bandwidths. So it produces high resolution as well as high large swath imaging. The swath is about 240 kilometers. With this configuration, NICER covers the entire global landmass and coastal oceans, including polar regions, in every 12 days, exactly without any gap. The primary goal of this mission is to capture any changes on the Earth's surface, changes as the physical changes as well as environmental changes. Currently the satellite is fully integrated with the bus, and this shows some several snapshots of this satellite being integrated and tested in URSC, and the photographs also shows the delivery of payloads from NASA, and the satellite is scheduled to launch early next week. This satellite actually, it took a long time to develop this satellite, and about more than 200 scientists, engineers from Isro, and equivalent number of scientists from US. They work together for this satellite, and it's a classic example of collaboration between two countries which are geographically just opposite, and and without any overlapping working hours. When we worked, they went to sleep, and vice versa. So effectively, and literally, people worked round the clock for the development of the satellite. The satellite will be launched by Isro using GSLV Mark II vehicle sometime soon in the next year. This mission has certain characteristics to facilitate several applications related to ecosystems, cryosphere, land deformations, ocean, coastal sciences, as well as to support disaster management. This the L and S band joint frequencies will enable addressing vegetation of various biomass and both tall and short vegetation due to their sensitivities at different levels. This SweepSAR technique will allow a global data collection without any gaps in every 12 days. And the satellite orbit is will be very precisely managed with a baseline of with less than 300 meters through regular maneuvering, so that it attains a very precise interferometric orbit to that determines any change on land in sub-centimeter accuracy. This satellite has been configured for left-only pointing to cover the Antarctic region up to 87.5 degree latitudes, sacrificing areas in the North Polar region with the intention that North Polar region is being covered by other satellite missions. So NICER will leverage from that data instead, and it will have a very continuous time series, uninterrupted time series over Antarctica. This is the snapshot. This is a snapshot of NICER global coverage in one of its 12 days orbits. And you can see the entire global landmass, including the polar regions and several islands, the major islands, coastal areas, will be covered at different modes. This modes has been very scientifically developed to cater to various needs, various application needs, and giving priority to a uninterrupted time series data. And this is another snapshot, and you can see the different color, they represent different modes of observations over different period of time, and this time will remain constant, and every 6 months this observation plan will be reviewed to add any new targets if necessity comes, without interrupting its time series data. This NICER has a predefined observation calendar, and this observation calendar has been very meticulously developed to ensure suitable targets are observed by suitable modes over suitable period of time. And since the resources of the satellite is limited, so this observation planning is also very stringent in terms of which modes and period of observations. And this is a typical example of observation calendar over Indian region. And these are the regions. NICER will basically collect data over the global targets in L band, and in certain regions which we call as the targets of Isro's interests, where the L and S band jointly will be operated. So these are basically these targets. You can see the Indian region, the Indian coastal seas, and various global calval sites are included in this, including some major parts of Antarctica. NICER data products will be structured into level 0, level 1, level 2, 3 and 4 products. Level 0 products are basically level 0 and level 1 are basically the products in the range Doppler or the radar coordinate systems. So the R stands for that. And level 2 products are basically the geocoded products of the corresponding range Doppler products. And level 3 represents the large area mosaics, and level 4 are the science products. These data products, NICER has a open and free data policy, and this data will be disseminated through ISRO's Bhunidhi portals and NASA's ASF DAC through various modes. These are the major science objectives for NICER, as NICER will focus on certain themes of applications areas like ecosystems, hydrology, solid earth, cryosphere, coast oceans, as well as support to natural disasters. I will not get into the detailed discussion of this due to shortage of time, but these science objectives would be supported by various science products. These products are will be generated at different frequencies depending upon the characteristic of the products, starting from weekly products to annual products, and these products will be disseminated at different and this shows a snapshot of Calvel plan for NICER data as well as science products, and we have established a lot of calibration sites in India where periodically we are collecting data. We have deployed instruments, and this calibration plan is well set for NICER. Even there is a large network of corner reflectors going up to Antarctica has been deployed for NICER calibration. So Krishna mission has certain these characteristics, and I don't think this audience requires any introduction of Krishna. This Krishna mission, it's a thermal mission, and its primary objective is to monitoring terrestrial ecosystem water stress and water use, and high resolution observation of water quality and dynamics of coastal inland waters. So these products will be very complement the NICER's products. If you look at the Trishna NICER products, the science products coming from Trishna would be leaf area index, land surface temperature, FFR, evapotranspiration, vegetation fraction. These products, complements very well with NICER science products like the forest AGB, surface soil moisture, then the monitoring of crop areas and crop types, these products like vegetation fraction, LST, and evapotranspiration, they will help advancing these science products from NICER. For example, this LST and ET products will help in segregating the canopy and stem biomass for forests, which is otherwise it's difficult with NICER. Similarly, the soil moisture also, the surface soil moisture as well as root zone soil moisture can be enhanced using these products from Trishna. And apart from that, there are a lot of other science products coming from the cryosphere as well as other ecosystems that will be benefited from NICER. I have a couple of examples to show. This is basically one SAR backscatter image of NCR Delhi, and you can see at the top right and top left portions, there is no amenable, there is no very differences between the crop types here. If you even look at the HHHB polarization RGB, there is no apparent distinction between the left and right. But if you see the LST, this temperature variation is quite large. This is because this is during the month of May it is taken, and you have areas at the left, these are harvested fields, whereas at the right there are still crop there, or these are planted crop fields. So this kind of information will definitely benefit enhancing NICER products. Right hand side you can see one image that shows the top one shows the above ground biomass map for a place in Shimoga and Karnataka, and you can see the bottom one is the corresponding LST image, and it shows a very clear relation with the canopy density and biomass with the land surface temperature. There are various inventory plots we have established through NICER mission, and over these plots, the biomass and LST value, they correlate well. There is another example of the role of this LST and albedo such information that enhances the soil moisture estimation. Those things will be very useful for NICER. I will not take more time, and I will conclude here that this microwave and thermal synergy will definitely go a long way in terms of NICER and Trishna missions, and we look forward to both the missions for various applications and addressing science questions. Thank you very much.
Thank you, Mr. Anup. I think we can take questions from audience, one or two questions. If anybody has any question with respect to synergy of Trishna with LSTM, SBG and NISR.
Hi, Gilles from the Ecosystem Stress Group for Trishna. So you've been speaking about how Trishna can benefit NICER applications. Actually, for a lot of applications, we need all-weather products. It's going to be a problem for very long cloudy periods, especially monsoon in India. So is there like a working group to try to get some information during that very critical period where actually active microwave could probably benefit applications that are normally done by Trishna? Thanks.
Vimalji.
You are asking question, or this is just comment?
It's a comment.
Okay. Yeah, actually, the soil moisture and cloudy sky. So that is very obvious challenge for the thermal remote sensing, and where actually this nicer soil moisture product, that will be the operational product. So that can actually be complemented to Trishna water stress and evaporative fraction under cloudy sky situations. But if it is cloudy with heavy rainfall, then I think water stress is of no use. So depending on the soil moisture level, correcting that, and then we can implement the evaporative fraction algorithm tuned to the cloudy sky.
I have question to Raf regarding that. In SPG, we have a very limited number of multispectral band. So what the reason behind it? Because in other mission like LSTM and Trishna, we have a more multispectral bands.
Test. Yeah. Okay. So for SPG tier, we actually have a total of 8 bands on the otter instrument, and then there are 3 bands on the veneer camera. So we have a total of 11 bands. For the tier instrument, those 8 bands are broken up into 6 bands for thermal infrared and 2 in the mid-wave infrared. So we feel that those bands are what is needed in order to produce data products such as the cloud mask or cloud detection. We'll also be able to do the retrievals for ET and therefore water use efficiency and evaporative stress index. One of the key things that we are looking forward to being able to provide to the community at large are these very unique mid-wave infrared channels. So the mid-wave infrared channels allow us to look at elevated temperature features. So there was some discussion about wildfires and wildfire management. Yes, that'll obviously be part of the benefit that we can provide. We have a tremendous interest in the Italian science community on being able to monitor volcanic activity. So being able to look at lava, look at the sulfur dioxide, and those types of emissions as well. So we have done I would say, a mapping of the bands that we need in order to produce the data products that we'll provide. And then finally, on the veneer camera side of the mission, we'll be able to obviously produce radiances and therefore surface reflectance. And by having those data products, you can actually do science with that. But from a thermal infrared perspective, like I mentioned before, NDVI is required as a scalar function in order to retrieve ET from the predicted evapotranspiration product. So in short, we've done a mapping of the bands that we need in order to produce the science data products that we are committing to produce to the science community. I hope that addresses your question. Okay, thank you.
I have one question to Simon. That spectral emissivity library is very much necessary for this any good accurate LST, and that for that airborne study is very much required. So already there are a lot of collections from US side and European side. So whether those spectral library are available openly for the emissivity, and what we can visualize for Indian conditions, means how we can approach for Indian conditions if we have to do the airborne hyperspectral thermal this campaign.
Thank you, Bimal. To answer the question on the spectral libraries, there are quite a few spectral libraries that are openly available, the ones in the US certainly. However, there aren't that many libraries that have good collections of emissivity data, and they may have certain types of emissivity data, but not other types of emissivity data. For example, If you're looking for good collections of urban materials, there are limited libraries of urban materials. So one of the things that we're working on with SBG is expanding those libraries and working together with the USGS, so enhancing them to bring in other materials. Now, there will be certain unique conditions to India, and so if there are particular materials that have not been measured, then we would be happy to measure some of those materials. And in fact, we do that with other countries where they will send us some samples. We'll measure them for them and send the spectra back. So we can certainly do that. I'm not quite sure I understood your second part of your question about the airborne campaign. About what were you asking? What will it take for us to come and do an airborne campaign?
Yeah, it may be difficult to answer now for you, so because there are some bilateral things involved, but we are definitely interested for high-test sort of campaign over India even before Trishna.
Yes, we would really like to do an airborne campaign over here. As I mentioned, we are building a second instrument, so we have a little bit more opportunity in terms of scheduling and things like that. I think the planning, the earlier we can start the planning to do an airborne campaign, the better. And I think the first high test instrument will be operating again early next year. And the second instrument will come on later on in the year. But we're happy to start planning whenever there's an opportunity on your side. Okay. And obviously, we'll have to talk to NASA headquarters about funding.
Right. Thank you.
My question to Hydroset. I have seen your products. The people or users are from different parts of the India, but Rajasthan is not covered in that. No user or farmer is from Rajasthan. So how do you select these farmers or the person who are using your products? Either on the basis of some research work or indirect contact with them?
Yeah, thank you for that question. The only way to reach out to a larger community is through local partners. So Hyderabad has some three local partners in India, and then yeah, it depends a little bit on their network, to be honest. So for some reason, the ones we are working with do not have a strong connection in Rajasthan, but in some of the other states. So this is actually quite important because also of the languages in India. So if you really want to make a farm app, it has to be in the local language, right? So a local provider has to do it in a local context with local language to give them this information. So hopefully in 1 or 2 years, you know, it's covered. And there are some nice plans coming up. But yeah, we are just rolling out now. So those things take time.
Yeah. So my question is like all the 4 satellites are like Hydrosat included are majorly with the LTDN of close to noon, 12 o'clock. So when all the 4 satellites come operational, you will be like having 2 satellites which will have more almost like close observations with which are like half an hour apart or 1 hour apart because you will be covering daily.
Yes.
Short. But are you there is no interest in diurnal variation over the day?
No, there is. So Simon gave a very good example of eco stress, and actually I should have mentioned in my presentation that we download big stacks of eco stress every day. Also Sentinel, you know, we have a big pile of Sentinel images. At the moment, we still mainly use open access data, but with the launching of our own satellites, we can complement open access. We will never replace open access. So I'm really looking forward to the LST group data that is coming available. Interesting is that
They all agreed apparently to have 12:30 as overpass time. There is consensus, which in a way I like a lot. So, because then you can have maybe daily or 2-day coverage depending on the position. I think that Hyderabad should go at a different timing, because I know for sure that the crop stress is different in different moments of the day. Okay, so I like to measure between 10 and 3. So we have a 5-hour span where I like to take thermal images from. Now, I will not be able to convince my team to have all these variable times, but I really would like to go not at 12:30, so that at least we can cover some different moments. And actually, I have a tendency for the Lancet overpass time, because that is in the mid-morning. These plants work very hard. They have the maximum sap flow. They have the maximum ET. Stomachs are completely open. In the afternoon, they all start closing. So I, from a scientific point of view, I think 10:30. Jill, what do you think? We should have a mid-morning overpass as well. If that was your question, hopefully.
I think during lunchtime we can have more discussion, if any. Yeah, please.
Thank you. And this concludes the first session here. And we are thankful on behalf of LOC chair and on behalf of organizing committee. We are thankful to our co-chairs, Thierry Carlier and then Nagalakshmi madam. So as a token of appreciation, I would like to call Rohit to present a memento to Nagalakshmi madam. So now I would like to call Ujjwal Gupta to present a memento to Thierry Carlier. So we thank both the co-chairs and rapporteur Nitesh Thapa, all the speakers, audience, and everyone to successfully conduct this session. Now we will break for the lunch, and then we will assemble here after 45 minutes because we are already late. So we will assemble here in the same hall. Thank you.
Yeah, but it's good to have one more. I don't know 12:30 the best, but I was not part of it.
One more request to all the speakers, those who have not sent presentations now, please send it on the email ID given, because it is a restricted network here and we face difficulty in last moment. Please send your presentations.
Hello. Hello, Teshwar.
Amazing.
But you see, I don't understand.
Hello. Hello, mic testing. Hello, check. Hello, mic testing. Hello, mic testing. Hello, mic testing. Check.
I can hear you. I'm online though. Does that help?
Hello, mic testing. Hello.
So, whoever's saying hello, mic testing, I can hear you. I don't know if that helps you with your mic testing. I'm online.
Hello.
नहीं, यहाँ पे भी लोकल मतलब इन पर्सन कह रहे हैं कि डब्ल्यू शायद इन पर्सन कर देंगे, अगर नहीं हो पाएगा तो ऑन बिहाफ ऑफ मेरे तो स्टार्ट करके तो पूछें या पहले पूछ लें पहले। Good afternoon. This is for Mary Neely.
Yes, I'm here.
I am Arvind Sahai from SAC Isro. Mary Neely, this is for you. Mary Neely from Nova. Am I audible? Can you hear me?
Yes. Yes, I
Okay.
hear you.
Okay, so this session is going to start within a few minutes. So I'd like to request you to join the link and you can present from there. You have to present from there.
Oh, could somebody resend me that link? Because I thought I was on the correct link. I used the one in the meeting invitation.
Mary, otherwise we can put your slide here and then you can speak from there.
Yes, but I just so you're aware, I'm not able to see the screen.
No, we will start meeting in 10 minutes, 5-10 minutes, because we are a little late actually. And the only thing is because we are late, so I'll request, if you want, you can be first presenter, okay?
No, I can go in the order.
Okay,
Yeah,
fine.
I'm awake. There's no problem. I'll probably be even more awake when the time really comes. I did send a slightly updated version. The only difference is I had an older footer on it. So
this is Pradeep here. Is it the same version which last night we communicated? I sent you the last one.
Yes, yeah, you did.
Thing.
So if you use that one, that'll be perfect. And then I'll just say next slide.
Yeah, the same thing I have already here.
Good. So if you can hear me, then I think we should be fine.
Now screen share नहीं किया उन्होंने.
Mary, this is Rashmi.
Yes, Rashmi. Yes, I heard you introduce yourself, but then I don't hear you anymore. Oh, I hear you now.
Yes. Chat उससे बोलो. Chat. What she has written in chat. Nikhila.
So I can hear you again.
So, good afternoon. Welcome for the second session. The session is algorithms of surface and atmospheric properties. And I would like to invite the co-chairs for this session, Dr. Pradeep Thapliyal from Space Applications Center and Dr. Farron Gascon from European Space Agency. Please come for taking the proceedings. And the rapporteur for this session is Ujjwal Gupta.
Good afternoon, everyone, for this first session after the break, the lunch break. I would invite the presenters to join us here in the scene. So please, if you could come here. Thank you. So there will be a remote presenter and the others might join later. So our first talk will be a share between CNES and Isro. We have Emily Delogu and Mehul Pandira, who will share this presentation. Thank you, please.
Okay, hello everyone. So with Mehul, we prepared some slides in order to show you the retrieval of land surface temperature and emissivity for Trishna. Here on the first slide, you have an overview of of the processing chain to compute the level 2 product for Trishna. So in input of this chain, we will take the level 1C product and combine it with some atmospheric data and with the DEM. Then we will compute the cloud mask. I will talk about it in a next presentation. We will do the atmospheric correction of the visible band in order to produce the surface reflectances. And we will also do the atmospheric correction of the thermal bands in order to produce the land surface temperature and the emissivities. So together on Isro and CNES side, we proposed different options for both steps of the TIR processing. The first step is the calculation of the land living radiance. We have two options to do so. And the second step is the temperature and emissivity separation. And we also have two options to compute the temperature and emissivities. So here you can see the two options we agreed on in order to determine the land living radiance. The first option is called SAC, Simplified Atmospheric Correction, and it's an approach based on machine learning trained with Motran outputs. And this option will be detailed in the session this afternoon by Ashwin Gujrati and Mehul Pandya. The second option is the use of meteorological data and radiative transfer code proposed, which is RTTOV. The idea is to download ECMWF data, especially temperature profiles, water vapor profiles, and ozone profiles, to do time and spatial interpolation at the time of acquisition, and then to use the DEM in order to adjust the profiles according to elevation of the pixel. We will then use the water vapor data coming from the visible band in order to adjust the water vapor profile. And then we will be able to reformat the input to run RTTOV and compute the atmospheric parameters. For temperature and emissivity separation, we also agreed on two options to be developed. The first option is the TESS algorithm. It's an algorithm which was initially developed for Aster and which is based on an empirical relationship between the spectral contrast and the minimum of emissivity of the spectra. This algorithm may be not adapted for surfaces with low spectral contrast and strongly depends on the spectral library used for calibration, but it's a very common method for TIR sensors. The second option is called direct TESS. It's based on a spectral database of emissivity, and the idea is to find the surface emissivity spectrum within a spectral library, which is consistent surface temperature in all four Krishna spectral bands. This algorithm needs more resources than TESS and also strongly depends on the spectral library used for calibration, but it's an innovative method developed especially for Krishna. Here it's just to say that the TESS algorithm, which have been modified for Krishna application, will be detailed in the session 1.4 by Ashwin. And I put here the link of the publication on the direct TESS algorithm. I will now give you a few details on the direct TESS algorithm. So the idea is that we will have 4 TOA radians coming from the 4 bands of Krishna. We will be able to compute the atmospheric transmittance, upwelling radiation, and downwelling radiation using RTTOV. And what we don't know is, and what we want to know is, which is the emissivity. So we use, just like I said, a spectral library, and the idea is to take the first spectra of the spectral library and to calculate the temperature for each band and each material of the spectral library. So with the first spectra, we will have 4 temperature in the 4 bands. Then we will use the second spectra, the third, and all the spectral library. Then for each material, we will check the consistency of the 4 temperatures to determine if the material is okay or not. And to compute the final temperature, we will take the median over all valid materials. We could also use information from the V3 in order to get rid of the obvious non-consistent material, knowing what we are looking at. An improvement of the direct TESS algorithm is called here double direct TESS algorithm. The idea is quite the same, but we will do a first test using only the TIR3 and TIR4 bands. So it's the band centered at 10.6 and 11.6 in order to calculate the temperature for each material and to get to target temperature. Then when we will able to know this target temperature, we will run the direct TESS algorithm just like I just showed. And then we will check the consistency of the temperatures between one to each other and with the target temperature. And then we will do the median for each pixel in order to compute the final temperature. Here you can see the evaluation of performances we made on theoretical data sets. So we compute a surface reference data set, then compute it to TOA, and then we are able to add sensor uncertainties, atmospheric uncertainties, and we apply the different processing options in order to compare the surface retrieved data set with the surface reference data sets. And we are able to evaluate the performances of the different algorithms. In the table, you can see the theoretical performances of the different algorithms on the theoretical datasets. And what we can see here is that with both sources of uncertainty, we have two options that gave the best results is the use of RTTOV and the double direct test, which yields to an error of 0.5 Kelvin, and the modified test method that will be presented by Ashwin just later, giving a 0.4 Kelvin error. Here you can see the evaluation of RTTOV plus direct test on actual eco-stress data. We took level 1 eco-stress data on a tile located around the Calval site of Laco in southeast France. And on the right, you can see the performances we got from direct tests. We computed the surface temperature with direct tests on matchups between eco-stress and in-situ data. And the performances of eco-stress of direct test, on this data set is 0.3 Kelvin bias and 0.9 Kelvin error. Here you can see some images extracted from the first tile. The first one here is around the Calval site of Lacroix. And what we can see here is that the direct test products seems to smooth the radiometric artifact compared to the LST eco-stress product. And we can see with the direct test product some details. Just we can see the airport that is in the right corner of the image. This is another extraction around the city of Avignon. We can see that we can retrieve a good contrast between urban area and natural area. And also here again, we can see that direct test allows to get rid of the radiometric artifact from ecostress. Now I will let the floor to Mehul.
Yeah, thank you, Emily, for nice overview. I'm going to just discuss or show some results from the other option, which basically first does the AI/ML based atmospheric correction, where we generate two basic terms, surface living radiances and down living radiances equivalent to Trishna bands. Or you can see these results are quite consistent with respect to true radiances. These are model radiances where surface living radiance actually estimates give very, very good consistency. Downwelling also in terms of RMSE and R square. The most important term is surface living radiance in subsequent, observations and calculations. If we talk about results of modified tests with respect to the conventional tests, with 1.5 Kelvin as a mean value, the modified test provides very good estimation or better estimation compared to original test. So based upon our AI/ML based atmospheric correction fed into the modified test model, and which we combinedly say it is a SAC test model, which also is being used for emissivity retrieval. So you can see some of 16 various land cover types where emissivity retrieval are shown with respect to the true values, where blue ones are reference and red ones are retrieved one. They are actually the shapes, numbers, they are quite consistent with each other, and this provides a very good RMSE numbers into all of the bands. So with these numbers, we made all, systematic modeling framework, which we say SEC test, and we applied it on many ecosystems across globe. What we are showing here is 8 various ecosystems over India, where SEC test, method was applied, and it gives a very good estimation of land surface temperature. I'm going to show very briefly the comparison of eco stress versus SEC test method. By and large, qualitatively, the images, they match very well. Kelvin. Paired with eco. Preliminary results of modeling, which we try to present. Framework is the beta version is ready for LST and emissivity retrieval. Concluding the slide, I request Emily to conclude.
Thank you. For the conclusion, as you can see, we agreed on a joint baseline activity for the temperature and emissivity retrievals with a different option for the radiative transfer and for the temperature and emissivity separation. We will now have to define common data sets for global and regional contexts, both theoretical and with actual data, in order to evaluate all processing steps separately and as a whole. And we will do that to try to narrow down some option if possible, and all the various options will be implemented in the ground segment, in the 2 ground segments, in order to allow the most informed choice potentially after launch. Thank you.
Thank you, Emily and Mehul. So Emily, you can start your next presentation on sea surface temperature. So for this, you have 10 minutes, and I request Rishi also to join here. Yes, because we will take question answer towards the end.
Okay, so for this presentation, we work together with Rishi in order to show you the same way we did for the land surface temperature, how we intend to retrieve the sea surface temperature and emissivity for Krishna. So the same graph here in order to show you that in input, we will also take the level 1 product combined with atmospheric data and DEM. We will compute the cloud mask, and then we also agreed on 2 options that will be developed and implemented. The first option is a split window method, and the second is also to do a proper atmospheric correction and then to try to retrieve the SST using a direct test approach. To give a few details, the first option, the atmospheric correction plus direct test algorithm, is based on the idea that the emissivity of water is well known. And then we can perform the atmospheric correction and calculate the SST for all Trishna channel, assuming that known emissivity. We will use for that all available spectral information with the 4 bands of Trishna, and we will have the possibility to retrieve the atmospheric parameters. The split window method is based on at least 2 adjacent TIR channels in the 10-12 micrometer interval. The hypothesis is that most natural surfaces have a flat emissivity in that domain. And the proposed algorithm is the NL-SST split window method and uses TIR1, 3, and 4 band. The TIR1 band is centered at 8.6 micrometer. Split window is also sensitive to calibration, which contains approximations of the radiative transfer, but it's very commonly used by the ocean community to retrieve SST. I won't come back on this slide, but the idea is the same. The difference with what I already shown is that for the emissivity, we won't use a spectral library, but we will calculate the emissivity according to the Nichols 2009 equations, taking into account the viewing angle and the wind speed. And then we will compute the 4 temperature in the 4 bands and take the median as the temperature of the pixel. We also made some theoretical evaluation of the direct test algorithm on water. And then without any uncertainties, we can see we have no bias using a direct test. When we add sensor uncertainty, the impact was limited. We got a bias of 0.3 Kelvin. And when we add atmospheric uncertainty, the performance were slightly better with a bias of 0.4 Kelvin. And the overall performance of direct test upon water with both sources of uncertainty is that we got theoretically a bias of 0.5 Kelvin. Now, I leave the floor to Rishi.
Thank you, Emily. Good afternoon, everyone. So for Trishna, from Isro side, we are proposing the widely used algorithm, which we are also using for our INSAT 3D series of imagers. So that is known as the nonlinear SST algorithm, which was actually proposed by Walter et al. In 1998. But in the case of Trishna, we have additional 1 channel in the window by 8.6 micron, which we don't have in INSAT 3D series. So this time I am proposing NLSST formulation using that 8.6 channel also. This is the difference between conventional NLSST and the NLSST, which I am proposing for Trishna. So this is the algorithm, formulation of the algorithm, which we are going to use for Trishna. Okay. So this is a pre-launch activity which we have carried out. This figure on the right hand side shows you the noise sensitivity on the simulated data set. So we have simulated the Trishna observation by taking the diverse data profiles which are available from ECMWF. The diverse data is actually representative of all the dynamic as well as seasonal variability of the sea surface temperature across the globe. And here you can say that on x-axis, the random noise is there, and y-axis, what is the RMSE in the SST can be expected. So you can see that Okay, so as you go on increasing the random noise in your observations, the RMSE of SST will also get deteriorated. So as far as for a given noise figures of Trishna bands, it's 0.25, 0.23, 0.25 to 0.3 Kelvin in the fine resolution mode, and as well as in 0.1 K in the reduced resolution mode. So we can expect the accuracy of better than 1 Kelvin over the coastal regions and better than 0.5 or 0.6 in the open oceans. So this is some results which this proposed algorithm we have tested on a limited data set of eco-stress. So this is just an example. Here the leftmost figure is showing the retrieved SST using the proposed analysis algorithm, whereas the rightmost is retrieved SST using the direct test algorithm proposed by the Keynes colleagues. And in the middle, this is the operational eco-stress product which are being disseminated through their portal. So you can see this all the two LSST as well as direct test algorithms are able to capture the fine scale features. Now to quantify these errors, we have also compared our retrieved products with the in situ measurements. Over two sites, one is Lake Tahoe, another is Salton Sea. So you can see here it's this scatter plot is between the retrieved as well as the in situ SST, and you can see both the algorithms are performing well with either as compared to radiometer SST. So based upon these comparison, we cannot say right now which one is better. Therefore, during the commissioning phase, we will be evaluating both the options so that we can decide which one is performing better. So this is the conclusion. So right now we have agreed on joint baseline ATBD or SST retrieval, which will be having both options, split window as well as direct test. And we also agreed upon to define some common data sets so that we can evaluate our respective algorithms and then decide whether which one we should use for our operational SST products. So thank you.
Thank you very much, Emily and Rishi. So we move now from sea surface temperature to surface reflectance, still staying in the retrieval domain. And for that, we have again Emily, who's doing a marathon of presentations, and this time with Manoj. Please.
So, good afternoon, everybody. As already told, but I re-verify myself, Manoj, and my co-presenter, Emily, common team player in almost all presentations. So, I'll be talking about on the topic of this atmospheric correction. So I'll be starting with the challenges, introduction to the problem of the physics, and cover the land part, and then after Emily will take the case of water. So, so starting with the first point, why atmospheric correction is the must, specifically for faithful vSphere remote sensing. As we already know that whatever we will be measuring from the space at the top of the atmosphere, having coupled information from surface as well as atmosphere, and if we are interested in surface properties, then we must retrieve something that is directly correlated to the surface properties, and that is surface reflectance. As we know that atmospheric constituent particles like aerosol, absorbing gases, they all modulate the top of the atmosphere signal, and as a result, they add path radiance that not only distorts the visual appearance by introducing a layer of haze over the real surface signatures and disappearing the fine signatures, but also distorts the spectral signatures, leading to the biased level 3 products, and that's why it is necessary to have atmospheric correction procedure. So if we say have a good atmospheric correction process, then we can have results something like this. The sensor level that is from top of the atmosphere, which seems to be very hazy, leads to the actual surface reflectance images that makes the surface features more visible, as well as improves the spectral signatures and thereby decreasing the error in the derived L3 products such as NDVI, vegetation indices, or any other water indices, as well as level 4 products like evapotranspiration that utilize these inputs as the primary inputs while doing modeling. So this is just showcasing a result how atmospheric correction improves the apparent look of the images when there is high resolution images. So it makes special features very much visible, increasing the information content. So how we do atmospheric correction, conventionally it is considered as a sequential process. For the case of multispectral sensors, for hyperspectral sensor, we have a modified approach where we simultaneously retrieve the atmospheric and state vectors. But for the case of multispectral sensor like Trishna vSphere, we will be going with the sequential process of retrieving the surface properties like atmospheric characterization, like aerosol optical depth retrieval, then water vapor retrieval, and then just doing the algebraic inversion of surface reflectance with the help of some accurate radiative transfer model. So the first challenge for Trishna. Properties. .1 micrometer and 1.24 micrometer, and those are unavailable with our Trishna vSphere, and therefore we have to look for some innovative solution. And there comes the two algorithms, Maya and Sire algorithm, that have capability to retrieve the aerosols even from the sensor not. And another is balances that increase. Anyway, this is one. Atmospheric correction from Maya, we will be inheriting the multi-temporal approach. From SAR, we will be inheriting the multi-spectral approach, and we're combining two to have a better atmospheric correction solution for our this particular SAR case. So what to implement it with Trishna, because Trishna is having different specs, having different missions, and therefore one of them is that varying imaging geometry. So if we will be having varying imaging geometry, that temporal stability of surface reflectance that we are assuming in Maya, that may be an additional uncertainty source. But on the other hand, if we have only multispectral approach and having only one blue channel, we will not be able to optimize the aerosol model online, and we have to have some auxiliary source of aerosol type. Another thing is, say specifically we face here in India, specifically in winter, if you go in IG plane, you'll see stable aerosol optical depth for 10 or 15 days. It is already around 0.5, not 0.6. There is no variation of AOD temporally, and henceforth, again, we have to increase the temporal window, and then that surface reflectance stability will create a problem. So we have to look over. So for that, we came up with solutions that for Maya, we will be having BRDF assistance to robustness of the temporal stability criteria, while we will be supplying externally some information about the aerosol model from CMS model. And we also refine the spectral reflectance models for visible and NIR bands for those who are valid for global applications. Now, coming to the uncertainty, every algorithm has some physical limitations, assumptions, and they introduce several algorithm uncertainties. So in our case, there will be aerosol properties related associated uncertainties, surface reflectance model related, lookup table approach if we will be looking over, and sensor measurement itself. Keeping all these things, doing forward model and inverting back, introducing the sources of uncertainty. For the case of SAR, we found that there is an absolute uncertainty of 0.06 in aerosol retrieval, and there will be a relative uncertainty of about 0.26, that is 25% around, for the typical retrieval cases. But this is the worst scenario. We may have, in real situation, we have a better condition. And that is what we have seen when we implemented SAR over OCM2 and evaluated data for 3 years. What we found, around more than 74% of the retrieval showing uncertainty within the critical uncertainty envelope. Similarly, for Trishna configuration, we utilize Cartosec 2S data because it has exactly the same spectral definition what we have defined for Trishna as far as visible channels are, visible and NIR channels are considered. So we processed 106 Cartosec 2S data scattered around the world. And what we found, as Cartosec 2S is an agile platform, we didn't find any ground measurement for aerosol optical depth. So as a reference, we utilize MODIS data, and we found a very good correlation between Cartosec retrieved AOD from SAR algorithm and MODIS. They show excellent correlation as well as an uncertainty of around 25 to 30%. That is also still within the theoretical error envelope. For the case of Maya, testing in Trishna configuration, Sentinel-3 OLCI has been considered. 2 scenarios were there. One, the constant view angle, another is variable view angle. Both conditions may occur. Say, for example, in 8-day cycle, if we'll be considering, we will be having Trishna vSphere imaging with similar view geometry, while in case of 2 or 3 days, we will be having different view geometries. So both cases we have tested, and we found satisfactory result, both for the case of constant angle and the another case for the varying angle when we assisted with the BRDF function of vegetation. However, we see that with varying angle, there is little bit more scattered, but still uncertainty is within 20-25%. Similar case for the dry desert case. Here also the results are satisfying, but what we can see that that vegetation BRDF hypothesis is not well. However, if we introduce the surface type for BRDF assistance, better results may be achieved. So status as far as land is concerned, we both, CNES and ISRO is mutually agreed that both approach has to be merged together to have a better aerosol retrieval, which will lead to a better retrieval of surface reflectances. So this is one small study that we looked over how surface reflectance characterization can be improved by introducing surface type related mapping function. So here we have used average data, and what we see when we use the functions, these surface characterization functions, depending upon the greenness of the surface, that is the NDVI, we get a significant decrease in the errors between the characterized surface reflectance and the actual surface reflectance. So, our pre-launch work plan is to generate globally valid stable surface reflectance relationship utilizing centennial MSI data. And post-launch, during commission phase of 6 months, what we will be doing, we will be refining those spectral relationship with Trishna data itself and the ground measurement of ocean of atmosphere. So I request Emily to please take over or what is.
Thank you. Just a quick word on what we intend to do to make the atmospheric correction upon water for the visible bands. We propose to use the polymer algorithm, which is a spectral matching method based on a polynomial to model the spectral reflectance of the atmosphere and sunbeam with 3 parameters, and a water reflectance model with 2 parameters. Polymer uses all available spectral bands in the visibles and was applied successfully to MARIS, MODIS, Sentinel-2, Landsat 8, and the code is available at this address. So the application of polymer for Krishna faced 2 potential limitations of the visible instrument. The first potential limitation was will polymer be robust to radiometric noise? And a study conducted showed us that we observed a good robustness of polymer to actual radiometric noise. And the second potential limitation was the number of spectral bands, because we wonder if polymer will be successfully applicable in the presence of only 5 spectral bands not affected by absorptions, knowing that it needs 5 parameters to derive the surface reflectances. To make the performance study, we use Sentinel-2 data at 60 meters. And quickly, here are some results we got from the study of the applicability of polymer in Trishna case. On the small images, you can see the RGB composition, the reflectances calculated with polymer with all the information available for Sentinel-2 and using the classic polymer algorithm with 5 parameters. And on the third image, you can see the reflectance we calculated in the Trishna case. So with the use of only 5 bands and with a simplified polymer algorithm using only 4 parameters instead of 5. And on the graph, you can see the comparison of reflectances in the blue, green, and red bands calculated for the Sentinel-2 configuration with the complete polymer algorithm with 5 parameters, and in the Trishna case using a simplified polymer algorithm with 4 parameters. And what we can say from this study is that the simplified polymer model was satisfying and limits degradation due to the only 5 available bands we will have for Krishna. Then to conclude, the test we made for evaluating the polymer performances in Krishna case were made with a critical specification, and we will need to refresh the results with the visible instrument performances updates when they will be available. Thank you.
Thank you, Manoj and Emily. So now we move on to the next presentation. Mary, can you hear us?
Yes, I can hear you. Hopefully you can hear me.
Mary, is your presentation next for coastal SST?
Yes, I think you are going to drive the slides for me.
You have to present from your side. Can you?
Mary, can you share your presentation from your side?
I can try.
Do you want to share, or do you want us to share from here?
If you can share from there, that would be better, I think.
Okay.
I think Pradeep already had slides loaded. And if he could just advance the slides, that would be great. Just let me know when you are ready.
Mary, just wait a minute. We are trying to share the slide.
Yes, no problem.
Okay. Yes, can you see the slides now?
I think they're coming on my end. Wait, just yes, I'm able to see them now. Yeah. So I will go ahead and start if that's all right. Okay. My name is Dr. Mary Beth Neely. I am with Global Science and Technology. I am supporting NOAA. I am a representative of the coastal user community. Next slide, please. Yes. My co-authors on this are other members of CIOS Coast and the CIOS SST virtual constellations. Their names are listed there. They include folks in the audience such as Pradeep and Rashmi Sharma, but also important folks, Masako Kachi, who prepared the slides primarily, from JAXA, Krista Whittle from CSIR, and Ed Armstrong from NASA. Next slide, please. Next slide. Okay. I'm just waiting for the slide to change on my screen.
Yeah, I think the slide is getting delayed. It is already third slide. Are you able to see?
My screen's not changing, but I'll go ahead and address the third slide. So for anybody in the audience who is not familiar with the Committee on Earth Observation Satellites, it's where CIOS Coast and the SST-VC are found. The Committee on Earth Observation Satellites is the primary forum for international coordination of space-based Earth observation. They certainly want to focus on the ease of use, for the user community, but especially validating data and for the focus of this presentation, it would be data in the coastal areas. They also work to validate any requirements levied by the external organizations such as CGMS or any other group. There's 64 members, 5 working groups, 8 virtual constellations, and 5 other teams. And I'll move to the next slide. A priority within the SST virtual constellation and the group for high resolution surface temperature, or GRIST, sea surface temperature, has been improving the delivery of coastal SST to users. Certainly, GRIST was founded 25 years ago to promote state-of-the-art SST. Many satellite agencies already use GRIST interoperable data sets, but most especially I want to draw your attention to the 2022 GCAUS implementation plan priority, which is to develop and serve coastal data products such as temperature within 1 kilometer of coast, and to extend that within the estuaries and at the also at the exclusive economic zones. So we view this within coast and CEOS as an opportunity to work to support coastal users. There will be technical challenges such as in quality validation and availability, and we recognize that. I'm moving on to the next slide. Coastal SST observations were featured in a special session of the GRIST 25 meeting, which Isro, I think Rashmi even co-arranged that session. That was held July 14th in Montreal. There were many talks on SST, especially in the coastal region, and the challenges observed with those observations. We also had a panel discussion that was very fruitful to identify gaps in the coastal areas. One of the issues raised was the coastal coverage mask for existing and future ultra-high resolution instruments and sort of challenges bridging that gap. I'm moving to the next slide. For ultra-high resolution SST, there are already measurements out there, primarily from the EcoStress mission, but users absolutely want the high resolution SST of less than 100 meters. We recognize that there are challenges to bridging the gaps from the current traditional TIR sensors with the 750 to 1100 meter spatial resolution. SGLI on the GCOM currently serves 250 meters in the coastal areas. But then, of course, the new missions will have less than 100 meters. We need to serve all of that data to coastal users. We especially want to avoid masking within the new missions that would shut out either the coastal users or the open ocean users. That's the purpose of my talk today and my advocacy on behalf of users. I'm moving to the next slide. So in this image, we just want to end this slide. We just want to reiterate on behalf of coastal users our advocacy for increasing the coastal mask. It's not just the resolution that's an issue, but it's also spatial coverage. On the right-hand side of this slide, there is an image from EcoStress. I believe it's at the mouth of the Chesapeake Bay in the US. And it shows that surface eddy features are easily resolved within the EcoStress product. The same mask is proposed for Trishna, and we approve that. However, on the right-hand side of the image, you should be able, maybe faint to see, but you should be able to see a purple line and then a red line. The purple line represents the coastal masking proposed for the upcoming SBG mission, and the red line represents the LSTM masking. Both of those features, or both of those masking lines proposed would eliminate from our coastal realm the eddy features that are shown in the eco-stress image. Thus, we argue for at least 100 meter coastal mask. I'm switching to the next slide. This is my second to the last slide. Specifically, we realized that within CEOS that a one-size-fits-all approach for the coastal mask might not still be appropriate. We have convened several subject matter experts with the goal to identify perhaps a variable mask for the coastal SST, and that would be based upon 5 to 6 regional features. This is based on the outcomes realized from a not similar process for SST in the Sentinel-2 project. They have identified some areas where maybe even 50 meters of a coastal mask is enough. 50 kilometers of a coastal mask is enough. However, there are other areas maybe where they need to go several hundred kilometers out from the coastline. We strongly encourage future ultra-high resolution TIR missions to provide users at least that 100 kilometer mask. And we hope that by convening these subject matter experts and providing a more regionally tuned mask, that can be implemented as well. Thus, we recommend that Trishna, LSTM, and other future missions maintain that 100 kilometer from the coastline mask. We hope to offer a refined science-based recommendation in early 2025 as an outcome from the convened subject matter experts. And my last slide just offers anybody in the room or online the opportunity to be among those subject matter experts meeting coastally on the coastal SST masking analysis. You can reach out to me, and there's my email address. You can also reach out to Rashmi or Pradeep, and they can get us connected, and I'll add you. And that's the end. I'm happy to answer any questions. Thank you.
Thank you, Mary, and thank you for being awake so early in the morning. We know that it's too early for you in the US. We'll take questions. We have one more talk left, and after that, we will take question session. So please be with us for another 15-30 minutes. Thank you. Man, can you also join on the stage?
So we move from
propose different options which are written in the ATBD. For the day overland, we will use the Maya algorithm. Manoj talked about it. It's a multi-temporal and multispectral algorithm that is based on the fact that surface reflectancy changes slowly with time while atmosphere changes fast. And the multi-temporal methods and multispectral thresholds are used to detect clouds, cloud shadows, snow, and water. and to correct thin cirrus clouds. Over water, currently Maya is the preferred option during the day because it's already implemented, and we can't see no significant improvement for the different option we tested. We will only use the multispectral approach over water, consisting in whiteness criteria, cirrus criteria, is origin. Detection of clouds upon water. And we conjointly agreed that the night cloud masking is the priority topic. Oh, sorry. Manoj already showed you the result of this study. The question was how to avoid directional effects in the particular case of Trishna when we want to use Maya. Should we use the 8-day cycles with constant viewing angles, or should we implement a good directional correction to use all the images acquired by Trishna? So we tested the two scenarios on Sentinel-3 data, and we evaluate the performances on the retrieved aerosols and on the cloud mask quality. And you already seen that, but the conclusion was that it was satisfying in all sites we tested if we used variable angles and we considered all the images on unique temporal series, because if we do not do that, if we use only constant angles, we had too few images, and then we constate a loss in cloud mask quality. So let's move on to the night cloud maskings. It's currently under study, and we need to evaluate different masks. So what we did is that we implemented multiple masks, statistical masks based on the Bayesian theorem, using some statistics and over different images, and other machine learning algorithms, different one, ensemble models, linear models, non-linear models, and neural networks. To evaluate and implement these masks, we constructed handmade data sets to train and to validate the cloud masks. So we took eco-stress images to conduct the study. Then multiple areas were used with handmade masks labelization on 11 zones and 140 tiles. Different zone for training and tests. We try to cover all the landscape we will have to mask, and some other side for tests only. On the first images, you can see an example of the mask labelization we made on eco-stress image. And on the map, you can see the localization of the training and test tiles. So we try to cover all geographical areas, but it's still under progress. For the construction of the statistical lookup table and the machine learning training, we used the brightness temperatures in the 3 eco-stress channel centered at 8.5, 11, 12. We use also combinations between the brightest temperature of the different bands to add information. And we made a distinction between land and sea, because we want the best mask for land and for sea, and we're not sure we can use the same algorithm for the two. The results that are currently under study that we got 9 statistical or machine learning masks over 140 tiles. And we also made some thresholding proposition because we'd like to produce confident level mask and not a binary mask. And we can see here that the way we will threshold the different possibility will give of masking, so we will have to work on this thresholding as we have to work on the algorithm. And to conclude, so the first conclusion we have on these different masks overnight is that we can see no generic tendencies, but the Bayesian approach seems to give the best results. The cloud structures were well reproduced, and we really need to find the best definition of the different thresholding to produce that confident level mask to be useful for the users. The band combinations, the Bayesian mask with band combinations is available as a prototype and has a good level of maturity. And we will now have to extend our study. We need to complete our training data set with the addition of water scenes and extreme scenes. We will also add the altitude of the scene input, and we want to take into account the spatial information in the model. Also, we intend to adapt the night threshold, especially on particular night scenes, and we think of using SLSTR data to do so. Thank you.
So now we have 10 minutes for questions to the speakers. I don't know if there is, we have Jean-Philippe there, another there. The question is to Emily for the first presentation. And so I appreciate a lot that you quantify the error. And I have maybe a source of error that is not quantified as far as I understand, because you are using the database of Aster. And as far as I understand, it is a database of material. Okay, so a leaf, ground, things like this. And actually, with a satellite, you observe landscapes, so which is a combination, you're gonna smile, a three-dimensional combination of material, leaves, ground, and so on. And if instead of considering the emissivity of material, you were considering emissivity of landscape, so schematic landscapes, obviously. So this is my question. So obviously I can imagine that it is impossible to say what is the final error, but shouldn't it be interesting to test the kind of error you may have if instead of using emissivity of material, you were using emissivity of simulated landscapes?
Okay, so we made a lot of work of how to have the most comprehensive emissivity database. So at first we took emissivity from the EcoStress library and SAIL and emissivities coming from the same model that are a mix of materials emissivities. And we also worked on the Kemmer database, which is produced from acquisition of Modis and Aster and EcoStress, I think. And so it corresponds to landscape emissivities. And then I have a lot of results and different results, but I never compute the uncertainty linked to the spectral library, but it's a big work we are making with Albert also, and with a lot of people to have the most comprehensive and most representative emissivity database. So we have that in mind, and we worked on it.
What I wanted to mean is, for instance, with forests, you know what I do here. So with forests, for instance, we can compute the emissivity of forests. So I'm thinking about the emissivity of forests, the Rami forest. So Albert knows about this. And obviously, the emissivity changes a bit according to the architecture of the forest. So does it change enough in order to influence results, your results? This is something else. But I think it could be interesting to test it. So sorry, I am a bit advertising what I am doing. Okay.
So my question is regarding this SST to both of you. Okay, so both the SSTs that algorithm that you talked about, one definitely is using all the bands of Krishna, and this NLSST, basically it was for 2 bands and then you extended it for including the other bands as well. So is it true that, I mean, pre-launch, now both the algorithms will be there, and what is the kind of improvement that you're going to do in the pre-launch phase further to this? Or are these algorithms now frozen?
In the pre-launch phase, we agreed that we will keep the 2 approach because we cannot narrow down one from each other until now, but we keep on working on and gathering all the data set we can gather in order to evaluate the 2 algorithms in the most data we can have.
Yeah, because the statistics which were shown was definitely showing, a kind of differences, a bit of differences in terms of RMSE. But in the case of SST, specifically in the coastal region, what is important more than the accuracy is the kind of feature that it detects. So the feature detection is more, desirable from the practical usage point of view than the actual accuracy RMSE number. So I would suggest that pre-launch you can focus on assessment of these 2 algorithms from that point of view. Thank you.
My question is to SST retrieval team. We are working in ocean color. So actually, how far from the
On this, RL. So it depends upon the resolution also.
No. His question is the variability from the land to the last line of the coast, so about 100 kilometers. So what sort of gradient you can expect from the algorithm? That is exactly your question is.
No, so that depends on the actual observations. If the gradient is in the observation, the SST will also have that much gradient because algorithm directly use the observations, no, sir. So if you have the fine features in your observation like brightness, temperature, radiances in the Trishna, you will definitely have those fine features in the SST itself. So it will depend upon your observations also. We haven't
shelves.
Downscaling of the atmospheric parameters. But what about the directionality effect or maybe that kind of thing in your LST algorithm? How it will compare as compared to the plain land to the mountainous region? Because snow LST will be very important.
Yeah, we did not look especially on this zone now, but we might look at it.
I think this is one of the R&D challenges one should look at. And my suggestion will be that when both the algorithms will be compared with the common data sets, you can take up the different landscapes for that, so that we can arrive at the final some estimates of the landscape specific errors.
So various ecosystem and landscapes we have been doing tens and hundreds of data sets we have done. But as far as these orography or DEM effects and directionality, that is very, very challenging, and we'll look forward. We'll work on.
Yeah, I noticed that the nominal, the revisit where you'll always have the same angle as every 8 days, but you'll revisit the same spot every 3 days, just at a different set of angles. Do you think how do you think that's going to impact the LST retrieval?
Yeah, I don't think there will be an impact because we took the viewing angle in the atmospheric. When we want to compute the atmospheric parameters, we use the viewing angle, so it's taken into account, and then we made some tests on EcoSpace data, so with different viewing angle, and we cannot see any difference in the performances depending on the zenithal viewing angle. So I think it's taken into account in the atmospheric parameters, and then it won't impact the performances of the algorithm.
I have two questions, small, regarding that. One is regarding when you're testing your algorithm for LSC, you have two approaches. So you're also planning to test in the urban region, because in that case, emissivity changes very fast. And this is also a function of weather. If the weathering is happening, as surface emissivity of that rooftop is also changing a lot. So that is one important point. And second thing, you are working on this cloud algorithm. So thick cloud is very easy one, and you can do many statistical and machine learning. And you are also targeting some specific strategies for thin cloud, also for separation of thin cloud. So that is a sometimes very, very big task.
Yeah. We have a cirrus band in Trishna to detect the thin clouds, so it's taken into account in our algorithms.
And regarding this urban emissivity, because what we have visited a few days back, and in that we have seen that rooftop, because of weathering, emissivity has changed a lot of different materials.
Emissivity is very challenging.
Same algorithm for detecting cloud and fog?
For cloud and
fog?
Fog. Yeah, we have only one algorithm to do so.
Yeah, but there are differences.
Fog, but moisture will be moisture.
There are differences because mainly fog detection MIR is used.
Sir, actually, it is not like, as of now, this algorithm is not discriminating between the various kind of clouds. For example, as the previous question has been asked, thin clouds versus thick clouds. So in that way, as of now, there is no plan into the discrimination of the cloud types, whether it's a cloud phase or let's say cloud height wise. So right now it is just telling whether there is a cloud or not. Maybe it's a kind of a probabilistic or something. But fog is a specific kind of cloud. So flag will be there. There is a cloud, but it is not able to discriminate whether it's a low cloud or fog. So as of now, this is the status. Yes, it is just said that it is a cloudy pixel.
So we take a very last question from participant what I was patienting for a long time, please.
This is a similar questions only that related to this cloud masking and this aerosol and these corrections you are doing. So in many cases, thin cloud, as previously asked, that sometimes it is quality tagging is, I think it's important that what this particular pixel is, how far it is corrections is possible, or this particular pixel is there is some uncertainty in the quality of the pixel, so that the users can have a check on that this pixel has this quality, is quality wise there is no question, and there are some pixels, there are some these quality issues that like bodies, they have some kind of issues they have tagged, but after that users look into the low quality pixels and there are some kind of corrections we have implemented. There are a number of corrections you can do, particularly thin cloud is a big question that is a bit difficult to do that. So there are some kind of statistical analysis. Sometimes it's very useful. That is first. And the second question is related to the emissivity part, particularly where the NDVI is very low, particularly less than 0.2, for example. That NDVI THR model, what people used to do that, their emissivity spectra is very, very important. But this emissivity spectra for the soil or different kind of materials, that is again site specific. So what is the plan for this transformation for that? What kind of emissivity spectra we are going to have that we can use it for getting this emissivity for, particularly for less than 2 NDVI.
Yeah, I could not understand first question. It was very long question. I think towards cloud. Yeah. But as far as this emissivity retrieval is concerned, what strategy we have taken is, simultaneous retrieval of temperature and emissivity. And if you could have seen in the presentation as a retrieval for number of line cover from standard library and some of the field experiments, what we have done using FTIR measurements at our site. So those spectra we have tested theoretically, and with very good accuracy, we have been able to retrieve the emissivity spectra in shape, magnitude, and the patterns. So we just showed the collage of, I think, 16 land covers. Either it is from very featureless kind of, classes of water, and vegetation is also not featureless many times, but featureless to desert and some of the sand and clay kind of, features. It is basically giving us very good estimation. The conventional Aster based test method we have modified for testing convergence levels at some different, type, and that particular method is giving very, very nice, at least theoretical, as well as we could not show, but we have applied it on the images itself. So it is actually picking up the features, magnitude, and the shape of the emissivity.
Measurements are in situ measurements, or it is your samples you are collecting?
No. As was mentioned, collection of as our senior colleague was also mentioning, collection of various spectral libraries from Aster, SAIL, and some of field experiments, what we have done. Right. We have done a lot of experiments on the field of vegetation and some of the sand and mineral kind of things. So those are basically spectral library right now for tuning the model. But as mentioned, and there are many questions that in real life problems, the emissivity, either it is rooftop, various urban types, it is one of the most challenging, it is going to be one of the most challenging types. And you could see some of the RMSE values which we are getting. The worst retrieval or not worst retrieval means not that great retrievals on urban features itself. So it is expected. So we are going to work on fine tuning probably on some of those very challenging targets as well in future. Thank you.
First question is quality tagging. Maybe you can, yeah, that is what.
I understood your question. I just repeating if I understood properly. You are concerned about the uncertainty for each pixel retrieval. Say, for example, yes, you rightly said, say, for example, the case of aerosol optical depth, when I said that there is an uncertainty of 25%, it is not true for all pixels. See, for heavy aerosol loading, uncertainty may be much higher, or it may vary with the value of aerosol optical depth. So when we say 25% is a statistical number, but yes, when L2 will be generated, this uncertainty has been taken care of. We will be generating uncertainty parameters. As you said that in MODIS, say for example, quality factor for aerosol retrieval 1, 2, 3, 4 are provided. So the same thing that can generate it from the uncertainty layer itself. Okay, but we will be providing the number uncertainty number. So you will be having the specific number. What is the uncertainty in this particular AOD retrieval? That may be used in the same way you are using for MODIS.
Thank you.
Thank you very much to all the speakers and for the quality of the presentations and also keeping your time. So with that, we can conclude the session and we'll propose to give a last round of applause for all of them.
So thank you on behalf of now I would like to call Jean-Louis. Thank you, everyone. We will assemble here in the same hall for next session. Next and last session. Please be here in 15 minutes.
Hello, mic check. Hello, mic check.
And we have a diffuse also component, which weight this tooth albedo, which is a fraction, which is a function actually of aerosol optical depth. That could be come from Trishna, for instance. So we have definition, or either from CAMS. So we discussed this aerosol in the previous presentation, so I don't want to go into too many details. So what's interesting is it actually next one, yeah. So actually the approach we consider, we talk already of BRDF. That's quite a considered approach that I use for many products in MODIS when we can decompose the BRDF in series of kernels. Là, I only show kernel for snow-free situation. There will be some presentation about snow during my letter by Dr. Singh and my talk that we explain, say a little bit about snow situation. And you say that we can decompose this signal in the three components: Lambertian, geometric effects, and volume scattering effects. And this works for any bands, or will be applied for any band of Trishna. Next. So I said the algorithm is quite solid. Was applied to map albedo from probably in the frame of Copernicus Global Dam Service. We did perform an interesting comparison with MODIS, that was published in 2018, and 300 meter resolution. And now also we have a project with Sentinel-2 with 10 meter resolution. We also applied after some adaptation the same algorithm at 10 meter resolution with different tiles over France. And you see that example for some prairies. You can see on bottom right that we get a pretty good comparison. So we have between a 10 meter resolution and 300 meter resolution, we have Trishna 60 meter resolution. So we are quite confident to have a method that will be quite successful to map albedo from Trishna to answer to meet the expectation of the users. Next. So that does it work for albedo. So of course we don't want to have gaps. So we try to have gap filling algorithm. So we don't start from scratch. We can priori information and recurrent algorithm. So we update every time we have an information. We update the system. So we have composite period and we have synthesis period. And so we have what we call a priori variance covariance matrix that tell you about the quality of the fit for the model. And then after that, we are able to propagate in time the albedo consistently to have consistent time series continuously with no gap. Next. Okay, now I will move to the next part of my talk, that's about directionality. What we have with Trishna, because decision to have Trishna orbit in the middle of the day, from March to October in the tropics, we have some what called hotspot effect. Next. So hotspot effect, you can see, I mean, this is kind of maximum of reflectance you can see from your eyes in the visible. If you fly, sometimes you have also from flying, you can see the shadow of the aircraft, and there is a big halo around the brightness, around the shadow. Because you have the on-sunlit area, you don't see any shadow. So that's the maximum of a peak of reflectance. And this is well characterized by the cosine of scattering angle. And what you see in the visible also exists in the temperature. So you have a peak in the temperature. Next. Yeah. And we did perform some numerical experiment with scope, for instance, and we found out that we have about 7 degree K of amplitude due to hotspot with scope. So it's quite significant. So we think that we should care of that for Trishna, of course, because that will be a significant signature. Next. So the approach is quite similar. We have from albedo. We have actually, we can decompose the thermal the LST in some kernels. One kernel will be for directional emissivity. The other one will be for hotspot. And the question is about the scaling issue. So we know that it works at core scale, but which we get of Trishna is still to be found. But we're working to prepare it with working with different strategy. Next one. So this is a simulation for orbit path from Trishna. So the 12 go from top left to bottom is from January to December. So when you have the red part, it means you have in the hotspot zone, and the green point that you see, that will be will be actually the Trishna observation. So you see actually when you have in the red, you will be in the hotspot. So I mean, due to our cloudiness, we have actually to consider even hotspot, and we to correct for the hotspot. That's pretty clear. And next, yeah. So we have two strategies so far. We can either correct for the hotspot bring a correction, or we can discard data. That's not pretty clear so far. We need to define a kind of zone around the hotspot to figure out what we're going to do with that and if we can correct. And next. Okay, and so yeah, clear data with, you can go next. Okay, so to work with the hotspot, we start a different scale. We have a ground-based camera measuring hotspot for deployment for different sites station, but also we work with Meteosat because at the Equinox with Meteosat, actually you can observe hotspot and it goes very quickly around noon time, and this is what you can see in white. So when you go to one, you are really the hotspot. So we explore the hotspot for Meteosat, even if it's a cost footprint of different kilometers, but still it's allowed to sample many ecosystem that's located in the Meteosat disk. Next. So, and the other beauty of that, actually, is we have two Meteosat. At the same time, we have two land surface temperature with different angles. This is what we explored at the equator and wanted to know at the difference of that. And next. And so, of course, we were trying to pick up to select data in the hotspot. So this is a DTC. This is DNA temperature cycle. Also for DNA cycle of the reflectance, you can see some peak. So there is band in the visible band in the thermal. You can see some peak in the visible that tell you that we are in the hotspot. And you don't really see it so much in the, it's not so evident in the obvious in the thermal. But if you look at the difference, like on the top right graph, you see the different temperature of the two satellites. So the temperature is very concomitant. Just the only difference, same atmosphere, same pixel, everything. The only difference is the angle. You see that you can have a difference by 4K easily just due to the angle. So that's interesting. So and you see actually that the more important difference occur in the middle of the day, which is not necessarily good news for Trishna. But okay, otherwise we get, so we try to understand the process of that because you have different peaks. You have the peak, solar peak of radiation in the middle of the day. You have peak of the satellite due to the spot, and you have some peak due to thermal inertia of the surface that emits with a certain time. So we try, that's the reason we study DTC, even we don't have DTC with Trishna, because we try to understand the whole processes. So next one. Okay, so I say we work with coarse resolution from satellite. We also have a strategy of deployment of ground-based camera on different stations. And if you go on Guyane, you can see there is a peak hotspot. We were able to capture the hotspot in the thermal, and it's about 6-8 degree K easily. So it's just confirmed the numerical experiment from scope model, for instance. We work with Otherville. We built up some mockup, also 3D modeling of nice crop. That's interesting. With the mockup, you can play with that. You can simulate the shaded part of the canopies and the part. And nicely, last year we start that really define our formal collaboration with Isro. We have a confidence site, a paddy rice site near to the south of here, or Ahmedabad in Navagam. So we set up thermal camera, and we did measure during all the growing season the temperature of this crop, of this crop. So you can see a bit the different temperature between the water and the rice. And so we have moving camera to capture the BRDF. We couldn't find any hotspot for the rice in this case, but we found interesting things anyway. So, and you see we have this system in India, and now it was moved to Malegaon near Bombay. See, because we need we need to learn more about the directional effects for different kind of covers. Next. Okay, so this is albedo. This is a flowchart describe how we're going to map albedo. So okay, so we start from geometry. We have a DEM. So we consider slope and aspect as particularly interesting on the relief when we have snow, and you have some presentation about that. We can go as the kernel section kernel can rely on land cover land use classification. We use a priori information. And I say we use black sky, white sky albedo. We make a ponderation of them, and we go black sky albedo. That's a flowchart workflow for algorithm. Next. Okay, so now actually, so this tell you actually the expectation for albedo to meet, to meet the objectives of the end user. So we expect that come from CEOs. Actually, ICO LPVs, it's about 5% of accuracy and 1% of ability. Next. Okay. Yeah, I leave the floor to Dr. Singh.
Thank you, Dr. John Lewis. Okay, so actually, when we were planning to work out on this albedo product, so it was like to develop the kernel function for different isotropic, volumetric, and geometrical conditions. Then it was likely for this non-snow target. But our interest grows because of this Himalayan region. A major portion is covered with the snow, and which is highly seasonal, showing the highly seasonal variability as we move from winter to summer. So what happened that we worked out on this jointly agreed ATBT that we can include the snow land cover as a feature, to take it as a challenge and to work out this albedo product over that target. And why it is important here to show that when we talk about this snow related feature, and where this cryosphere is also an important component over Trishna mission, and we will be working on different aspect of cryosphere related product. So this will be an add-on or integrate the information to understand that dynamics in a better way. So if you see this top left image, it is with respect to the grain size, and you can see that when the grain size are changing, it is showing the highly variability. And if you come down, then you can see the black dot, and which is a outcome of experimental data set where we have used the soil and the black carbon as a contaminant, and you can see that how it is influencing the reflectivity over snow. So it is making an important target. And if you see one scatter plot, the snow cover area and LST, so where we have used more than a decadal data set of LST in three major river sub-basins of Indian Himalaya, Indus, Ganga, and Brahmaputra, and you can see the temperature and snow cover amount is showing a correlation with that, and where we are having the high temperature conditions, the snow cover is low. And as the type is also changing because we are having the different LST in that part. The right, the albedo and temperature, where it is a long-term observations using this in situ data, where you can see that as the temperature is rising over that observatory, there is a decrease observed in the albedo, which could be either because of the contamination or because of the snow metamorphism processes, which affects the grain size over that region. And why we need to go for high resolution temperature information, because when we talk about this dynamics at the sub-basin scale, then you can see that how much additional information which we may get, which is not possible if we use modest type of sensor. Next, please. And why that topographic consideration is important, there is one exercise which we have carried out using this AWIFS data. The top left image shows the snow cover subbasins in Indian Himalaya. The down image shows that DM. The center image shows that the illumination geometric interaction when with solar zenith angle, and the viewing geometry with varying with the slope of a target. The right side top image is the reflectance before the topographic normalization. And in this analysis, we performed slope matching aspect, where we have used this north and south DM aspect and the slope angle information. And the downside image, you can see that it has the image which are showing the brighter part. They have been normalized to the lighter one, and where in the north slope facing regions, it has been slightly showing the higher energy. So that means that the topographic normalization is an important element when we are talking about this albedo. However, it will be taken care by the working out on the kernels, but this is just to show that how this normalization can influence the reflectivity over the snow-covered basin. Next, please. Okay, so this is one experiment which we have carried out over the snow, where we have used the spectroradiometer in different aspect and the changing angles. we couldn't carry the goniometer, so we have designed one different sort of experiment with the availability of a logistic facility. Next, please. So this is the left image just to show that the different aspect, how they are changing the reflectivity when we are changing the angle of observations. And right image shows that at the same angle, how the different aspect can influence the reflectivity over the snow target. So this shows that why we need to consider the different kernel function when we will be talking about the albedo product retrieval over the snow surface. Next, please. And apart from developing a different kernel function, we also need to validate our product. And we have chosen different sites, which include the agriculture, forest, desert. But I will just emphasize here on snow because the other side will be discussed in the different presentation. So the one thing will be like the inter-sensor comparison. The installation of different met stations in higher Himalayas, and this is one more difficulty because the installation is difficult and maintenance is much more difficult of such type of met stations in the higher altitude. But like I will be showing one slide. Okay, next. But before that, we will be in validation strategy. We will be following the approach which has been developed by Dr. Jean Louis to assess the quality of our product. Next image. Okay, so this is just to share one met station which has been installed in the Jhaskar sub-basin at Drang Glacier, and the lower right panel you can see that it is showing the albedo variability in that region of February month, and because this time it is completely covered with snow, you can see that albedo is almost reaching 75 to 80% of that. Next, please. Okay, so I now request Dr. Jean Louis to conclude that.
Yes, rapidly just to end this talk to conclusion. So we, of course, we try to cross-compare different methods over India as per mandatory. I'm talking about radiation product, especially for cloudy sky net radiation. Of course, we need to have Calval site in mountain area. That's pretty clear for the presentation of Dr. Singh. We need to estimate the daily radiation that we come from geostationary because we are only instantaneous measurement from Trishna. Albedo, so albedo is quite mature. We agree ITBD very quickly, so it's really we are confident in this product. Except we also need to consider snow kernel to add into that, and maybe also to refine the DM because to improve the accuracy of albedo assessment over topography. We have identified some sites when we could have quick delivery of albedo in India, but also in France, in Europe. Directionality is more complicated. We still need to do some ground measurements, different. The more, I mean, acquire more information even from 1D model or 3D model like DART, especially for the analysis cycle of the temperature. And okay, we need also collaborate with space agency, especially I tell you so this morning there is some air campaign, airborne campaign. We try to capture the directionality of the different crops in Europe and also next year. So actually, and so scaling issue. So scaling issue may be something we probably have to learn after lunch because few meter resolution, few kilometer resolution, different story, and between is not like optical thermal, is more complicated. Anyway, so that's the end of my talk. Thank you.
We can have one short question now if you want. No question now. Okay, so I guess you keep them for the end of the session. So next presentation. Yeah, sure. Go ahead, Bima.
So it's for how we were planning to incorporate the orographic effect
Actually, same was the question in the last session also. So in the BRDF or in the even directionality effect also, you are incorporating the topographic effect, especially in the mountainous region.
I mean, we know, I mean, mathematically, we know how to do it because we've done it for the project. Can you, yeah.
Yeah.
Yes, maybe better, sorry. So technically, we know how to do that because we did before for Metosat, for instance, for the other project with the DM. So we need to consider this. Question when we are going to do it, maybe that's your question. And so I think this meeting is perfect because we need to we need to agree in many ways in different things. And we spent time for Albedo. It started about 2 years ago. We had the first meeting, and even if we convert very quickly on the algorithm and in many ways and the flowchart, but still so I think this is something we meant to do, and the snow kernel is to discuss also. I mean, we have some ideas, that's no problem. So we try to do that. The sooner the better, but that's a matter of discussion with Dr. Singh to do that, I think. But we know how to do it, you just have to do it.
Thank you.
I mean, you mean the link between Sentinel-2 and geostationary satellite?
Algorithm, you are using geostationary satellites data, right? Meteosat Severi. So there'll be coarser resolution.
For which product?
For the product of what you just now told about AOD, that albedo you told, reference albedo.
So albedo.
Slide I could read that the reference albedo is taken from geostationary satellites.
No. Okay, no. I mean, albedo, no, we don't.
Okay, fine.
Yeah, but it's for radiation, it's for albedo.
So thank you. We can move to the next presentation. So the presentation was prepared by Marie Weiss from INRAE and Anand Shahadevan from SAC. And Marie, unfortunately, is not available, and Anand kindly accepted to make the presentation in the name of them both. So thank you, and the floor is yours. It's about the generation of vegetation variables for Trishna.
Thank you. Good evening, everyone. It's a pleasure to be here to discuss the updates on vegetation variable products from Trishna. This specifically from VNIR sensor. And this is a team member from INRAE and Isro. And I'll try to cut short my presentation because of the time constraints. And these are the vegetation variables we are targeting. Effective green area index, FAPAR, that is a fraction of absorbed photosynthetically active radiation, then green fraction. So these are the three major climatically important variables we are targeting in this vegetation variable product. And the major objectives, generate vegetation products that contribute to accurate estimation of the evapotranspiration from Trishna without auxiliary information. That's the major point. The second one is we try to provide a globally applicable, flexible and scalable algorithm. That means if we want to improve the model later on using more parameters, we should be able to incorporate it, and we should be able to scale the model. Finally, and it should rely on the existing validated state-of-the-art model. And this model, actually, the baseline model is already available in Snap Toolbox, and it's developed by this INRAE team from France. And we have some, we are trying to improve the accuracy of the model using some extra considerations of our forest and some other targets. And this is, here we consider 1D radiative transfer model. This is prospects plus sale model for generating the synthetic data. And we are not considering the 3D RTM model majorly because of the lack of 3D mockups of different ecosystems or different trees or agricultural crops available. So that is why we consider 1D radiative transfer model. And we consider hybrid model. That means we have two major parts here. One is the forward modeling, and the second one is the inversion using the machine learning. In forward modeling, we are using the process model. Means all the parameters in the process model, we are actually considering a range of values, and that range comes from some database. And we are simulating vegetation spectra based on this set of parameters. So finally, you will have a set of parameters as well as a database of the corresponding vegetation spectra. Then from the vegetation spectra, we finally estimate the leaf area index, FAPAR, and green fraction. And the advantage of the proposed model is globally applicable in the state-of-the-art algorithm, because already it's an operational model available in Snap as well as the Sentinel processor. And the RTM model, that is the 1D model, and the training datasets can be modified in future. Means if there is any improvement in the model, we can incorporate in this particular algorithm. The major improvement happened in this particular model development is, you can see this green it's okay. So this green, the green bars you can see here, that is the previous algorithm, the range of the parameters they used. And now this the violet color that indicates the updated parameter range. So that it comes from the TRI database. TRI means it's a vegetation tree database. So it covers different vegetation types. So we consider the different parameter ranges from that particular database. So what we are expecting is that will be a good representation of the different vegetation types available over the entire globe. So that way we can improve the accuracy of the algorithm. Then the strategy for ground data collection. So sampling side, we consider this different land use land covers, crop types and forest types. And even India, we identified the sites even considering the cloud cover. Then plot size here, sorry. Here, the spatial resolution of the sensor is 60 meter. So we consider 3 times the spatial resolution of the sensor, that is 180 meter, for establishing the permanent plots, for collecting this vegetation variable parameters. And this availability of the sites, we have permanent sites at different places in India. Specifically, we have collected, we have established these sites for a NICER CalVal program. And we have some other agricultural sites identified across in the entire subcontinent that I will show in the next slide. Then these are the ground measurements we are planning, and we are already taking the data. And from CNES side, they already have a good database of different parameters. So finally, we will be combining all these ground measurements for validation of this particular product. In this database, the major improvement in the database is like, for example, the major part is like the background of the vegetation, that means the soil types. So for example, if the leaf area index is low, vegetation soil brightness has a major role in the vegetation spectra. So to accommodate that in the algorithm, what we have done is we are planning to incorporate this open soil spectral library. So that covers the different soil spectra from different part of the world. And that way we will have a very good representation of soil types as well as vegetation types in the database. And this is a validation Dr. Mary and the team have performed with this modified algorithm. And you can see the improvement in the this NDVI against this LA values here, and it shows the better consistency in the relationship. On the right side, you can see the observed versus predicted LA, and there is a small deviation you can see at the top side. That is because of the some error in the, not error actually, because when we consider the planned area index, that means the entire planned area over the surface area and the green area over the surface area, these are different. So for example, in this measurement, what they have done is they have taken some measurements at the later stage of the wheat crop, and some of the measurements they have taken the flowering stage of the rapeseed crop. So what happened was the green component was less. So that is why that error was there in the particular outcome. And this is the validation of a forest. And still we are considering the some improvement in this incorporating the the variability of the forest spectra. And this is the one study, recent study. The results from the recent study published in the remote sensing of environment using this baseline algorithm. And you can see like a promising result, but still improvements are there is required. But you can see that square is around 0.70 over forest with the just Procel model, just using the Procel model. So it's like an encouraging result. So with this, we are planning to add more vegetation spectra from Indian forests as well as Indian forest species, and we are trying to generate some more results over Indian subcontinent. And this is a study from we have done using the Prisma data. So we have collected temporal Prisma images, that is hyperspectral images, over Surendranagar region in Gujarat district in India. Here you can see 3 images, one in January, then February and March. This is like you can see the phenological changes in this entire images. So it's an interesting observation. And what we have done is we have resampled the Prisma images using the Trishna bands, that is 550, 650, 850 nanometer and 1610 nanometer. Then we have actually generated LUT samples around 10,000. Then we have used that neural network model for doing the inversion. You can see clearly, you can see that January, that means in India, specifically this region, January is the, you can see that crops will be in the early stage, and February it will be almost in the middle stage, and March it will be in the harvesting stage. And that variation in the leaf area index, you can clearly see that in the bottom picture. So that indicates that this model can capture the dynamics of leaf area index throughout the phenological season. And this is the proposed validation sites in India. These are the agricultural sites, 10 agricultural sites. And you can see that it covers most of the major crops. And the right side, you can see the different forest types. That is major 6 plots we have, sites we have identified. Out of that, 3 are from the nicer sites. And we have good observations like LiDAR observations, 2 centimeter accuracy, spatial resolution radar observation over these sites. And this is like 100 by 100 meter, like in F2, you have 100 by 100 meter, 10 plots are available. Like that, we have 30 plots in 3 different nicer calibration sites. And it covers different forest types also. And these are the validation strategy before launch we are planning. And And we are planning to use Prisma data as well as Nmap data for the simulation studies, because right now, the major issue is like Sentinel-2 bands and the Trishna bands, it is not matching properly. So that's why we have to simulate the Trishna data from Prisma or Nmap. Then we are also planning to use EMI data for this same simulation studies. And ICOS network data also actually, CNESTN will be using for the validation purpose from France. And the future plans. So what we have understood that over forest, still we need some improvements. So because ProSail model cannot actually represent the entire complexity of the forest structure. And even, so that's why we found the info model, because info model can actually consider the leaf area from this multiple layers canopy. So that's why we try to incorporate one-dimensional info model for improving the accuracy over forest, but still we feel like that may not be sufficient. Finally, if we will be trying to use some results from DART model also, but if the info model performance is it's enough for achieving the the required uncertainty, then we will not be using this DART model. Otherwise, we are thinking that info model may be a useful model for achieving this particular accuracy. And finally, one more thing is like in India, we have lots of rice fields. Their standing water is available. So such kind of scenario was not available in this baseline Sentinel baseline vegetation variable model. So we will be using a SAIL SAIL model, which consider this water background also for simulating this rice scenario. So these refinements will be incorporated in the version 2 of the ATBD algorithm. Thank you.
Any question for Anand?
Can you? Yeah. Actually, I have two questions. I have simple question and less simple question. I come first with a simple question. So you show some confidence site over India. I'm just curious to know if there is some common Calwell site for albedo and vegetation parameters, because consistency is quite important for that.
Yeah. Actually, we have some nicer calibration sites or established sites, permanent sites in India. And agriculture sites, actually, it's not permanent, but we are planning to establish some permanent sites also for agricultural observations.
And you do measure albedo on this site?
No, right now, I don't have idea about albedo.
Targeting agriculture and forest. In few locations in agriculture and forest, we are targeting that LAI and vegetation fraction and albedo can be measured simultaneously, but not for all sites which are Anand showed, because in some sites there is we will not do continuous measurements. So in that we are planning to do some interval-based measurement we can possible to do, and then we will do, because we need more and more database for different land use land cover. So in that manner we can go, but still we have chosen near about 5 to 6 sites where we have a leaf area index measurements as well as albedo measurements.
Okay, that's important because consistency check between albedo and vegetation is paramount for application. Now I come to the less simple question. So you mentioned that effective green area index. What we need is a true green area index, so we need to correct for clumping. And
clumping, yes.
So, and do you have any strategy or idea how to do that?
Actually, if you use the DART model, you can have a better accuracy actually. But the major problem is how many such kind of scenes you can generate to improve this accuracy of the algorithm. That is a major question because it's very complex. And you need to have the mock-up of almost all type of crops and for tree types. That is almost impossible to do that. So that is why there may be, it's a trade-off kind of thing. So actually we are discussing about that. We'll come up with some solutions. Yeah.
Yeah, I mean, so we have global map of LA of green, effective and not necessarily clumping.
Yeah.
Okay.
Yeah.
Okay.
Yes, yes.
So we need to discuss because there was some strategy to retrieve clumping for BRDF.
Okay.
So we need to
Yeah. We'll
that.
discuss.
Okay.
Thank you.
Thank you. So now we welcome Ashwin Gujrati from SAC. He's going to present machine learning-based atmospheric correction of tier data for land surface temperature retrieval. You have 15 minutes?
Yes. Okay. Greetings, everyone present here and present online. Today I will be presenting on machine learning-based atmospheric correction of thermal data for land surface temperature retrieval. With me, our team members are Mehul Pandya, Dheeraj Shah, Jalpesh, Disha, and Himanshu Trivedi from academias. So as we all know that land surface temperature is very crucial for understanding various temperature, various processes like energy balance, climate change, and ecological dynamics. And various algorithms have been also been developed and been discussed also for LST retrieval. And the major retrieval algorithms included the equations as shown in the right hand side, where the surface unknowns are the emissivity and the surface temperature, whereas the atmospheric unknowns are L up, L down, and the transmittance in the equation shown. So Trishna, with having the spectral channels of 8.65, 9, 10.6, and 11.6, has great potential for simultaneous retrieval of LST and LSCV. But in the multi-channel LST retrieval, it requires atmospheric corrections as a prerequisite steps for the LST retrieval. So there are multiple algorithms for simultaneous retrieval of LST and LSC, which can be classified into multiple approaches like empirical or physics-based methods, single channel, split channels, and multi-channel approaches, single or multi-loop measurements, retrieval with known and unknown surface emissivities, and known and unknown atmospheres. So in case of Trishna, we will be trying to retrieve LST with the unknown atmospheres. And in these cases, the machine learning algorithms will come into the picture. So with as we know that many atmospheric correction uses auxiliary atmospheric profiles and run pixel by pixel additive transfer models for retrieving atmospheric correction gradients. So as we also know this is one of the approach in retrieving atmospheric corrections for the Trishna. But Trishna with simultaneous observations in multi-band optical and thermal can provide a coherent information of the atmosphere. So with this as the major thrust for doing this study, we have our objective to develop a machine learning based simplified atmospheric correction, which is SAC scheme for utilizing LST retrieval for multi-thermal infrared observations. The overall approach of the SAC algorithms is like this. We have an RT simulations, pre-run RT simulations with inclusive of emissivity spectra, LST ranges, atmospheric profiles, sensor spectral response functions, and view zenith angles. We do multiple large number of RT simulations to retrieve the atmospheric terms and the surface temperatures as the training data sets. While in the operational terms, we will have the satellite observed TOA radiances, view zenith angle, and the auxiliary total columnar water vapor from the atmospheric profiles or from the auxiliary input from the visible channels. And we will be using this in the machine learning models to calculate the surface living in and downwelling radiance terms, which goes as a direct input for the TES algorithms. And with the TES algorithms, we will be able to calculate the simultaneously LST and LSC values. The simplified atmospheric correction scheme or the SAC schemes, which I'm mostly focusing for this papers, has a pre-run atmospheric radiative transfer models with atmospheric profile, surface parameters, and view zenith angles, and calculated the total radiance, transmittance, path thermal, and uses the spectral response function to calculate Trishna simulated TOA radiances. With input of view zenith angle and total columnar water vapor, we uses these three inputs as the input layers, use and fully connected neural network based models to calculate the output radiances at surface living radiance and the downwelling radiances. So For the radiator transfer simulations, we collected large number of seaboard profiles, atmospheric profiles, and divided the whole profiles into 13 different sets based upon the water vapor content and the LST values or the bottom layer temperatures. Its graph been shown later in the downs, and we made many variations in the boundary layer temperature as well as the columnar water vapor and the view zenith angle to calculate real world scenarios. So we changes the boundary layer temperature to -5 to +5 within 5 Kelvin interval. And as we move to a higher boundary layer temperature, the variations was further increased from -10 to +20 Kelvin. Also, for the columnar water vapor, also for a lower temperature, we had the variations from 0.1 to 1, whereas for the higher, we go up to 6.3 with a constant view zenith variations of 0, 20, 30, 40, 35, 40, and 45 variations. And total 3.65 million simulations were being performed. And then we did our forward radiative transfer modeling using MOTRAN. So MOTRAN is a comprehensive atmospheric radiative transfer model widely used for simulating atmospheric transmittance, radiance, and irradiance for wavelength ranges from ultraviolet to thermal radiations. And as shown in the images, the graphs with change in the total columnar water vapors, the radiances changes. And it also depends upon the boundary layer temperature. So as for a lower boundary layer temperature, with increases in columnar water vapor, the radiances increases. But for a higher temperature, the increasing water vapors turns out to be giving higher total transmittance values and reducing the total radiances. And this is the graph showing the total transmittance values in different Trishna channels. So while training the machine learning models, we had multiple approaches going on. The first model was to calculate the path thermal and total transmittance, as they were the one key inputs in the transmittance terms. So we first tried that, then we didn't get the good accuracies. So we further moved to retrieving path thermal and land leaving radiance, which again was not very satisfactory. And finally, we converged to calculation of directly using land leaving and downwelling radiances. So as the TS has the input variables of land leaving and downwelling sky radiances as a direct input, we found that this gives us the best accuracy of among the models. And we also trained multiple models like linear regression model, regression trees, support vector machines, Gaussian progressions, kernel-based approximation, assembled tree, and neural networks. And what we found the most stable algorithm was the multi-layered neural network with fully connected hidden neurons with ReLU activations. So to further tune our machine learning models, we did these exercises with multiple number of hidden layers and increasing the size of the neurons also, with single layer with 32 neurons, 64 neurons, with double layer 64, 32, triple, 4, and we increases the neurons to get the best RMSE values. And we also changed the activation functions like ReLU, Leaky ReLU, soft plus, tan H. We also changed the epochs, mini batch sizes, and optimization of stochastic gradient descent based models, Adams optimization, and further. And this is our final results which we get using RT simulation results. We had very good accuracies in cases of surface living radiance for all 4 channels. The RMSE was less than 0.07 for across all the channels, with R square greater than 0.9 and across all the bands also. Similarly, for downwelling radiances, the RMSE was approximately 1.2 to 1.9 for different bands, with again R square values for greater than 0.9 in every cases. So these are the overall results which we have. We can easily see the bias is also very minimum with values up to order of 3rd decimal places. We also did the sensitivity analysis with changing of the total columnar water vapor as the noise added. So we add up the noise up to the 10% in total columnar water vapor, which shows the with increasing noise in columnar water vapor, we get an increasing RMSE values for surface living radiances, but it's for downwelling radiance, it has an increasing RMSE values, but for surface living radiances, the bias and the RMSEs are quite constant with a sudden jump in increasing noise at the initial levels. Finally, when we tried to add up our SAC module with the test module and retrieve the accuracies, so here is the comparison of ECO's test product with the SAC test LST product. So machine learning based atmospheric correction retrieval is not limited to Trishna, but the application can be used for upcoming Isro missions like GISAT and existing multi-bands eco-stress data. So the product here is between the eco-stress and the LST, and we can see we have a good RMSE with approximately 0.7 Kelvin. And we also did the exercises on multiple land cover types, and here also with low temperatures over snow and glaciers of approximately 265 Kelvin to deserts and urban regions approximately 340 Kelvin. The overall RMSE was less than 1 Kelvin, which is the requirement of the Trishna mission. To conclude, the machine learning algorithm developed at SAC for atmospheric correction, corrected radiance retrieved promising results with minimal inputs. These methods shows very high accuracy in retrieving surface leaving radiances and fairly good in downwelling radiances. But as we know, the TS algorithm is more sensitive to surface leaving. Therefore, this method yields very good LST retrievals. And the training approach is also general and hence can be implemented to various missions like Trishna, GISAT 1A, based upon the individual trainings upon the datasets which we have. So in GISAT, we will be having 6 channels thermal datasets. So probably the retrieval accuracies of surface leaving and downwelling gradients will further increases. And as a part of the future studies, additional of other atmospheric profiles inputs may likely improve the retrieval accuracies. So one of the suggestions from the Kenneth side was to include the temperature of the atmosphere. So we are trying to incorporate how we can incorporate the columnar temperature as one input values through our models. Further, the sensitivity to the input total columnar water vapor needs to be examined and rectified. As we see, there was a sudden jump in initial LST retrieval values. And finally, the training of other complicated machine learnings can be incorporated in retrieval accuracies. But at present, the simplified atmospheric correction with simple neural networks has also resulted us very good accuracies with LST retrieval less than 1 Kelvin, which is the requirement of the Trishna missions. So we are okay with that, but we are further trying to improve our models in further iterations of our projects. Thank you. Any questions?
Thank you. We have time for a couple of questions.
So there at the back. Ujjwal.
Just some 1 or 2 questions. Have you tried batch normalization in your network?
Batch normalization was already is a part of the training datasets. So we use that k-fold batch normalization during the training datasets while dividing the datasets. We had large number of simulations. We have reduced while training. We use that. Yes.
Okay. And you have used RMSE as your metric.
Yes.
There are other metrics like MAP. Don't you think MAP would be better?
In case of LST retrieval, RMSE is generally the measures which we take. But yes, mean absolute percentage error could be also been taken because we have seen for higher LST values, the inaccuracies in the temperature retrieval are large, but for lower it has low. So yes, that could be used. But overall, the project requirement is based upon the RMSE retrieval in LST. So we have stuck up to the requirements of the missions.
Good work. Keep it up.
Thank you, sir.
So can we use meteorological satellite data like INSAT or other Himawari in like predicting the atmosphere so as to correct for LST and SST?
Any atmospheric profile inputs could be useful for corrections but INSAT is only localized to Indian regions. But the Trishna is a global mission, so we must be having an synchronous atmospheric profiles for every part of the world. So this is not feasible as an operational product. But yes, for Indian profiles, we could probably use that.
Because you mentioned atmosphere profile you want. So that you get from meteorological satellite, even though at a coarser resolution.
Yes, they are a course. So the other, the model data is also available at 0.25 degree cross 0.25 degrees. So anything better than that would be really would helpful in retrieving inaccurate atmospheric profiles and in terms of better LST values.
One question from my side, just a basic query. We have been using RT model since very long time for this atmospheric correction, etc. So there are so many sensitive parameters in machine learning. Which is the most sensitive parameter? I mean the temperature. Whatever you are getting in RT model, the same you are getting. Like
as shown in the scatter plot, the retrieval accuracy was very high for surface
accuracy
and
is
for
okay.
downwelling.
Accuracy is
Yes.
very high. Usually all the machine learning, neural network, or this multi-layer you have used, they show above 0.99, above 0.9596. Only thing is that which parameter is most sensitive? Are you passing those parameters through machine learning, like viewing geometry you are taking?
Yes.
So temperature profiles you are taking, this humidity profiles you are taking, you are passing into the machine learning model.
Okay, no. These profiles are go as an input to the RT models, and we directly get the total radiances and the view zenith angle. So the idea was to make a machine learning model robust and specifically for the Trishna mission with minimum inputs. So we have as a part of the TO radiances, we will having only TO radiance, view zenith angle, and water vapor as an auxiliary input from the visible bands. So we are using only these three as a input variables to get our atmospheric.
Got your point. So we can use many other parameters also.
Yes, that's what the idea was, key also to use the temperature as one of the other inputs.
Correct. Okay, thank you.
Question, I have two questions.
Yes, sir.
That LST retrieval requires atmosphere and emissivity correction.
Yes, sir.
So you have concentrated mostly on the atmospheric correction.
Yes, sir.
So what about the role of emissivity?
Okay, so the temperature emissivity separation algorithms is it simultaneously retrieve both LST and LSC values. So we doesn't need any LSC inputs from the other data sets, and it simultaneously retrieve both the parameters. So we don't need any input of emissivity into the model.
You don't require any spectral emissivity.
No, sir. We need the spectral library to make our model coefficients, which is the MMD coefficients. We already have a large number of data sets from the eco stress library, Ester library, SAIL library. So we use that to make our model coefficients. And once our coefficients are tuned, we can directly use that to simultaneously retrieve both LST and LSC values. Yes.
And you have shown your in your validation true radiance. Here.
Yes, sir. The true radiance
radiance
means this simulated radiances from the RT model equations from the Mortran. That
No,
Mortran.
Then your validation is with respect to only the model simulation.
Yes, sir.
What about with the actual data?
We cannot retrieve actual surface living radiances. It could be only retrieved to the models.
No. What I mean is that you have retrieved down, means machine learning based finally resolved these surface living radiance, and you are comparing with the true radiance. Okay, so that true radiance is actually simulated radiance.
Yes, sir.
Right?
Yes, sir.
So that is where my question is whether you have used any satellite based true radiance or some other sources like suppose EcoStress is providing similar kind of data.
Okay, sir.
Otherwise, it all between simulated versus machine learning.
Yes, sir. Because prior to launch, it should all goes based upon the simulations data sets only. And in case of EcoStress also, we have only total radiances. It doesn't give intermediate products like surface living radiance or the downwelling radiances to compare it with the EcoStress product.
Yeah.
Where at least you will get the surface living long wave and incoming long wave. So that data at least independently you can use for checking.
Okay, sir.
For picture, that suppose you are getting 0.98. So whether it is
you are getting 0.9K. So whether it is truly 0.9K, so with some in situ or maybe from some measured radiance, you have to.
Okay, sir. We will try to incorporate that.
Just to add, for academic purpose and for getting exactly the picture, one can use some tower data where all components are available. Practically, what mission will require is based upon TOI radiance is how would you proceed. So that has been done. End to end, this is based upon SAC approach. The first is atmospheric correction, getting land living radiance, downwelling radiance, and correcting it for atmosphere, and then putting it in modified test, which gives you separation of emissivity and temperature. So that has been full chain has been tested on real scenario. For getting the actual picture from theoretical modeling, 70-80% percentage of points have been used for training, 20 independent percentage has been used for validation. But you are right. On some of the sites, if all those components are available, one must use and one can have that. Here. Okay. A good suggestion.
It is available, you can use that, because finally TES algorithm, you are using the surface living downwelling surface living radiance for decouple it, right? So up to that level, you can use that.
Yes.
Wherever.
I think there is a presentation for tri-kelnet, something like that.
Yeah.
So with that input, we can try it and use it as well.
Yes. It will give some more true picture, but it's a good one.
That's a nice conclusion.
Thank you.
Thank you. So we'll move on to next presentation by Dr. Eshwar Rajasekaran from Indian Institute of Technology, Mumbai. He will present on improving the spatial temporal resolution of LST in the Indian context, lessons learned and way forward. Eshwar, you have 15 minutes.
Yeah, I'll be taking less time than time. Yeah. Okay. So good evening, one and all. So till now we are hearing about the actual retrievals from the Trishna mission, whereas this one is like slightly off track, where we'll be discussing about our need to obtain high spatio-temporal land surface temperature data, at least until all the missions like Trishna, SBG, and LSTM comes into picture. Still, we have to rely majorly on coarse resolution sensors such as MODIS or VRS, or sometimes we also get Landsat 8-9 and EcoStress data sets. But still, like how far we can go down into getting like up to like a field level or sub-field level LST measurements for various applications. So whatever work we have been doing for the past few years has been summarized in this particular talk, and I'll try to keep it as short as possible to provide a broad overview. So basically the trade-off between the spatial and temporal resolution of land surface temperature data sets is quite well known. And the two approaches that we often use is one we call as disaggregation and one we call as spatio-temporal data fusion. In disaggregation, as we all know, we try to combine the land surface temperature data with some auxiliary variables at coarse spatial resolution, and then using the same auxiliary variables at fine resolution. Primarily, these are visible NAR and SWIR data sets. And once we combine this fine resolution auxiliary data sets, we will be able to get land surface temperature data at a fine spatial resolution. So this is started with like the pioneer paper by Kustas in 2003 when the discharge model was proposed. Another approach is spatio-temporal data fusion, where we need both high and coarse spatio-temporal resolution LST obtained at the same time, and then we will be building models using these two data sets to provide synthetic high spatial resolution data whenever you have a coarse spatial resolution data that is available. Say, for example, if I have like a MODIS observation from Terra and Landsat observation obtained at the same time, then on the next day, when Landsat observation is not there, I can predict Landsat-like LST using MODIS Terra observation. But spatio-temporal data fusion has practical difficulties, especially with respect to the Indian context. Here in this slide, I have just listed the number of data sets available, like clear sky LST data points that are available over 2 sites in India. One is Berambadi and one is Navagam. 2 are the sites which are going to be like test sites for the Trishna mission for 1 year. As you can see over Berambadi, like out of 365 days in a year, we have only 119 MODIS dataset from Terra. It was clear sky datasets. Remaining datasets are gone. And total Landsat 8 and Landsat 9 were 11 and 7 respectively. And the total number of days in which both MODIS and Landsat were concurrently available is just 5 days. So for the remaining 360 days, concurrent data sets are not available. But if we look at like Navagam, the situation is much more rosy. Like we get a better picture. We have like 46 days in which modus and data set are available. So this tells us the spatio-temporal data fusion approach is rather limited by the concurrent availability of coarse and fine spatial temporal LST data sets, which may not be available all across India. Over some sites, we have a severe limitation of especially high resolution data set, primarily due to cloud cover. That is one. And second limitation of this approach is the timeliness or the concurrent data acquisition by both high and low spatio-temporal resolution sensors. Even if there is some mismatch in the time, then the spatio-temporal fusion algorithms may go wrong. An example from like a machine learning model is given here, like from maybe the first image on the left side, we have like a modus terra nighttime LST. On the figure B is eco-stress LST obtained during nighttime. And the third picture is like the machine learning model predicted LST. But this machine learning model has been trained to predict fine resolution LST using daytime modus. Like we know that different objects have their own thermal inertia properties. So water tend to be naturally, like water will be cooler than the land surface during daytime, and during nighttime it reverses. Land will be cooler than water. Whereas if you look at it in this picture, if you compare the eco-stress LST with the machine learning predictor LST, you can see the water bodies, like which are the red patches in the middle image are appearing like a blue patch in the rightmost image, which tells us, okay, if we use like a coarse resolution data from the daytime to predict nighttime images, this kind of patches or this kind of thermal inertia mismatches we may miss. So this is another problem in using spatio-temporal data fusion approaches. The both fine and coarse spatial resolution data set must be obtained as close as possible, and we cannot extrapolate daytime LST to nighttime and vice versa. So we started working on the disaggregation approaches where the visible NIR and sphere images were available at a much finer resolution than the thermal data sets. So we started testing with the classical district model over different sites in India. We started with multiple scales, like starting from geostationary data using INSAT data at 5 kilometers. Even we tested the approach with Kalpana data at 8 kilometers. Then we went to modus. So we started testing the district approach basically. And then we started looking at, okay, why only NGVI? Can't we use some other vegetation indices based on like, the land cover conditions? And what we found based on our analysis is the auxiliary variable, the single vegetation index, which we use as the auxiliary variable in the district model, is actually depends upon the dryness of the site. For sites that are dry, actually we should use SWIR indices based indices such as NDWI, and only when the site is completely wet and completely covered with vegetation, NDVI or fraction vegetation cover gave a better result. So the choice of vegetation index really matters when we work with such district like very simple disaggregation algorithm with single auxiliary variables, and the auxiliary variable has to be carefully chosen. So also in addition to that, the simple auxiliary, basically the distrat type of models which works only with the single auxiliary variables also has some sort of like a boxy appearance, which is because of some addition of some residuals. So we shifted our focus from using a single auxiliary variable to a multivariate disaggregation where we use more number of auxiliary variables. So we came out with a principal component regression based method using like 8 plus auxiliary variables. So we tested this with the traditional or the classical distrat method. We applied this data at different sites, both in India as well as the USDA sites in collaboration with Dr. Kustas and his group. So what we found was like the traditional distrat method works well over homogeneous sites. If you look at this in this table, the Jaisalmer site is a desert site which is rather homogeneous compared to the other sites, Navagam, Malegaon, and RIP 720, which are quite heterogeneous croplands, and Malegaon and RIP 720 sites are like vineyards. So basically, as the site heterogeneity is more, the more complex or the multivariate disaggregation yielded better results. However, for the homogeneous sites, the simple distrat algorithm worked much better, like slightly better than your distrat approach. So then came the next problem. Okay, we are able to use or we are able to obtain the single snapshot of LST at a high spatial resolution, but what about the diurnal LST? That was the next question that we asked. So then what we did is we tried to combine the multi-temporal modus observations available in a day with a classical diurnal temperature cycle modeling approach. So the diurnal temperature cycle modeling approach is has been used quite frequently in the literature, especially for gap filling of geostationary observations and so on. So what we did is we combined our spatial disaggregation model with this particular DTC model called GOT01TS model in order to obtain the diurnal variation of land surface temperature. So here also we used our multivariate disaggregation as well as the univariate disaggregation, the distrad, to test the approach. So here what we used is we used the 4 modus observations available within a day, like 2 from Terra and 2 from Aqua. Sometimes if Aqua observation is not available, we replace that with VARS observation. So then these 4 points were fitted to the DTC model to attain the diurnal temperature cycle. And the results are quite significant. It tells us okay, this approach really works, especially during clear sky days, in order to obtain the diurnal temperature cycle over different sites. And this is pretty simple. All we need is one high coarse resolution data set. And as long as we have the fine resolution auxiliary variables that are available, we are able to satisfactorily obtain diurnal cycle of land surface temperature over multiple sites. Then obtaining 4 modus observations in a day again becomes tricky. Not all days we will be having the luxury of getting 4 modus observations. So then we again wanted to apply a similar approach, but with geostationary scale datasets. So geostationary scale datasets, even though they can provide data once every 30 minutes or 15 minutes, they have a much coarser spatial resolution. So we thought of applying the multivariate disaggregation, what I showed in the previous slide, called the PCI disaggregation. And the next approach, we used a 2-step disaggregation approach where we combine spatial disaggregation plus a temporal disaggregation also. Say, for example, here we wanted to disaggregate the parameters involved in the DTC model itself. So it's not only a spatial approach. If you look at the figure on the left, the scheme 1 is a very simple spatial disaggregation, starting from geostationary scale to field scale, that is 100 meters. But if you look at the scheme 2, that's a hybrid approach which combines spatial disaggregation plus disaggregation of the DTC model parameters. So it's a quite tricky model. So what we found is, again, we tested it on multiple sites. One of the example over the US GrapeX site has been given here on the figure on the right. So what we can see is both the approaches are giving similar results in terms of RMSE, but what we observed is in the direct approach where we directly downscale this 2 kilometer data from GOES to 100 meters, we are observing some sort of a boxy patch. That boxy patch is not seen in the hybrid approach. However, the hybrid approach sometimes misses the extreme LST values. So both the approach has their own pros and cons. The direct downscaling comes with a boxy appearance, whereas the 2-step approach comes with its inability to pick the extreme LST values, very high and very low LST values. Maybe this could be due to the very coarse spatial resolution of the geostationary data. But if we start with the fine resolution data itself, we may be able to land up with a better disaggregated LST product. Then we are also trying machine learning based approaches because, these kind of approaches, what I showed in the previous slide, has to be applied on a daily scale. And for every pixel to fit a DTC model, it might become computationally little expensive. So what we planned is okay, can we build a machine learning based model? So that we are doing now. We are trying to predict, we are trying to use eco-stress data as the basis, and using eco-stress data for multiple modus and VARS observations, we are trying to downscale 1 kilometer to 100 meter data sets, and the model is working pretty good here also. So what is the context for Trishna LSTM SBG for this disaggregation? Even though these missions can provide data at the resolution of say 60 meters, still for field scale work or sub-field scale work, especially in the Indian conditions, we may be needing a much finer resolution. LST up to say 10 meters or 20 meters might be the need, looking at the heterogeneity of the Indian croplands. So combining these data sets with say Sentinel-2 data sets, which are available at say 10 or 20 meter resolution, could be one stopgap solution. In addition to that, as we know, all these missions are going to have an overpass time of around say 12:30 in the afternoon, where none of the other a coarse resolution sensors such as Modus or VRS, they don't pass. They have a slightly offset time. They pass around 1:30 or 2 o'clock in the afternoon. So getting a common overlap between Modus and these 3 future missions will be difficult. So I think using disaggregation will be like the better approach to use these data sets to go ahead. And also like what we have found is like if the starting resolution itself is like pretty fine, then the level of downscaling that we are able to perform increase. Say for example, if we start with say 1 kilometer data, and if we have like a threshold of say 2 Kelvin RMSE error, then we can do up to like say a 480 meter, just one time downscaling. That itself we reach this 2 Kelvin error. But say if we start with say maybe like 100 meter data, even we can reach 20 meter data with much less error. So if the starting if the starting resolution is much finer, the data set contains more information which helps us in doing like a better downscaling. So in this context, Trishna, LSTM and SBG will be really useful as they provide 60 meter data sets, and rather than using any coarse data set to bring it down to 20 meters, I think these data sets will be like the much better, like the data sets to go to field scale, especially in the Indian context. So what are the issues and challenges? Still, these approaches are like kind of semi-empirical. We need some sort of like a model fitting when LST data is available. So this has to be done repeatedly. And in addition, the machine learning algorithms need large quantity of data before they can be trained efficiently. That is one. The major problem comes in validation of these sort of disaggregation approaches. Like we have just 1 point measurement where we try to compare both 1 kilometer data from MODIS as well as 100 meter disaggregated data. So what happens is like there will be obviously like a like a scale mismatch between your ground observation and your satellite data. Especially this happens at like MODIS scale. So that could be one problem, like the representativeness of your ground data point may not be there, which could be artificially blowing at the error. That could be one. Plus, even for in situ sites, we are using like a simple 4-component net radiometer or like a simple radiometer. So the emissivity of the sites are not known. That is one. Uncertainty in the disaggregation due to multiple LST retrieval algorithms, sensor specifications, and viewing geometry. They are not taken care. Each LST product comes with its own uncertainty because of various factors. We are not accounting for that till now. That should be studied in detail. And the DTC modeling approach that we have showed will be applicable only for clear sky days. For intermittent cloudy days, again, we need multiple observations. And even when all the three missions, Trishna, LSTM, and SBG, work simultaneously, providing us daily observations, still modeling DTC will be a challenge because ultimately we are having only one fine resolution data point. So we should develop an approach where we combine geostationary data with such data sets. So how can we proceed further in this? So maybe we should be having both the approaches, multivariate disaggregation as well as machine learning approaches combinedly running. So till 2-3 years of data becomes available, we can use multivariate disaggregation. Then we can try moving on to machine learning when the data set become, or when our database becomes really rich. We should be developing super sites for validation of disaggregated LST. Like within say 1 kilometer patch, we should have like a multiple like a high precision radiometers that are fit similar to like some sort of like a CMULF radiometers or something, so that we are able to validate both coarse as well as fine resolution LST with a much higher confidence. That should be done. LST directional normalization or combining DTC modeling with kernel directional models should be the way forward to go to account for the directional effects of LST. And then again, one more hybrid approach, combining geostationary data to give the DTC params, which can be combined with Trishna or LSTM or SBG sort of data sets to predict field scale diurnal temperature cycle modeling. And using these data sets for various applications. Tomorrow, 2 of my PhD students, Adira and Kukusara, will be presenting the applications of the downscaling approaches we do, one for evapotranspiration modeling, one for heat wave monitoring over urban cities. So maybe you are welcome to attend the talk. One in the ecosystem stress session and one in the urban heat island session. So the applications forms the really critical part of such approaches that will drive home development of these sort of spatial disaggregation approaches. So with this, I end my talk. I thank all my collaborators for sharing data and their advisors. And thank you very much for your patient listening.
Thank you, Dr. Isro, for your informative presentation on disaggregation. Now the paper is open to the floor. Any questions? Yeah, okay.
Yeah, Dr. Isro, I have one query that when we perform such type of downscaling operations, so scale, heterogeneity, and topography. So whether it is affected by all factors? And if it is affected, then which one is most critical?
Okay, so scale mismatch means like between your ground target and the satellite, or?
Yeah. When you're coming down from a coarser resolution to the final one, so what could be the ratio of both the satellite spatial resolution, or how much you can come down, or you keep on coming down, then like it is again to come down at what factor?
Okay, okay.
And then heterogeneity of the surface and then topography of the region.
Okay, okay. So basically in the multivariate disaggregation, we take care of the topographic effect. We use DM also like one of the predictor variables or for the model to get itself trained. So that takes care of the topographic differences to some extent. But most of our test has been carried out over like a relatively flat domain. We have not yet tested our approach over mountainous region, mainly because of also the lack of validation data for us. Whatever validation data we got, it was available over like croplands or like flat terrain. That is one. So it has to be tested over mountainous terrain, how complex it is. That is point one. And point two, regarding your first question about how far we can come down, that depends on the starting resolution of the the starting resolution of the data which we are using. Say for example, that's what I said, like, let us say like I need LST with a typical RMSE of say 2 Kelvin. If I start with MODIS data with 1 kilometer, most likely I will be saturated at say 500 meters, just one time, like a 2x down scaling. But let us say like I start with say like a 500 meter data, I will be able to get the similar error after downscaling up to say, rather than 2x, I may go up to 4x. So the starting resolution, as it becomes finer and finer, the amount of disaggregation that you can do also, the chance increases. So that's what I said, like going from say 100 meter data to 20 meter data or 60 meter data to 20 meter data is like much more reliable rather than going from like a much coarser resolution. So even we talk about disaggregation, still we need fine resolution data sets even to go to the subfield scales. We cannot say that, okay, I'm having MODIS data, from MODIS I'm coming to 20 meters in Indian context. That's not going to work. I need Landsat type bare minimum, like 100 meter, finer than 100 meters, so that I can go up to 20 meters. So there is a limitation up to which we can do this disaggregation.
One curiosity, which one is more critical out of these three?
At least to the approaches that we have tried, the accuracy of the coarse spatial resolution data is more critical. If the coarse resolution data itself has a lot of errors, that's going to carry forward always. We are not going to improve on it.
Ishwar, I have one question.
Yes.
What is the practically for this Trishna mission? What is the best resolution we can get after disaggregation? What is what in your?
Can you please repeat? Can you please repeat your question?
For Trishna mission, I want to have a disaggregation algorithm so that I can achieve the high resolution LST.
Okay.
What would be that resolution?
That's what, like, I'll be targeting 10 meters or 20 meters.
10 meters.
If I'll be using like a univariate disaggregation, I can go up to 10 meters using Sentinel-2. But if I want to use sphere data sets also for my multivariate disaggregation, I will stop myself to just 20 meters.
LST speak for LST, you can come to 10 meters.
Yeah, that's what, depending upon my disaggregation approach, because the auxiliary variable also has to be available. But say, I can say like 10 meters.
Okay, thank you.
Yeah. Yes.
Yeah, actually, when you do principal component regression, you use variance in the data for decomposition, right?
Yes.
So that variance includes the noise in the data, right? That variance can be noise in the data also. So how can you actually consider, can you segregate that noise when you do this principal components decomposition when you consider PCR?
Okay, so first thing is like, we are like limiting ourselves only to like, like first few principal components where we believe like the effect of noise is reduced. We are not using all the principal components. Generally, our basic notion is like, let us say like we have like 8 principal components for like the 8 layers that we are using. Maybe like the higher principal components may be carrying the noise, whereas like the first levels will be carrying like the information. That's like the notion that we are following. So we assume, we are not actually tested it, but we assume like the noise is not there. Plus, as I said, if the data, the starting data itself has some sort of like a noise or error, it's going to get transferred to your disaggregation too. We cannot rely on it. So the quality of the original data, what we are starting, is actually critical.
Okay, thank you.
Thank you.
So we proceed to our next presentation. And this declining clear sky TOA short wave radiation in Northwest India, the role of vegetation growth by Manoj Mishra.
Yeah, so good evening. So I will be presenting on declining clear sky top of atmosphere short wave radiation in northwest India, the role of vegetation growth. So actually, as you all may be aware, that Cirrus instrument on Aqua and Terra satellite measures this outgoing short wave and long wave fluxes, and it is measuring these fluxes since 2000, and so around more than 20 years of data is available now. So we were doing some study, we were analyzing some of the trend using this top of the atmosphere short wave radiation. So in the this northwest India, that is around region around 27° latitude and 73° longitude, that is in Rajasthan region of this India, covering this Nagaur district. So that is a semi-arid region, and we found that there is a significant this trend of this negative trend of this outgoing short wave radiation. So we found that around 6.5 watt per meter square have been there is a decrease of around 6.5 watt per meter square during this 20 years. So we thought of actually this we used clear sky top of the atmosphere short wave radiative fluxes, not the cloudy sky. So this decrease we have seen in the clear sky cases. So we thought of analyzing other variables like vegetation dynamics, that is NDVI from the Moody's and AOD. So we found that there is a significant increase in this NDVI during this season from 2000 to 2022. So, and similarly, we have seen the corresponding albedo also have increased significantly during this time. And so, AOD also, there is a significant decrease during this time. So what is happening is like there is a vegetation growth that is causing this less aerosol production, and because of that AOD is decreasing. So, and similarly, we analyzed this land surface temperature, and we found that there is a significant decrease daytime velocity during this period. So, and interestingly, this there is not much increase in this nighttime velocity, and similarly during this time period, if we see the precipitation, there also a significant increase is there. So what is happening there? This during this period, there is a precipitation increase, as well as there is a lot of irrigation project which is causing increase in soil moisture, and that that is causing a vigorous growth in this vegetation. So that we can see this image we have generated from Google Earth Engine from 1990 to 2020. So we can see that there is a very clear growth in this vegetation, and that like from 2010 onwards, this growth is much larger. So we analyze the seasonal trend also, and this trend is existing in the all the seasons also. So our findings are like NDVI showed an increase, indicating that vegetation cover has been expanding. AOD decrease, suggesting lower aerosol concentration, likely due to reduced dust or pollution in the atmosphere. Surface reflectance also declined because of the vegetation growth. So together, these changes appear to be driving the observed decrease in short wave radiation fluxes. So, and we can see that this albedo decrease and vegetation increase, they are going hand in hand. So actually, so this and so what is happening? A positive radiative forcing indicating more sunlight is being absorbed, but at the same time, there is a this vegetation growth. So that is causing this biophysical feedback, and that is resulting in the decrease in land surface temperature. So because of this biophysical feedback mechanism, we are experiencing this decrease in land, significant decrease in land surface temperature. So we can conclude like vegetation change in Northeast India driving significant change in radiative fluxes, particularly through change in surface albedo. And the greening coupled with enhanced evapotranspiration is mitigating daytime warming despite the positive radiative forcing. This finding highlights the importance of considering the interplay between vegetation dynamics, aerosol, local climate, when designing climate change mitigation studies. However, this is just a simple study. So this is just a first step. We need to go further, like we need to analyze how the surface fluxes are varying, how this diurnal changes, whether there is a change in this diurnal variation of the fluxes. So all these need to be explored, and I think Krishna observation may help in analyzing these complex relationships. So with this, I end this talk. Thank you.
Thank you, Dr. Manoj. Before I open for the question, I have one question to you. When it is true that in that region vegetation increases, so LST will of course decrease and albedo will also decrease. Yeah. Why this short wave, this radiation is decreasing? Is it incoming short wave or outgoing dust?
Because vegetation in desert region, desert means semi-arid region. So vegetation growth will cause larger contrast. So means it will become much darker. So albedo is changing. So because of that, outgoing.
So it's a reflected component of short wave radiation, not incident component. Outgoing. Okay, then it is linked together.
Yeah.
The now question is open to the audience. Any question? Oh, if there's no question, thank you,
Okay,
Dr.
thank you,
Manoj,
sir.
for a good observation. So we are proceeding for the last presentation of this session. That is done by Dr. Disha B. Kardani. Add sensor signal simulation from thermo-infrared bands of Trishna mission using Matron radiative transfer model.
Hello and good evening, everyone. I am Disha Kardani. I am a research scholar. Recently, I am working as a junior research fellow in the Trishna mission under the SAC TDB program of Isro under the guidance of Mehul Pandya, Aswin Gujarati and Dhirat Shah. So I am very honored to present our recent work on a Trishna mission at sensor signal simulation for the thermal bands of the Trishna using the Motran radiative transfer model. So basically what we are doing is checking the sensitivity of the each of the bands of the Trishna by varying the different parameters like surface parameter, atmospheric variables, and the sensor characteristics. How each of the bands is responding by varying these much parameters. And why we are studying this? The first one is the application is when we are studying the sensor system involving the target, atmosphere, and a sensor. For that we are required that sensor signal simulations, and when we are retrieving the different geophysical parameters like land surface temperature, land surface emissivity, and for to develop different algorithms, it plays a very important role. And the third one is we all know that for the data calibration and the validation, it is very important to simulate that sensor signal simulations. So what are the key parameters? From this figure, we can easily understand that first one is the surface emitted radiance. So how much amount of the radiation that is emitted by the Earth's surface? It having a spectral dependency of the surface emissivity. Second one is the atmospheric interaction. We all know that our atmosphere is made up of the gas molecules and having a water vapor content. So this layer also emits the radiation, and that is also captured by the sensor. Third one is the reflected solar radiance. As our sun emits the radiation, hits the Earth's surface, and some part of the radiation is absorbed by the Earth's surface, and some part of the radiation that is reflected by the Earth's surface and received by the sensor. The fourth one is the sensor spectral response function. It is basically the sensor characteristics. And the fifth one is the sensor viewing geometry. At what angle sensor is observing the Earth's surface or atmosphere. So one of the major application of the thermal infrared region is the retrieval of the land surface temperature. Why it is important? Basically, it plays a very important role in climate monitoring and the estimation of the Earth radiation budget. So how one can retrieve that? So using the Planck's inverse black body law, and using the top of the atmospheric radiance, we can easily retrieve the land surface temperature. What equation is okay? Why the land surface temperature is very important? I explained that at sensor signal simulations are very crucial in the retrieval of LST because the top of the atmospheric radiance is affected by different parameters and how it is responding to in the each of the bands of the Trishna. So I explained elaborately that we are simulating the at sensor signal simulations for the thermal infrared bands of the Trishna and evaluating the sensitivity of the Trishna bands by varying the different parameters. So what are these parameters? First of all is the land surface temperature. Basically, it is the radiometric skin temperature of the Earth's surface. Second one is the land surface emissivity. Third one is the water vapor. Fourth one is the viewing geometry, viewing zenith angle, and ozone and the aerosol. So how one can simulate the sensor signal? There are number of ready-to transfer models are available like MOTRAN, RTTO, etc. Here we are using the MOTRAN, Moderate Resolution Atmospheric Transmission Model. It provides us the simulation in the thermal infrared region as a function of different parameter as I showed in the previous slide. So how the MOTRAN works? As input, it requires the model atmosphere, atmospheric columnar parameters, and etc. And as output, it gives us the total radiance, total transmission, etc. So in this slide, we have a detailed information about the sensor specification and ready to transfer simulation data. We have done little exercise here. We having a 4 bands of the Trishna, basically the relative spectral response of the Trishna bands. And in the thermal region, the major contributor in the atmosphere is the water vapor. So we are varying the water vapor from 0.1 to 3 to 6. As we are increasing in the water vapor, transmission in the each of the bands is decreases. So when 3 and 4 shows the differential absorption behavior, and it can be used as a in the split window algorithm to retrieve the land surface temperature. So how the land surface temperature effect on the top of the atmospheric radiance? Basically, we are keeping some of the parameters fixed, like water vapor 1.5 gram, land surface emissivity 0.99, and for the nadir view, we are changing the land surface temperature from 240 Kelvin to 340 Kelvin in the interval of 10 Kelvin. The first plot we can from the first plot we can observe that as we are increase the temperature in each of the band, top of the atmospheric radiance also increases. But how each of the band is responding towards the increases in the temperature? So in the right hand side plot, as we are increase the temperature from 240 Kelvin to 340 Kelvin, on the y-axis we having the change in TOA radiance per Kelvin in each of the band, but band 2 and band 1 shows the most sensitivity towards the change in top of the towards the change in land surface temperature. The second one is the change in emissivity by keeping the sum of the parameter fixed and changing the emissivity from 0.79 to 0.99 in the interval of 0.02. How each of the band having a top of the atmospheric radiance. From this plot, we can easily show that as we increase the land surface emissivity in each of the bands, top of the atmospheric radiance also increases. And in the right hand side plot, we shows that there is less amount of change in the top of the atmospheric radiance as we increases the land surface emissivity, but still the band 2 and band 3 shows the maximum amount of sensitivity by changing the land surface emissivity from 0.79 to 0.99. Third one is the major culprit in the thermal infrared region is the water vapor. So as we increase the water vapor from 0.5 gram to 0.5 gram to 6 gram per centimeter square in the interval of 0.5 gram per centimeter square, it's in each of the band shows the negative impact, and each of the band top of the atmospheric radiance is decreases with the increasing in the water vapor. And from the right hand side plot, we can see that band third and the band fourth shows the negative impact, shows that most sensitive with the change in the water vapor. The fourth one is as we changing the viewing zenith angle from 0 to 50 degree, indirectly we are adding the atmospheric path length. Additionally, the absorption also increases. So the total radiance in each of the bands also decreases. And band 1 shows the maximum sensitivity by increasing in the viewing zenith angle. So this is the summarized table of what are the 4 parameters we are changing, and highlighted box shows that the band number, and each of the band in the band 2 is most sensitive with the land surface temperature, band second and third is most sensitive with the land surface emissivity because it lies at the peak emission of the thermal radiation, and with the relative humidity, band 4 is most sensitive one because it lies at the edge of the atmospheric window region, and with the viewing zenith angle, band 1 is the most sensitive one. We also have checked the sensitivity of the atmospheric profile we are giving as input in the RT model. There are some of the parameters like air temperature, relative humidity, ozone, aerosol, and we are keeping some of the parameter fixed. So in this summarized table, we can say that as we increase the air temperature by +2 Kelvin in each of the layer, we are observing the change in radiance and change in temperature also. In the number, we can say that the band 2 is the most sensitive one by increasing in the air temperature. And as we increase the water vapor from +20% in each of the layer of atmospheric profile, band 4 is most sensitive one. And as we increase the water vapor from normal to double, we are observing that band 2 and band 3 is most sensitive one. And as we change the aerosol from urban to rural, the band 2 is most sensitive. As we are in general not considering the aerosol, but still we are keeping here that is shows the less sensitivity with the change in aerosol. So what is the conclusion? We can say that we have to do the at sensor signal simulation to access how thermal infrared bands of the Trishna are responding towards the change in atmospheric variables, surface characteristics, and the sensor characteristics also. And it optimizes the performance of the sensor. And what is the future scope? Basically, when we are developing the different algorithms to retrieve like land surface temperature and emissivity, and for the data calibration and the validation, we are required the at sensor signal simulation at the baby step. Thank you.
Thank you, Disha. A good presentation. You have done all academics of which factor influences what. So now the questions from audience. Any question? Then I have one question to you. There's one question. Yeah.
Yeah, just had a simple question for you. Did you do any predictive analysis? I was just curious, did you have any idea as to which band was going to be sensitive to which parameters going into this? Did you know that band number 2 was going to be more sensitive? I'd just like to understand your thought process before you did the investigation.
We have not done any prior prediction, but from this we can say that as the band 2 and 3 are lies at the peak emission of the thermal infrared radiation, that's why the band 2 and 3 most sensitive with the parameters like land surface temperature and the land surface emissivity. And with the ozone having a maximum out of the absorption in the band 2 and 3, that's why with the ozone also band 2 and 3 is most sensitive one.
Okay, all right, thank you.
Thank you.
Any other question? Disha, I have one question. You told that there are so many variables for a given output, no?
Yeah.
So many things influences this. So, in your opinion, while simulation you might have seen that suppose I have 2 important culprits which changes my output. One is say water vapor, the most important factor, as you correctly say. Other is that what you call emissivity. Suppose I am not able to know the true emissivity by some way, or I have uncertainty. Which is more influence me in my result, the water vapor content or the emissivity? Hoping both that both are going to influence. In your opinion, which would be more influencing?
As we are retrieving the land surface temperature and emissivity. It is the application part. But when we are retrieving with the temperature emissivity separation method, we are retrieving simultaneously. But the thermal region, the edge sensor signal simulation coupled with the atmosphere and the surface. So water vapor have its separate role. So it's a main culprit.
Okay. Thank you very much. So if there is no other question, so we can conclude this particular session. And I thank all the speakers for their informative presentations and deliberating how they are thinking to see that products are going to come. And it shows that a lot of preparations are there. So obviously with some improvements or more sensitive analysis, things are going to take place well. I take this opportunity to thank the organizers, Dr. Bimal and all the team, for giving me opportunity to come to this seminar. And now I request Dr. Philip to say some words.
No, I just want to thank all the speakers again. And it seems that a lot of work has been done, but we still have a lot of work ahead. And so that's very nice to hear that and to share. So thank you very much to all the speakers again.
So thank you. So this was the last technical presentation of today's last session. So before we conclude the session, there are some important announcements. But before the announcement, I would like to thank, on behalf of organizing committee, I would like to thank both the chairs, Dr. Philip Gameth and Dr. R.P. Singh, for conducting the session on our request. And thanks are also due to Rohit Nagori, who was the rapporteur of this session and who has noted down all the minutes. And now I would like to request Philip Massogren to give a token to Dr. R.P. Singh. Thank you, Dr. Philip. Now I would request Nagalakshmi Madam to give memento to Philip Gameth. Thank you. Now I would call Dr. Rahul Nigam to make some important announcements before we conclude this session. Dr. Rahul.
So after in morning, good morning. Now it's good evening to all. So before we disperse for today, we have some announcement. That first announcement is that we today started a little early to make sure that all people have get biometry and electronic clearance. Gadgets should be clear. So today we start 15 minutes late, especially for Novotel and Marriott who are staying in. So the bus will reach at Novotel at 8:30. Another is important announcement is tomorrow we have a poster session. So everyone who is having a poster, please come with your poster print, and we have in the back side. Oh, in that side we have that. We have a posters we have to display, and we have a special session for that poster, so everyone can be interact with all the presenters. Another important is that after when we come in morning, we have a multiple parallel session, and first parallel session will start in this auditorium only, but in the basement we have another conference room. In that we have a inland and coastal inland session as well as urban. Whereas in afternoon we also have one session in solid earth and cryosphere that will be going to be happen in a different auditorium, and we have in horseshoe room. And after all session, all people have to come in this auditorium only. Then we have a one culture event. And after that, we have a dinner which we hosted by the director SAC. And after that only, most probably by 9:30, we'll disperse from the auditorium. So, and another very important announcement, and for basically those who have a presentation for tomorrow, please send your presentation by up to 12. Okay. So in morning, at least our people can download and present your presentation here. Okay. So still we have seen that many people have now sent their presentation. So please send your presentation as soon as possible. And you know the email of this workshop. So kindly send your presentation. Thank you, and thank you for your kind support. Thank you. And another thing is that ecosystem, those who are working have an ecosystem that will be continue here only. And last day, all session, third day, all session is here only. So ecosystem people come here only, but coastal, inland, urban, they have a separate room in this room. And Soledad and Chrysler, they have to move in afternoon to another auditorium. Then people will convey you where is that auditorium. Thank you.
So thank you all for today's session. High tea is arranged in the basement. Please have the high tea and then go to your respective places. Thank you.